telescopes to push back the darkness. The cosmos. There are many puzzles in a universe. There are times when the things we cannot see are more important than what we can see. We use the visible to piece together the great mysteries of the invisible. Take the behavior of matter around black holes, for example. The mysterious, still unexplained phenomenon of dark energy is revealed by distant stellar explosions. The age of the universe is estimated by studying distant stars. Cosmology is the study of the universe's structure and context. We study how the universe functions as a whole, how it is currently and will be in the future, and how things within it form. Cosmology is a little like being inside a building, examining the switches and outlets we can see on the surface to determine the wiring inside. Space is a vacuum, but its objects are part of a larger structure, and astronomers must understand this structure's physics before understanding how the features function. Looking out at space is like looking back in time. Our location receives light from the farthest objects in the universe that left those objects billions of years ago, so we see them as they were then. How do we see these farthest objects when we capture their light? Most distant galaxies are more minor, irregular, and lack clearly defined shapes. Hubble could see these distant galaxies before any other telescope. After observing a nearly empty patch of sky for 10 days, astronomers turned Hubble on what appeared to be a roughly bare patch of sky. The team was taking a risk. Most Hubble observations take only hours, and the time was better used on less speculative projects. Hubble might not have been able to see the objects the astronomers hoped to find, because they were too faint or too small. The search yielded the now famous Hubble Deep Field image, containing 3,000 galaxies, large and small, amorphous and shaped, burning in the depths of space. Astronaut Hubble looks back in time. The farther Hubble gazes into space, the farther it gazes back in time. Recent surveys, such as Hubble's Ultra Deep Field, HUDF, and the Great Observatory's Origins Deep Survey, GOODS, provide images of vast collections of galaxies, including some that date back to when the universe's time was less than 1 billion years old. The Hubble Space Telescope teamed up with other observatories in the following years to study small patches of the sky in high-resolution, long exposures and multiple wavelengths. This chart shows Hubble's most significant deep sky surveys and their covered regions. We can follow the evolution of the universe with images. The most distant parts of the visible universe are littered with tiny red dots, the shapeless building blocks of galaxies whose light has been stretched by the expanding universe into an infrared glow. As we move closer, we see galaxies colliding and merging, increasing growth. Further away, we see versions of the large, stately galaxies we know today. Seeing how galaxies have evolved can show how the universe we know today evolved from a uniform void to an uneven universe ready for stars and galaxies to form. Furthermore, the differences in these galaxies allow us to learn about the first stages of the universe, the part we can't see. There was already some structure when the galaxies formed, or the spread of matter would have been even. In contrast, we see the coalescing of groups of importance, small pieces that began, collided, and merged. This Cepheid variable star in galaxy M100 doubles in brightness during each pulsation. We are being beamed down from the sky with the answers to the universe's age. We know the universe has been expanding since the Big Bang. So, if we can measure its size and rate of expansion, we can calculate its age. There is more to it than you might think. All estimates are based on the brightness of objects, since you can't extend a ruler to the stars. Cepheid variable stars are a particular type of pulsating star whose brightness cycles indicate their inherent brightness. Observers find Cepheid variable stars in galaxies by comparing their intelligence with how faint they appear due to their tremendous distances to determine the distance to those galaxies. It's like judging a car's distance from you by judging the brightness of its headlights on a dark street. Cepheid variable stars enable astronomers to measure distances in space. Discover how pulsating stars serve as yardsticks for measuring the universe. Cepheid variables have been found in galaxies as distant as NGC 4603, 108 million light-years away. Their stars appear faint from Earth. It is complicated to distinguish the characteristics of the Cepheids found in NGC 4603. Cepheids were used to determine the distance to the galaxy. Up until Hubble, astronomers could only narrow the universe's age down to 10 to 20 billion years, a measurement with 10 billion years of error. Hubble conducted a comprehensive study of 31 Cepheid variable stars, determining the current expansion rate and narrowing the universe's age down to its most precise point. In combination with measurements by other observatories, observations of Cepheid variable stars in galaxies like NGC 4603 led to the estimate of 13.7 billion years old. With Hubble's observations, the universe's age changed from a vast range of possibilities to a precise number. It isn't just a matter of curiosity to know the universe's age. Having a timescale for the development of stars and galaxies will help refine our models of how the universe and everything in it formed. Numerous elements of cosmology were shaped by the actual age of the universe. Star and galaxy formation timelines required a period. Previous problems with the universe's age range have included things like stars thought to be older than the universe. We can now determine everything from the time needed for stars to die to how long it takes to produce elements such as carbon, nitrogen, and oxygen, the ingredients we need to survive. A watershed epoch is shown on each side. From the Big Bang to the present, it represents the universe's evolution over 13.7 billion years. As a result of reionization, the light from the first stars burned off a fog of cold hydrogen. A later epoch quasar pumped enough ultraviolet light to reionize the primordial helium with the black hole-powered cores of active galaxies. Radio telescopes were first used to study some familiar cosmic objects, including the remains of supernovae, distant galaxies, and influential areas of star formation. The quasars in these images appear to emanate from one galaxy, left, and two galaxies colliding, right. There are 1.5 billion and 1.6 billion light-years between the galaxies respectively. The entity that appeared to be a star appeared to be nothing more than a light point. As quasars are so far away and their size is so tiny, about the size of our solar system, the fact that we can see them with a telescope makes them among the most luminous objects in the universe. As Hubble proved with its high resolution, there was actually a galaxy hidden behind the glare of the quasar. He contributed to the quasar mystery. The surrounding regions of a supermassive black hole heats up and releases enormous energy and light, creating a quasar. As a result of multiple galactic mergers, Hubble found quasars in the centers of galaxies colliding or brushing up against one another and in elliptical galaxies. Quasars may be lit up by these interactions and fed by the central black hole. Observations by Hubble have also led to the discovery that these brilliant galactic centers are powered by giant black holes. Quasars weren't the only ones involved. According to Hubble, almost all galaxies with bright active centers have supermassive black holes feeding on the galaxy's matter. Additionally, the mass of a black hole is closely related to the mass of the bulge of stars forming the center of the universe, indicating that the formation of a galaxy is closely related to that of its black hole. The study of these monstrous black holes raises many questions about the formation of galaxies and the structure of the universe. Why do some regions form galaxies with massive black holes and others include rather ordinary galaxies? Why does the black hole phenomenon exist over such a wide range of sizes, from giant black holes in galaxies to tiny black holes a few times the size of our Sun? Is the formation of quasars just a stage in constructing supermassive black holes? The universe began with a bang and has been expanding since then, increasing the distance between galaxies with time. For many years, astronomers contemplating the death of the universe considered two main scenarios. Either the universe would keep expanding forever, the galaxies gradually drifting apart, or it would stop growing and collapse in a big crunch. In the late 20th century, astronomers believed the universe would expand forever at a constantly decreasing speed, coasting like a car out of gas, but never totally losing momentum. They began determining the rate of expansion. The brilliant stellar explosions known as supernovae could also be used to determine the distances to galaxies, just as they were for Cepheid variable stars. However, supernovae can measure distances even farther than Cepheids because of their incredible brightness. Astronomers used Hubble's clear vision to find the very distant supernovae needed to calculate the universe's expansion rate. Hubble's observations, however, upended the conventional wisdom. The universe wasn't slowing down. A study of the properties of the supernovae Hubble had imaged revealed that the universe was expanding faster and faster, as if it were being propelled. Understanding what is causing this acceleration will take time, since it doesn't seem to be a part of the glowing matter we see. How could this be? Scientists have no idea. A previously unknown dark energy might be the cause, but humans are only just beginning to understand the mysteries of this field. We must develop tests for a phenomenon invisible to us to describe and define dark energy until it is as clear as the stars in our own backyard. For now, Hubble continues to study the supernovae that might hold the key to unraveling this mystery. Dark energy's discovery. Known as Type 1a supernovae, certain exploding stars constantly emit the same amount of light. As a result, their brightness is nearly the same. Type 1a supernovae vary in brightness because some are closer to us and others farther away. By comparing the apparent intelligence of the supernovae with their actual brightness, astronomers can calculate the distances to the supernovae. The distance to the galaxies where the supernovae occurred is also indicated. Astronomers believed the universe's expansion would slow down as the distances to faraway galaxies increased. Cosmologists can measure the universe's expansion rate at different times in the past based on the brightness of Type 1a supernovae. Hubble found that the most distant supernovae were dimmer than they should have been, indicating that they and their galaxies were farther away. This contradicted the hypothesis that the universe expanded constantly or slowed down over time. Only if the universe was growing faster could they make sense of their space. Scientists involved won the 2011 Nobel Prize for Physics for their discovery. The science of the galaxy. Galaxies are islands of activity in a sea of emptiness, where the action takes place in space. We will never be able to travel far enough to see our Milky Way galaxy from the outside, composed of 100 billion to 400 billion stars. While we can observe the activity within our own galaxy and the interactions between galaxies far away, we can also watch the activity within our own galaxy. Hubble helped identify the sources of the universe's most powerful explosions, studied how galaxies formed, and studied stars near the end of their lives. The universe is revealed in its most precise and visible form by our observations of galaxies. Through the study of galaxies, we can observe the dynamics of the cosmos and how things form and change. We observe dominant galaxies feeding off their surroundings and stars, created under the influence of galactic gravitational forces, and puzzle over the varied shapes galaxies take. The study of galaxies past and present is essential to understanding the forces that shape our existence. The minor solar system resides within a universe. The United States Air Force deployed a series of satellites to monitor gamma rays in the 1960s. After signing the Nuclear Test Ban Treaty, the United States wanted to watch for the telltale radiation emitted by nuclear blasts. The satellites immediately began detecting gamma-ray events, but the study ruled out the possibility of bombs. In reality, there was no connection between the bursts and Earth. Scientists further investigated and slowly realized they were witnessing explosions with the power of 10 million billion suns per day, emanating from seemingly random points in the cosmos. Until then, the universe's most violent explosions had gone undetected. Gamma rays. What are they? Gamma ray burst 971214. This galaxy, located 12 billion light-years from Earth, gave off a gamma-ray burst in 1998 that was brighter than the entire universe for a few seconds. A release of energy of such a rapid and enormous magnitude had never been seen by astronomers before. The extreme events that produce gamma rays and why we look for them are explained by scientists. The gamma-ray burst of 080319b. During a powerful gamma-ray burst in 2008, this single object was as bright as 10 million galaxies for nearly 1 minute. The observations followed up on the mystery and concluded that the shots came from supernovae, explosions of massive stars that can produce a black hole or neutron star. Nevertheless, not all supernovae had gamma-ray bursts. What was the actual cause? Observations by Hubble have revealed that many gamma-ray eruptions originate in bright star-forming regions with stars with low metal content. Currently, scientists know there are at least 2 kinds of gamma-ray bursts. There may be a difference between the process of creating a supernova from a star that has lots of metal and one with little. Stars with low metal content are thought to produce black holes when they die, while stars with high metal content form neutron stars instead. Gamma-ray bursts are often black hole birth announcements if that's true. Gamma-ray bursts add another piece to the puzzle of supernovae. Because supernovae are one of the few methods astronomers have for measuring vast distances in space, understanding these titanic explosions is key to understanding the universe. Witnessing the explosion in action can help us determine how it happened. A neutron star is surrounded by gas and dust, all that's left after a supernova explosion. The neutron star N49 emitted a tremendous gamma-ray burst a decade before this observation. Tracing the history of the galaxy. Gravitational pull can cause galaxies to collide and merge. Galaxies crashed more frequently in the early universe than today, and astronomers believe that these collisions are necessary for galaxies to grow and evolve. It is thought that our own Milky Way galaxy, along with Andromeda, has increased in size by absorbing smaller nearby galaxies. We can test this hypothesis by studying the ages, arrangements, compositions, and speeds of stars in a galaxy. The simulation shows an entire galaxy collision sequence and compares the different stages of collision to those observed by Hubble in various galaxy pairs. A combination of simulations and high-resolution observations can help us to better understand these titanic crashes. Observations of 300,000 stars, young and old, in Andromeda's halo by Hubble. During Hubble's time, he observed the halo of the Andromeda Galaxy, a region of stars located beyond the central galactic disk. Andromeda is the nearest large galaxy to our Milky Way, and while it has been observed from the ground frequently, Hubble's resolution allows it to be seen at an individual star level. Because halo stars develop early during galaxy formation, astronomers expected Andromeda's stars to be old. However, they found that the stars in the galaxy's outer regions range from around 13 billion to 6 billion years old. Andromeda would have eaten the smaller galaxies, bringing them into the Andromeda halo and making them their own stars. Based on Hubble's observations, all large galaxies have experienced galaxy mergers and interactions throughout history. Scientists have known for years that the Milky Way and Andromeda are headed toward one another, but it is still an open debate whether they will collide, brush against one another, or miss one another. One day, we'll be able to see that for ourselves. Hubble has revealed that the Milky Way and the Andromeda Galaxy are directly colliding. The two mammoth galaxies will collide in 4 billion years, spinning together in a slow, massive dance, eventually combining into a single universe. The sideways motion of the Andromeda Galaxy was observed by astronomers over 5 to 7 years. Using Hubble observations, scientists predict the future of the Milky Way and Andromeda galaxies. Based on computer simulations, the two galaxies are expected to collide in 4 billion years. Earth and its companion planets will not be affected by the collision, as the Sun is flung into a new region of the galaxy. The distance between stars is so great that there is little chance of stars striking each other when galaxies collide. Stars that are dying. A planetary nebula is a unique and beautiful formation formed by gas heated by radiation from a white dwarf. Over about 30,000 years, mid-sized stars like our Sun eject their outer layers of gas into space, leaving behind their hot core, a white dwarf. Astronomers thought that dim shapes they saw through telescopes were related to planets in the early days of astronomy. We can see previously expelled material interacting with newly ejected material in Hubble's observations, showing that planetary nebulae are not formed in one dying breath, but in multiple outbursts. Many of these nebulae have been observed by Hubble today, and Hubble has observed many complicated and extraordinary shapes, ranging from tunnels to interlocking rings. For example, the Cat's Eye Nebula consists of 11 bubbles of gas that appear from our perspective three-dimensional structure of the Helix Nebula visualization. From our perspective, planetary nebulae seem flat, but they're actually quite complex. There is evidence that the Helix Nebula consists of two nearly perpendicular disks. Although we still do not understand the dynamics that create such intricate structures in such a short time, each Hubble image helps us learn a little more about how Sun-like stars spend their final years. Solar-like stars produce carbon, nitrogen, oxygen, and iron, which are indispensable for life as we know it in their cores. By studying their deaths, we can learn how these elements are spread throughout the universe. A star that is 8 to 25 times more massive than our Sun ends its life in another way by exploding in a tremendous explosion called a supernova, which may leave behind a neutron star or a black hole. Supernovas are the titanic explosions that end a star's life. The star's material is flung into interstellar space at millions of miles per hour during a supernova. The elements formed inside a star are scattered across the area in its lifetime to become part of future nebulae, principles, and planetary systems. Their cores collapse and explode when they exhaust fuel, sending their outer layers racing into space. Astronomers last observed a supernova in our galaxy in the 1600s, when Europe was still settling in North America. In the Large Magellanic Cloud, a supernova, one of the Milky Way's satellite galaxies, reached Earth in 1987. Hubble began monitoring the explosion from the first ringside seat ever for a supernova 3 years later when it was launched. Starburst from supernova 1987A, 1994 to 2006. Supernova 1987A has been observed repeatedly by Hubble, which has seen rings and knots of gas brightening around the exploded star. Material unleashed by the stellar explosion illuminates a 6 trillion-mile ring of gas around the dying star. Over 2 decades of watching the supernova progress have given us a better understanding of how these events unfold over thousands of years. A supernova in the making has also been observed by Hubble. A supermassive star more than 100 times the mass of the Sun, or a pair of supermassive stars, is Eta Carinae. It briefly became the second prominent star in our night sky in 1843. Hubble images revealed that the unstable star had released 2 lobes of hot gas before its eventual explosion. Scientists believe Eta Carinae's mass could lead to a hypernova that would outshine the entire galaxy. The elements denser than iron are produced by massive stars, and when they die, the material is ejected into space. Our solar system was once filled with material from supernovae, as evidenced by your gold ring or titanium watchband. Eta Carinae, the doomed star. Eta Carinae, an unstable star, is expected to explode as a supernova someday. A 150-year-old outburst sent lobes of gas racing outward at 1.5 million miles per hour, 2.4 million kilometers per hour. Science of the planets. The Hubble Space Telescope has observed stars and planetary systems in formation, examined the atmospheres of planets around distant stars, and seen the destructive power of cosmic impacts. What happens on the surfaces of our nearest neighbors? Are there other places with populations that wonder at the skies as we do? As we gather more information about planets and discover new ones, our understanding of planet science expands. Having only 9 worlds on our initial list, including Kuiper Belt object Pluto, is an insignificant sample from which to draw conclusions. The discovery of extrasolar planets, planets beyond our solar system, has stunned astronomers with the wide variety of planetary systems. Giant planets orbiting close to their home stars, planets in strange elongated orbits, even a planet that orbits 2 stars at the same time. Seeing planets within our solar system and beyond enables us to learn more about how these bodies came to be and our own planet. The birth of stars and planets. When clouds of gas and dust collapse, gravity pulls the materials together into a dense object surrounded by a spinning disk of leftover matter. It eventually erupts with jets of intense radiation trillions of miles long, traveling at 500,000 miles per hour, 800,000 kilometers per hour. Scientists are uncertain exactly how the jets form, but believe they result from magnetic fields rotating around the forming star. Astronomers could see jets before Hubble, but not star-forming disks. Hubble's vision enabled them to see both. It captured the first detailed images of jets and disks in the Orion Nebula in 1995. In the past decade, Hubble has taken many images of jets and found the first direct evidence that they originate at the center of the dusty gaseous disk from which the forming star is drawing its raw material. During star formation, the jets are thought to slow down the spinning disk so that more matter can accumulate on the star. The Orion Nebula in a panoramic view. The nebula contains 700 young stars in various stages of formation within a cavern of gas and dust. Astronomers once thought it would be impossible to observe protoplanetary disks, the disk of dust around stars that coalesce into solar systems. The disks were engulfed in giant clouds of gas and dust, making them difficult to discern. By identifying the dark clots of dense dust against the bright background of glowing nebulae, Hubble disproved this theory and found numerous protoplanetary disks. According to Hubble's observations, planet formation is influenced by the environment in which a star develops. The Hubble observations have also provided clues about the missing steps in our understanding of planet formation, such as how a disk of gas and dust evolves into individual planets that orbit newborn stars. Planets outside our solar system. Exoplanet HD 189733b's evaporating atmosphere. Many extrasolar planets have been discovered beyond our solar system. Ground-based telescopes have found most of them by looking for tiny wobbles in a star's motion caused by planets tugging at it, or the slight dimming of light caused by a planet passing in front of its parent star. Hubble can provide insights into the planets that cause these light-blocking periods called transits. In addition, Hubble measures the amount of light passing through the atmosphere of the Earth, which allows it to determine the makeup of the atmosphere. Hubble has discovered atmospheres containing sodium, carbon, and oxygen, and a world with a comet-like tail of hydrogen evaporating into space. In addition, the team detected the first organic molecule on an extrasolar planet. Methane in the atmosphere of a Jupiter-sized planet blisteringly close to its star. Space Telescope's ability to make these observations was a breakthrough, confirming and bolstering the idea that they could examine the atmosphere of far-flung planets and set the stage for current and future telescopes to continue this critical science. Moreover, Hubble took the first visible light picture, something astronomers thought was impossible. Observations of Fomalhaut's dusty surroundings had led astronomers to suspect that the star might have planets since the early 1980s. An image of the dust belt around a star shows a tiny speck of Fomalhaut b, a planet approximately 3 times the size of Jupiter that might be surrounded by a disk of dust and gas. Observations of the planet Fomalhaut by Hubble. Scientists used coronagraphs to black out nearby light sources, including the star in the center of the image, to observe the much dimmer planet as it passes near a dust ring surrounding the star. Photographs taken years apart show the planet moving along its expected path. For the first time, Hubble observes a planet orbiting another star. Having suspected for years that planets may exist in other solar systems in the universe, the Hubble Space Telescope captures visible light images that provide the first evidence of these extrasolar planets. Scientists describe the discovery of Fomalhaut b, the first extrasolar planet captured on a camera in visible light. Techniques for finding planets. Planets are microscopic compared to other objects in the universe. Moreover, they can be 1 billion times fainter than the stars they orbit. Astronomers have developed innovative methods to hunt planets in other solar systems since they are nearly impossible to see directly. Transit-based hunting. When a planet passes in front of its parent star, it will cause the star to dim slightly as they block some of the light. Astrophysicists watch for these telltale changes in brightness. Radial velocity hunting. The gravitational pull of a planet causes its star to wobble. Telescopes can detect this wobble by observing the starlight broken into a spectrum of colors. As the star wobbles, dark lines appear caused by light being absorbed by its atmosphere. Astrometry as a method of hunting. A planet's gravity pulls its parent star out of place as it orbits. There is a possibility that a world is pulling on the star if it sways in a periodic rhythm. A telescope with exceptionally sharp vision can sometimes see the star moving back and forth in the sky. Using direct imaging for hunting. Because the stars are so bright and the planets so dim, it's challenging to capture a candid image of an extrasolar world. A mask called a coronagraph can sometimes block enough of the star's light to pick up a planet's dimmer reflected light. Microlensing by gravitational force. Whenever one celestial object passes in front of another, its gravity can bend and magnify the light behind it, making it appear brighter. The closer star will brighten twice if it has a planet. Comet crashes into the solar system. Comet Shoemaker-Levy 9 plunged into Jupiter's atmosphere in 1994, sending large plumes of debris into space. A spectacular view of the event was provided by Hubble, who watched the comet approach the collision site. As Jupiter's gravity shattered the comet into dozens of fragments, it observed violent waves erupting from the impact sites. Scientists believed it was a once-in-a-thousand-years event. Astronauts visited Hubble in May 2009 to install new instruments. In July, an amateur astronomer discovered a strange dark spot on Jupiter's surface as engineers and scientists tested and adjusted the refurbished telescope. As a result of an unnoticed asteroid impact, an expanding impact site has been left behind. Once again, the big world has been hit. 1994. First strike. The first comet, P. Shoemaker-Levy 9, which fragmented upon impact with Jupiter, produced a plume near Jupiter's limb. It was an important event that couldn't be missed. Hubble's team temporarily rearranged its schedule to take pictures of the impact site with one of its new instruments. Impacts of comets in visible and ultraviolet light. An asteroid struck Jupiter in July 2009, leaving a bruise the size of the Pacific Ocean. The Hubble Space Telescope observes different forms of light, allowing us to see more detail than we might otherwise. After a recent servicing mission, engineers interrupted the telescope's calibration to take a picture of the impact. As seen in visible light, Jupiter shows impact sites in its southern hemisphere. The same places on the planet are visible in an ultraviolet picture taken 20 minutes later. This image shows the comet's residue and materials thrown from Jupiter's lower atmosphere into its upper atmosphere by the impact, since the fine particles are easier to see in ultraviolet light. The images were taken on July 17, 1994. Images of Jupiter's impact sites raise questions about the planet's composition. The properties of the waves racing outward from Shoemaker-Levy 9 sites, for example, indicate that the planet's design is less similar to the Sun than researchers previously thought. Hubble's advantage is its ability to take high-quality images of such events on short notice, enabling us to deeply study our cosmic neighborhood. Given the short interval between results, one may wonder if these impacts are as rare as once assumed. Perhaps the timing of these incidents is coincidental, or perhaps collisions occur more frequently than we thought. Scientists once thought they had implications in our solar system that occurred thousands of years apart. NASA's Space Telescope. Since the dawn of astronomy, astronomers have shared one goal: to see more, see farther, see deeper. Humanity made one of its most significant advances in that journey thanks to the launch of the Hubble Space Telescope in 1990. The Hubble Space Telescope is one of NASA's most successful and long-lasting science missions. It is located above the atmosphere. It views the universe typically much better than ground-based telescopes. It has relayed hundreds of thousands of images back to Earth, shedding light on many of the great mysteries of astronomy. Named after a legend. Dr. Edwin Powell Hubble, an astronomer who made some of the most important discoveries in modern astronomy, is the name of the Hubble Space Telescope. Working with the most advanced technology at the Mount Wilson Observatory, Hubble showed in the 1920s that some of the numerous distant faint clouds of light in the universe were entire galaxies, much like the Milky Way. It changed the way astronomers viewed our place in the universe forever when they realized that the Milky Way was only one of many galaxies. Hubble's most important discovery came when, in 1929, he discovered that galaxies appear to move away from Earth faster the farther from Earth they are. The Big Bang theory posits that the universe began with a burst of energy at a single point and has been expanding ever since. Hubble Space Telescope cross-section. Hubble travels at about 5 miles per second, 8 kilometers per second, fast enough to cross the country in about 10 minutes during its orbit around Earth. Hubble's mirror captures light as it travels and directs it into its science instruments as it does so. A Cassegrain reflector telescope, such as Hubble, is a type of telescope. The main mirror or primary mirror reflects light. After being reflected by the primary mirror, the light is reflected by a secondary mirror. Using the secondary mirror, light is focused through a hole in the primary mirror, which is connected to the telescope's science instruments. It is a common misconception that the power of a telescope lies in its ability to magnify objects. A telescope works by collecting more light at a higher resolution than the human eye can see. The larger a telescope's mirror, the more light it can hold, and its vision is better. Hubble's primary mirror measures 94.5 inches, 2.4 meters. It is smaller than current ground-based telescopes, measuring 400 inches, 1,050 centimeters, but Hubble's location beyond the atmosphere gives it remarkable clarity. Following the light's capture by the mirror, Hubble's science instruments work together or individually to provide the observations. These instruments probe the universe in different ways. Hubble's functions are all powered by sunlight. Solar panels on Hubble convert sunlight directly into electricity. When the telescope is blocked from the sun's rays, some electricity is stored in batteries in Earth's shadow. Design of the Hubble Space Telescope. Wide Field Camera 3, WFC3, detects near-ultraviolet, visible and near-infrared light, but not all at once. It is now Hubble's leading and most efficient camera. COS is a spectrograph that sees exclusively in ultraviolet light. Like prisms, spectrographs separate light from the cosmos into their component colors. A wavelength fingerprint provides information about an object's temperature, chemical composition, density, and motion. Advanced Camera for Surveys, ACS, sees the light in wavelengths from the far ultraviolet to near-infrared and is designed to study some of the earliest activity in the universe. ACS identifies the most distant objects in the universe, searches for massive planets, and examines the evolution of galaxies clusters. NICMOS is Hubble's near-infrared camera and multi-object spectrometer. The Space Telescope Imaging Spectrograph, STIS, is a spectrograph that sees ultraviolet, visible and near-infrared light and is known for its ability to spot black holes. COS can map out small objects like stars and quasars, but STIS can map out larger objects like galaxies. Working with Hubble's instruments. Hubble's primary camera, WFC3, imaged NGC 6302 in ultraviolet and visible light with various filters to determine the properties of the nebular gas. It can observe objects hidden by interstellar dust, such as stellar birth sites, and peer into the deepest reaches of space using light which humans perceive as heat. Known as Fine Guidance Sensors, FGS, these sensors keep Hubble pointed in the right direction by locking onto guide stars. They can be used to measure stars' positions and motions precisely. Large Space Telescope Concept Art. In 1923, German scientist Hermann Oberth, one of the founders of rocketry, proposed blasting a telescope into space aboard a rocket. Lyman Spitzer Jr., an American astrophysicist, proposed a space observatory in 1946. During the next 50 years, he would devote himself to making this space telescope a reality. In 1969, NASA approved what was then called the Large Space Telescope Project. The original proposal was downsized to stay within budget, reducing the size of the telescope's mirror and the number of instruments it would carry. The team working on the project proposed a telescope with several interchangeable instruments. The telescope would either be returned to Earth for repairs and replacement instruments or serviced in space in orbit. Legends are made of this. Several decades before the Hubble telescope became a reality, legendary scientists considered the possibility of a space observatory. The European Space Agency, ESA, and NASA began working on a plan that eventually became the Hubble Space Telescope in 1975. To supply NASA with manpower and funding, ESA's support was crucial. NASA would provide the solar cells and one of the telescope's instruments, the Faint Object Camera. Congress approved funding for the telescope in 1977, after being reassured by the partnership. NASA centers and companies like Lockheed Missiles and Perkin-Elmer Corporation began working on the Hubble telescope piece by piece. The astronauts trained in a weightlessness tank in 1979 using a mock-up telescope to simulate Hubble Space Telescope construction. Lockheed Missiles and Space Company, Lockheed Martin, diagram of the Hubble Space Telescope. Hubble was scheduled to launch in October 1986. Tragically, the launch was delayed until January the 28th. Just over a minute after liftoff, the Space Shuttle Challenger exploded. Shuttle flights were suspended for 2 years. The telescope parts were stored. During the delay, Hubble workers continued improving solar batteries and upgrading other systems. Hubble was launched into orbit on April the 24th, 1990, aboard Space Shuttle Discovery. 5 instruments were carried by the telescope: the Wide-Field Planetary Camera, the Goddard High-Resolution Spectrograph, the Faint Object Camera, the Faint Object Spectrograph, and the High-Speed Photometer. Designed to be repaired and upgraded by astronauts in orbit, it would be needed sooner than later. Starting off on the wrong foot. It was clear almost immediately that something was wrong after Hubble entered orbit. The pictures were more explicit than those of ground-based telescopes, but they were not the new images promised. The photos were blurry. In Hubble's primary mirror, polished so carefully over an entire year, there was a flaw called spherical aberrations. The mirror was just slightly the wrong shape, which caused the light that bounced off the center of the mirror to focus differently from the light reflecting off the edge. This flaw, about 1/50th the thickness of a sheet of paper, was enough to distort the view. Hubble was the first instrument to come with built-in corrective optics. Scientists and engineers were faced with a well-known problem. Astronomers had been dealing with spherical aberrations since Galileo's time, but Hubble's mirrors could not be altered or replaced while in orbit. Fortunately, a solution was found. Mirrors could be used to intercept the light that reflects off the mirror, correct for the flaw, and bounce it to the telescope's science instruments. COSTAR, or Corrective Optics Space Telescope Axial Replacement, could be installed in place of one of the telescope's other instruments to correct their images. In addition to replacing the Wide-Field Planetary Camera, astronauts will install the Wide-Field and Planetary Camera 2, WFPC-2, containing small mirrors to correct aberrations. As scientists and engineers worked, Hubble sent back images that, despite their flaws, still gave astronomers a better look than they'd previously had at the kind of cosmic phenomena Hubble was intended to reveal. scientists developed new image processing techniques that partially recovered some of the information lost due to blurring. A planet-spanning storm churned on Saturn. The number of stars in Galaxy M87 revealed the scale of the supermassive black hole at its center. The lobes of gas emitted by the unstable, explosive supermassive star Eta Carinae were observed. The science Hubble accomplished with the problematic optics hinted at what could be accomplished with a fixed mirror. One of the most complex space missions was trained for 11 months by astronauts and NASA staff. Over 100 specially designed tools would be used in the repair process. It would be the first test of the telescope's vaunted capability of being serviced and repaired in space and its critical nature. The Space Shuttle Endeavour launched 7 crew members into orbit on December 2, 1993, for a mission that involved 5 days of spacewalks and repairs. The high-speed photometer was replaced with COSTAR. The Wide-Field Planetary Camera 2 replaced the original Wide-Field Planetary Camera. They also replaced solar panels, fuse plugs, and other hardware. They were finished on December 9th. Training for the first servicing mission. The Neutral Buoyancy Simulator simulates weightlessness by filling a vast water-filled tank with water. A view of the Indian Ocean shows the Space Shuttle Endeavour approaching the Hubble Space Telescope. NASA released the first images taken by Hubble's fixed optics on January 13, 1994. The photos were gorgeous, the resolution was excellent. Hubble finally became the telescope that had been promised. Pillars in the Eagle Nebula, M16A, one of Hubble's most famous images. Hubble's 1993 servicing mission was the first of many successful attempts to upgrade the telescope. Hubble received 2 gifts from the Space Shuttle in 1997, 2 instruments that featured technology not available when scientists designed and built the original equipment. New appliances gave Hubble a broader view of the cosmos, a pattern that repeated itself in the years that followed as astronauts brought Hubble improved technology. Astronauts would visit Hubble in 1997, 1999, 2002, and 2009. 3 of Hubble's 6 gyroscopes had failed, and Hubble needed at least 3 to observe a target. In November 1999, a 4th gyroscope failed, forcing Hubble into safe mode. Hubble was protected but could not keep its targets. In December 1999, Servicing Mission 3A was launched, followed 3 years later by Servicing Mission 3B. In 7 months, we developed, approved, and executed an urgent call-up mission. In Servicing Mission 3A, astronauts replaced all 6 gyroscopes and installed more powerful electronics, batteries, and new insulation. Hubble's Advanced Camera for Surveys, ACS, and a new power control unit was installed for Servicing Mission 3B. It was a delicate mission. Hubble had to be turned off for the first time since its launch to replace the power unit. The mission went well, and ACS, with its wide field of view, superb image quality, and exquisite sensitivity, brought 10 times more discovery power than the camera it replaced. An astronaut visit to Hubble in May 2009 was the culmination of a long effort to provide one more servicing mission to the telescope. The mission was initially scheduled for 2004. The view from Hubble improves over time. A Hubble image of a small region of the Orion Nebula reveals how the telescope's vision has improved over time. Hubble's 4th servicing mission was perhaps its most challenging and intense. As a result of the loss of the Space Shuttle Columbia, the mission was postponed until May. NASA approved a second shuttle mission after restarting the shuttle program and re-examining the risks. 2 weeks before the launch of the task in late September 2008, a malfunction occurred in a system that controls science instruments and directs data flow within the telescope. The problem was resolved by switching to a backup plan, but NASA was unwilling to leave the telescope without a spare. ACS and the Space Telescope Imaging Spectrograph, STIS, had already stopped working because of electrical malfunctions in 2007 and 2004. As part of servicing Mission 4, astronauts installed a replacement data unit and performed on-site repairs for 2 failed instruments that had never been imagined by telescope creators. During spacewalks, astronauts had to crack into the interior of the instruments, replace components, and reroute power. In addition to Hubble's nail-biting repairs, 2 new advanced instruments, the Wide Field Camera 3 (WFC3) and the Cosmic Origin Spectrograph (COS), gave Hubble 5 tools for future observations. Hubble's latest workhorse instrument, WFC3, is susceptible and efficient, and it is capable of taking ultraviolet, optical, and infrared pictures. The COS spectrograph examines nearby stars, distant galaxies, and gas and dust. Space Shuttle Atlantis and the STS-125 crew launched on the final mission to upgrade Hubble on May 11, 2009. At first, NASA hoped Hubble could be brought back to Earth by the end of the task. Since SM-4 is likely to be the last astronaut mission to Hubble, astronauts installed a new device, the soft capture mechanism. In the future, when Hubble reaches the end of its life, a robotic spacecraft could attach itself to this device and guide it through its descent into Earth's atmosphere. Hubble will eventually cease to exist. Over the years, Hubble's components will gradually degrade to the point that the telescope stops functioning. When that happens, Hubble will continue orbiting Earth until its orbit decays, allowing it to spiral toward Earth. Getting ready for the future. While the shuttle released Hubble back into space in 2009, an imaging system called the Relative Navigation System, RNS, acquired images and video of the telescope's aft bulkhead. The artist's depiction shows one of the RNS cameras collecting data. Having this information will allow NASA to explore many options for a safe deorbit of Hubble. The replacement vehicle is unlikely to be able to return Hubble to Earth because it was explicitly designed to function with the space shuttle. Robotics will be used to help deorbit Hubble, guiding its remains through the atmosphere and into the ocean. Hubble's legacy, discoveries, trailblazing design, and success in showing us the universe in unprecedented detail will live on. Researchers will rely on Hubble's discoveries for years as they continue to understand the cosmos, a pursuit that has gained clarity, focus, and triumphs through Hubble's wealthy existence. Astronomical exploration of the universe will not end with Hubble's eventual demise. The James Webb Space Telescope, the successor to Hubble, will be the next giant observatory in space. The Webb Telescope, which will see infrared light, and the Hubble Telescope, visible light, will be tennis court-sized telescopes orbiting far beyond Earth's moon. The James Webb Space Telescope, beyond Hubble. In addition to the Hubble Space Telescope, the James Webb Space Telescope is NASA's next orbiting observatory. Webb will navigate through a frigid void nearly 1 million miles from Earth and peer back to when the universe was first illuminated by stars and galaxies. A stellar jet in Carina, visible versus infrared. Observations taken by Hubble in visible and infrared light reveal dramatically different and complementary views of an object. As Webb scans the cosmos, he will be looking for invisible radiation called infrared. Our ability to see infrared light is crucial to understanding the universe. The furthest objects we can detect are seen in infrared light. More spectacular objects that would otherwise be invisible emit infrared light, and infrared light passes through clouds of dust to allow us to see their depths. As Hubble sees visible light, Webb will see infrared clearly and precisely. Our view of a telescope is quite different from Webb's. This spacecraft has no tubes, only a tennis court-sized sunshield that blocks light from reaching its cold side, which houses its mirrors and science instruments, A box would interfere with faint infrared radiation going Webb's mirror and devices by trapping heat. The Webb telescope's 2-story high primary mirror is made of 18 segments of beryllium, which can withstand the extreme cold it will have to endure, -233.3 degrees Celsius. Webb will be the world's largest telescope. The primary mirror of the Webb telescope is too large to be monolithic, like Hubble's 94.5-inch, 2.4-meter mirror. Thus, its mirror is divided into 18 precisely ground and polished hexagonal segments. The giant telescope will have to be folded up inside the rocket that carries it into space. The mirror will unfold as it approaches its destination, and the sunshield will spread like wings. The vision of Webb will be able to detect features. Through Webb, infrared light will be visible because it will be stretched as it travels across space, a phenomenon known as redshifting. This will enable scientists to see the light from the first galaxies formed in the early universe. Infrared views from Webb will enable us to see through opaque clouds of gas and dust in our own galaxy to objects like newborn stars and dusty disks forming new solar systems, allowing us to better understand how stars and planets evolve. Webb's instruments will allow us to detect traces of water vapor from planets around other stars, possibly indicating the presence of life-giving oceans. Targets for Webb science. With Webb now in operation, and despite the high expectations for the telescope, the real excitement will come from Webb's discoveries. This simulated image shows what deep-field photos will look like with Webb. Far-reaching galaxies reveal new galactic populations. Astronomers will have an unprecedented tool to explore the cosmos once Webb takes its place among the stars. The science it reveals may, as with Hubble, lead to questions astronomers haven't considered yet. Webb's true strength may lie in its potential for unbounded, unexpected discovery. A cluster of stars, NGC 2074, in the Large Magellanic Cloud. Hubble observed a small nebula region near the star cluster NGC 2074, upper left. It is a firestorm of raw stellar creation, possibly caused by a nearby supernova explosion. The galaxy is about 170,000 light-years away near the Tarantula Nebula, one of the most active star formation regions in our local group. In the 3D image, we see dramatic ridges and valleys of dust, serpent-headed pillars of creation, and filaments of gas glowing under torrential ultraviolet radiation. It lies on the edge of a dark molecular cloud that is an incubator for new stars. Clusters of hot young stars born in NGC 2074 are eroding the nebula's wall with high-energy radiation. Another young collection may be hidden under a circle of brilliant blue gas at the bottom center. Another young cluster may be hidden. Retina Nebula, a seemingly square nebula, dying star IC 4406. Is it possible to make a square nebula form a round star? The conundrum is revealed when studying planetary nebula like IC 4406. IC 4406 is likely a hollow cylinder whose square appearance results from our vantage view. IC 4406 probably looks like the Ring Nebula when viewed from the top. Combining images taken by the Hubble Space Telescope in 2001 and 2002, this color composite picture represents the Hubble Space Telescope in representative color form. The cylinder's ends are filled with hot gas, while dark dust and molecular gas line its walls. Within the planetary nebula's center is the star that created this interstellar sculpture. IC 4406 will be nothing more than a fading white dwarf star in a few million years. NGC 3603, Star Cluster. Stellar Jewel Box is one of the most massive young star clusters in the Milky Way galaxy. Within the giant nebula NGC 3603, there are thousands of sparkling young stars. About 20,000 light-years away, NGC 3603 is a prominent star-forming region in the Carina spiral arm of the Milky Way. In this image, a young star cluster is surrounded by a vast area of dust and gas. It shows the stages of star formation. Sir John Herschel discovered the nebula in 1834. It spans roughly 17 light-years. Composite image of SNR 0509-67.5 taken with optical and X-ray imaging. A combination of data from 2 of NASA's great observatories was used to make this image of supernova remnant 0509-67.5. Hubble Space Telescope images of SNR 0509-67.5 and its surrounding star field are combined with Chandra X-ray Observatory images. We see a soft green and blue hue of heated material surrounding the glowing pink optical shell based on the X-ray data. This is a result of ambient gas being shocked by the expanding blast wave from the supernova. Bright areas of the X-ray data correspond to ripples in the shell. Eagle Nebula gas pillars, Messier 16. M16, or the Eagle Nebula, contains these towering tendrils of cosmic dust and gas. In this stunning Hubble image, the pillars of creation are part of an active star-forming region in the nebula and hide newborn stars within their wispy columns. It is not Hubble's first image of this iconic feature of the Eagle Nebula. However, it is the most detailed. Located just outside the frame, a cluster of young stars emits scorching ultraviolet light that bathes the pillars in light. Blue represents oxygen, red represents sulfur, and the green represents both nitrogen and hydrogen in the image. Winds from these stars are slowly eroding the towers of gas and dust. As a fascinating but relatively minor feature of the Eagle Nebula, which spans 70 by 55 light-years, the pillars of creation span approximately 4 to 5 light-years in length. The nebula was discovered in 1745 by Swiss astronomer Jean-Philippe Loy-de-Chaussure, located 7,000 light-years from Earth in the constellation Serpens. The Eagle Nebula can be seen through a small telescope and is best viewed in July when its apparent magnitude is 6. A large telescope and ideal viewing conditions are required to resolve the pillars of creation. The star-forming region S106. IRS-4, a massive star, is beginning to spread its wings. About 100,000 years ago, material streaming from this newborn star formed the nebula dubbed Sharpless II 106 Nebula, S106, shown here. This nebula has an hourglass or butterfly shape due to dust and gas orbiting infrared source 4, IRS-4, visible in brown near the image center. Gas near IRS-4 emits light after ionization, while dust far from IRS-4 reflects light from the central star and functions as a reflection nebula. An infrared image of S106 reveals hundreds of low-mass brown dwarf stars buried in the nebula's gas. About 2,000 light-years away, S106 lies in the constellation of the Swan, Cygnus. The remnant of the supernova SN1006. Ancient supernova explosion creates a ribbon of light. A new star appeared suddenly in the sky in 1006 AD, witnessed and recorded by observers from Africa to Europe to the Far East. For several weeks, people could see the star without any aid during the day, and it remained visible for about 212 years before it faded away. This was probably the brightest star ever observed by humans. Scientists now know the object's true identity. SN1006 was a supernova that occurred about 7,000 light-years from Earth in the constellation Lupus. Over 1,000 years, the stellar explosion sent a blast wave racing through space at nearly 20 million miles per hour. Gas and dust in its path are being swept up and heated by the blast wave. There is a nebulous bubble about 60 light-years across surrounding the explosion site of this supernova. The star-forming region 30 Doradus. At 160,000 light-years away, the Tarantula Nebula 30 Doradus is a bright and active star-forming region outside the Milky Way galaxy. 30 Dor contains the central cluster NGC 2070, the most dynamic region R136, which appears in the central right part of the image. This galaxy is a few million years old and contains thousands of young stars, including several of the largest. Bright blue stars are visible in the cavity excavated by stellar winds. Some redder stars are still embedded in the cloud material, seen in shadow except where illuminated by cavity stars. The embedded stars are more clearly visible in the infrared Hubble view due to the intervening cloud material. There is a nearby galaxy called NGC 602. Young stars in the small Magellanic Cloud are spewing radiation, eating away at the gas and dust cloud that gave birth to them. That scene can be seen in this Hubble image taken with the advanced camera for surveys. NGC 602 is a cluster of blue stars that developed when a large part of the gas cloud collapsed under gravity and became very dense. These hot young stars are currently producing fierce radiation, sculpting the inner rim of the gaseous nebula. The nebula's parts resist erosion better than others, leaving tall pillars that point toward the stars, the radiation source. It's relatively close to us, less than 200,000 light-years away, so it gives astronomers a chance to study star formation in a different galaxy. Additionally, it's a dwarf galaxy with fewer stars and lacks the enriched gas that more giant galaxies like ours possess. Therefore, it may provide a glimpse into what star formation might have been like in the early universe, NGC 6357 and Pismis 24. What is the maximum mass of an average star? Based on distance, brightness, and standard solar models, one star in the open cluster Pismis 24 was estimated to have more than 200 times the mass of our Sun, making it one of the most massive stars ever discovered. This star is the brightest object above the gas front in the featured image. However, the Hubble Space Telescope has revealed that Pismis 24-1's brilliant luminosity is not derived from a single star but from at least 3 stars. Component stars would still be among the most massive stars on record, with masses close to 100 solar masses. Stars are still forming in the emission nebula NGC 6357 at the bottom of the image. A spectacular cocoon of stars appears to be breaking out of what seems to be a Gothic cathedral. A Trifid Nebula. Charles Messier discovered the M20 in 1764. It is a star-forming nebula located 9,000 light-years from Earth in the constellation Sagittarius. M20, also known as the Trifid Nebula, has an apparent magnitude of 6.3 and can be seen with a small telescope. This is the best time to observe it. Hubble's image shows the center of the Trifid Nebula with its 3 wing-like bands of thick dust. Near the nebula center, we can see a group of recently formed massive bright stars. UV radiation from these stars dramatically influences the structure and evolution of the surrounding nebula. Star formation does not occur near these bright stars anymore because radiation has blown away the gas and dust from which new stars can form. As a result of the camera's design used to take the exposures, the image has a stair-step appearance. One of the 4 light detectors provided a higher resolution, but it had a smaller field of view than the other three. Black regions were left when the images from all 4 detectors were combined because the detector with the higher resolution did not cover as much area as the others. Small Magellanic Cloud infant stars. For the first time, Hubble astronomers have identified a population of infant stars in the Milky Way satellite galaxy, the Small Magellanic Cloud, SMC, located 210,000 light-years away. Hydrogen fuel has not yet been ignited to sustain nuclear fusion. Its exquisite sharpness revealed a population of infant stars embedded in the nebula NGC 346 that are still forming from gravitationally collapsing gas clouds. The smallest of these infant stars is only half the mass of the Sun. Though starbirth is common in our galaxy's disk, this smaller companion galaxy is more primitive, as it lacks much of the heavier elements forged in successive generations of stars through nuclear fusion. As primitive building blocks of more giant galaxies, fragmentary galaxies like the SMC are considered primitive. When the universe was much younger, these galaxies were most common. The SMC offers a unique opportunity to study how stars formed in the early universe. The nebula NGC 346, nestled among other starburst regions within the small galaxy, contains more than 2,500 infant stars. Galaxy cluster Abell 520 merging. The image below depicts the distribution of dark matter, galaxies, and hot gas inside the core of the merging galaxy cluster Abell 520, formed through violent collisions of massive galaxy clusters. NASA's Hubble Space Telescope and the Canada-France-Hawaii Telescope took the natural color images of the galaxies. False-colored maps are superimposed on the image, showing the cluster's concentration of starlight, hot gas, and dark matter. From observations by the Canada-France-Hawaii Telescope, starlight from galaxies is colored orange. NASA's Chandra X-ray Observatory detected the green regions which show hot gas. This indicates that a collision has occurred. The blue areas indicate the bulk of the mass in the cluster, dominated by dark matter. Most of the universe's mass comprises dark matter, an invisible substance. The dark matter map was constructed using Hubble Wide Field Planetary Camera 2 observations that detected how light from distant objects is distorted by the cluster of galaxies, an effect called gravitational lensing. There is a clump of dark matter near most of the hot gas in the center of the image, where few galaxies are found. The findings confirm previous observations of dark matter in the cluster. Fundamental theories of dark matter predict that galaxies should be anchored to dark matter, even during shocks of collisions. Hubble 1689, Hubble ACS-WFC. Hubble's latest image shows galaxy cluster Abell 1689. Hubble's Advanced Camera for Surveys, ACS, collected both visible and infrared data over a combined exposure time of over 34 hours, left image over 13 hours, right image over 20 hours, to show this patch of sky in greater and more striking detail than before. Golden clumps, bright stars, and ethereal spiral galaxies pepper this image. There are also several electric blue streaks circling and arcing around the fuzzy galaxies in the center. Material from some of these galaxies is being stripped away, giving the impression that they are bleeding into the surrounding space. Gravitational lensing is responsible for these streaks. Due to its massive size, Abell 1689 bends and warps the space around it, which affects the way light travels from objects behind the cluster. The streaks are the distorted forms of galaxies that lie behind the collection. NASA's great observatories study the galactic center. As part of the International Year of Astronomy 2009, NASA's great observatories, Hubble Space Telescope, Spitzer Space Telescope, and Chandra X-ray Observatory, have provided an unprecedented image of the central region of our Milky Way galaxy. In this spectacular image, infrared and X-ray light observations reveal the intense activity near the galactic core obscuring dust clouds. The image width covers about 1/2 of a degree, like the full moon's angular width. The galaxy's center is located just to the right of and below the middle of the image within the bright white region. Each telescope's contribution is displayed in a different color. Hubble's near-infrared observations are represented in yellow. In addition to revealing hundreds of thousands of stars, these observations highlight the regions where stars are being born. Spitzer's infrared observations are represented in red. From the radiation and winds of stars, glowing dust clouds are formed with complex structures, from compact spherical globules to long, stringy filaments. Gas is heated to millions of degrees by stellar explosions, and the supermassive black hole at the galaxy's center emits X-rays. Chandra's X-ray observations are represented by blue and violet. On the left side is a bright blue blob, a neutron star or black hole emitting radiation. The composite image provides one of the most detailed views of our galaxy's mysterious core. Fornax Galaxy Field. Fornax, the furnace, is visible in the southern hemisphere sky on December evenings. Located in a bend of Eridanus, the river, Fornax is one of 14 constellations named by Nicolas Louis de Lacaille in the mid-17th century. It does not hold any exceptionally bright stars. Still, Fornax does save some treasures in its darker depths. At least 6 exoplanet systems. The Fornax Dwarf Galaxy, a satellite galaxy of our Milky Way. The Fornax Cluster of Galaxies, a cosmic filament showing the most considerable rotation in the universe. The fantastic Hubble Ultra Deep Field Image. Galaxy M87's black hole emits a jet of high-speed electrons. Astronomers have detected particles being accelerated at speeds faster than 99% of the speed of light by the famous giant black hole in Messier 87 using NASA's Chandra X-ray Observatory. With observations of the massive dark object at the center of Galaxy Messier 87, or M87, the Event Horizon Telescope collaboration released the first image of a black hole in April last year. About 55 million light-years from Earth, this black hole has a mass of about 6.5 billion times that of the Sun. Astronomers have named the black hole M87, and it has recently been given the Hawaiian name Puwehi. Astronomers have observed radiation from a jet of high-energy particles blasting out of the center of M87 for years. Researchers have studied the jet in radio, optical, and X-ray light, including with Chandra. Chandra's observations have shown that sections of the jet are moving at nearly the speed of light. This is the first time such extreme speeds by a black hole's jet have been measured using X-ray data, said Ralph Kraft of the Center of Astrophysics, Harvard and Smithsonian in Cambridge, Massachusetts, who presented the study at the American Astronomical Society meeting in Honolulu, Hawaii. We needed Chandra's sharp X-ray vision to make these measurements. A cluster of lensing galaxies, Arbel 383. There is so much dark matter mass in the giant cluster in the center of the image that its gravity bends the light of more distant objects. For very distant galaxies in the background, the cluster's gravitational field acts as a magnifying glass, turning and focusing the light towards Hubble. Astronomers can use gravitational lenses to extend Hubble's vision beyond what it would typically be capable of seeing. Additionally, the lensing effect can determine the distribution of matter, both ordinary and dark matter, within the cluster. Astronomers can study some of the very first galaxies in the universe in this way. Galaxy cluster CL0024 plus 17, ZW CL0024 plus 1652, dark matter ring. The blue map of the cluster's dark matter distribution shows a ring-like structure. It is superimposed on a Hubble image of the cluster. The ring is one of the strongest indications that dark matter, an unknown substance that permeates the universe, exists. Based on Hubble observations, this map shows how the cluster ZWCL0024 plus 1652 distorts the light of more distant galaxies, an optical phenomenon called gravitational lensing. The universe's material is primarily made up of dark matter, which is believed to be its underlying structure. Even though astronomers cannot see dark matter, they can infer its existence by mapping the distorted shapes of background galaxies. Based on this mapping, we can determine the distribution of dark matter in a cluster. According to astronomers, two gigantic groups collided, forming the observed dark matter ring. Abell 2744, Pandora's cluster. At least 4 smaller clusters have piled up simultaneously to form Abell 2744, nicknamed Pandora's cluster. The collision occurred over 350 million years. Approximately 5% of the cluster's mass is occupied by galaxies. Around 20% of the gas is so hot it shines only in X-rays, red in the image. The cluster's invisible dark matter, which accounts for around 75% of its mass, is blue. The gravitational attraction of dark matter makes it apparent, as it does not emit, absorb, or reflect light. Using gravitational lensing, the team pinpointed the location of this elusive substance. The gravitational field created by the cluster bends light rays from distant galaxies. Images of galaxies in the background of Hubble and VLT observations show a series of telltale distortions. It is possible to map dark matter accurately by carefully analyzing how the images are distorted. Hubble WFC-3, Infrared Ultra-Deep Field. From 2003 to 2009, astronomers captured the Hubble Ultra-Deep Field (HUDF) images in visible and near-infrared light. Fornax is a constellation in the southern hemisphere seen in the HUDF. Astronomers have combined Hubble's colors using ultraviolet light to near-infrared. As a result of 841 orbits of telescope viewing, the resulting image contains approximately 10,000 galaxies extending back hundreds of millions of years to the time of the Big Bang. Moons of Saturn. The Hubble Space Telescope captured a picture of 4 Saturnian moons passing in front of their parent planet on February 24, 2009. Saturn's north polar hood is cast in a large shadow by the giant orange moon Titan. Near the ring plane and to the left of Titan is the moon Mimas, which casts a much smaller shadow on Saturn's equatorial cloud tops. The bright moon Dione and the fainter moon Enceladus are a little farther to the left, and off Saturn's disk is the bright moon Dione and the fainter moon Enceladus. As seen from Earth, these rare moon transits occur when Saturn's ring plane is near edge-on. Saturn's rings will line up precisely with our line of sight on August 10, 2009 and September 4, 2009. At that time, Saturn will be too close to the Sun to be seen from Earth. Ring plane crossings occur every 14 to 15 years. Hubble observed the ring plane crossing in 95-96 and several moon transits and helped discover several new moons of Saturn. The color of Neptune with satellites. Neptune is the 8th and most distant planet in our solar system, dark, cold, and whipped by supersonic winds. The only planet in our solar system not visible to the naked eye, Neptune is more than 30 times as distant from the Sun as Earth, and the first predicted by mathematics before its discovery. Since its discovery in 1846, Neptune finished its first 165-year orbit in 2011. View of Mars from Hubble, 8/2703. Within minutes of Mars's closest approach to Earth in nearly 60,000 years, NASA's Hubble Space Telescope captured this image of the planet. A series of exposures were taken between 5:35 a.m. and 6:20 a.m. on August the 27th, using Hubble's Wide Field and Planetary Camera 2. The red planet is 34,647,420 miles away, 55,757,930 kilometers from Earth. This sharp natural color image has several prominent Martian features, including the largest volcano in the solar system, Olympus Mons, extensive canyons called Valles Marineris, an immense dark marking called Solis Lacus, and the southern polar ice cap. Located just above the center, Olympus Mons is an oval-shaped feature 3 times higher than Mount Everest. The dormant volcano is located in the Tharsis Bulge region, about as big as the US, and home to several extinct volcanoes. Just beneath Olympus Mons are the 3 volcanoes of Tharsis Montes. At the southernmost volcano, Arsia Mons, there are faint clouds. The moons of Pluto. On one of Pluto's moons, it might be difficult to tell when or from which direction the Sun rises each day. A detailed analysis of Hubble data shows that Pluto's moons Nix and Hydra wobble unpredictably. Moons wobble because they are embedded in a gravitational field that shifts constantly. Pluto and Charon are whirling around each other as they create this shift. Pluto and Charon are called twin planets because they share a common center of gravity located in the space between the bodies. It is strengthened by the football-like rather than the moon's spherical shape. The smaller moons tumble erratically due to their variable gravitational field. Pluto's other 2 moons, Cerberus and Styx, are likely in a similar situation. Ganymede and Jupiter, FPCC2 4907. With its Hubble Space Telescope, NASA captured Jupiter's moon Ganymede playing peekaboo with Jupiter. Ganymede can be seen just before it ducks behind Jupiter in this crisp Hubble image. Ganymede orbits Jupiter every 7 days. Ganymede's orbit is tilted nearly edge-on to Earth, so it can frequently be seen passing in front of and disappearing behind its giant host, only to reappear later. Ganymede is the largest moon in our solar system, composed of rock and ice. It is more significant than Mercury. Compared to Jupiter, the giant planet in our solar system, Ganymede looks like a dirty snowball. Jupiter is so prominent that only part of its southern hemisphere can be seen in this image. Astronomers can see features on Ganymede's surface thanks to Hubble, most notably Tros, the white impact crater and its system of rays, bright streaks of material blasted from the crater. Tros and its ray system are about the width of Arizona. Additionally, the image shows Jupiter's Great Red Spot, the prominent eye-shaped feature at the upper left. The Great Red Spot has been raging for more than 300 years and is the size of 2 Earths. Hubble's sharp image of the planet also reveals the texture of the clouds in the Jovian atmosphere and various storms and vortices. Moons and rings circling Uranus. Uranus's faint rings and some satellites are visible on this broader view. Brightness was enhanced outside Uranus to reveal soft rings and satellites. The brightest part of the outermost ring is on the lowest side, where it is more expansive. The dust and small pebbles create a thin, dark, and almost vertical line across the right side of Uranus, most visible on the natural color image. The bright satellite in the lower right corner is Ariel, which has a white surface. Outside the rings can be seen 5 small satellites with dark characters. They are Desdemona, Belinda, Portia, Cressida, and Puck from top to bottom. Deeper exposures of even fainter satellites were also taken in August 2003 with the advanced camera. Ceres, an asteroid-dwarf planet. Ceres is the largest object in the asteroid belt between Mars and Jupiter, and it is the only dwarf planet in the inner solar system. Giuseppe Piazzi discovered it in 1801 as the first asteroid in the asteroid belt. Ceres was the first dwarf planet to receive a visit from a spacecraft when NASA's Dawn arrived in 2015. Ceres, which has long been called an asteroid, is so much bigger and different from the rocky neighbors that scientists designated it a dwarf planet in 2006. Pluto is still 14 times more massive than Ceres, even though Ceres comprises 25% of the belt's mass. The Venusian cloud tops. On Venus, however, the clouds never part, for the planet is encased in a 20-kilometer thick layer of carbon dioxide and sulfur dioxide. Venus's cloud tops, as seen from 30,000 kilometers by the Venus Express spacecraft on December 8, 2011. Almost all the image shows the planet's southern hemisphere, with the South Pole at the bottom and the equator near the top. The top cloud layer visible in the picture is about 70 kilometers above the planet's surface. Venus's bright and dark markings are caused by variations in an unknown absorbing chemical at its cloud tops. This material is abundant in the low latitudes, upper part of the image, making this region appear dark in UV. Towards the brighter high latitudes, lower part of the image, the UV absorber is either insufficient or masked by a haze of a reflecting aerosol. The shapes of the cloud top features indicate vigorous circulation and dynamics in the planet's atmosphere. Saturn Aurora, January 28, 2004. This picture combined ultraviolet images of Saturn's southern polar region with visible light images of the planet and its rings. Solar particles collide with nitrogen and oxygen in the upper atmosphere to create auroral displays, primarily green and blue in color. Because of the ultraviolet light, the auroral show appears blue. As a result of glowing hydrogen in the atmosphere, the aurora would appear red to an observer on Saturn. Pluto's changing faces. Using multiple Hubble Space Telescope photographs from 2002 to 2003, this is the most detailed image ever created of Pluto's surface. Even though Hubble's view isn't sharp enough to see craters or mountains on the surface, it shows a complex and variegated world with white, dark orange, and charcoal black terrain. A dark, molasses-colored, carbon-rich residue is left behind when ultraviolet radiation from the distant sun breaks up the methane on Pluto's surface. A mysterious bright green spot appears at the center of the disk, 180 degrees, where there is an unusually high concentration of carbon monoxide frost. The New Horizons probe will photograph this region in the highest possible detail when it flew by Pluto in 2015. Global map of Jupiter. Hubble Space Telescope image of Jupiter's atmosphere reveals distinct bands of roiling clouds. This is a stretched-out view of the entire planet. Cloud bands parallel to the equator, currently orange in hue, are confined by jet streams that blow in opposite directions at different latitudes. There are a series of red oval-shaped cyclones embedded in the red swirling band of clouds above the equator. The white oval-shaped wind systems above this cloud band are called anticyclones. Cyclones are low-pressure areas, while anticyclones are high-pressure regions whose winds blow in the opposite direction of winds in cyclones. An oval-shaped string of white anticyclones, seen for decades, appears along with another latitude band in the planet's southern hemisphere. The Great Red Spot is slightly larger than the entire Earth and rotates counterclockwise. This image appears orange rather than red, with a small core of deep orange color in the center. Right to the left, clouds moving toward the giant storm are darker than in recent Hubble observations. There are whiter clouds to the south, moving towards the Great Red Spot from west to east. The Great Red Spot has been shrinking since the 1800s. It is springtime on Neptune. Neptune blooms in springtime. Neptune is the farthest and coldest planet among the significant planets. This might seem like an oxymoron. However, the Hubble Space Telescope has detected an increase in Neptune's brightness in the southern hemisphere. The increase in activity is considered a sign of seasonal change by astronomers. The Hubble Space Telescope observed in August 2002 that Neptune's brightness has increased significantly since 1996. This is due to increasing clouds in the planet's southern hemisphere. Increases in these numbers may result from seasonal changes caused by solar heating changes. In a 164.8-year orbit around the Sun, Neptune experiences seasonal solar heating because its rotation axis is angled 29 degrees to its orbital plane. Due to Neptune's distance from the Sun, the seasonal variation is 900 times smaller than on Earth. Neptune orbits the Sun every 165 years, so the rate of seasonal change is also much slower. Thus, spring will last for several decades in the southern hemisphere. This indicates that Neptune is responding to the weak radiation of the Sun. Hubble's Wide Field and Planetary Camera 2 recorded these images in visible and near-infrared light. Grand Design Spiral Galaxy M81. The American Astronomical Society released the sharpest image of the spiral galaxy M81. It is tilted at an oblique angle on our line of sight, giving us a bird's-eye view of the spiral structure. While the galaxy is similar to our Milky Way, our favorable view provides a better idea of spiral galaxy architecture. The Hubble Space Telescope can resolve individual stars in the galaxy, open star clusters, globular star clusters, and even luminous regions of fluorescent gas, even though it is 11.6 million light-years away. Spiral arms, which wind down to the nucleus, are formed by young, bluish hot stars in the past few million years. Additionally, they host a population of stars formed during a star formation episode about 600 million years ago. Dense green areas of star formation can be seen in the green regions. Clouds of hydrogen gas fluoresce due to the ultraviolet light from hot young stars. Sinuous dust lanes also wind into the nucleus of M81. The Hubble research shows that the mass of a galaxy's bulge is directly proportional to the size of the galaxy's black hole. The galaxy's bulge is much more prominent than the Milky Way. Much older, redder stars are found in the galaxy's central bulge. There is a 70 million solar mass black hole at the center of M81. The black hole is about 15 times bigger than the black hole in the Milky Way galaxy. Due to an encounter with a nearby spiral galaxy, NGC 3077, and a nearby starburst galaxy, M82, about 300 million years ago, M81 may be undergoing a surge of star formation along the spiral arms. Hubble's image will study the galaxy's star formation history and its relation to the neutron stars and black holes seen in X-ray observations made with NASA's Chandra X-ray Observatory, Hoag's Object Galaxy. Observe the Serpent constellation closely slithering through the northern sky, and you might see a galaxy within a galaxy within a galaxy. Astronomer Arthur Hoag discovered this cosmic turkducken in 1950, baffling astronomers. We are talking about a rare ring-shaped galaxy situated 600 million light-years from Earth and measuring 100,000 light-years across, slightly larger than the Milky Way. The oddball object was photographed by the Hubble Space Telescope and processed by geophysicist Benoit Blanco. The Hubble image shows a ring of billions of blue stars surrounding a much smaller and denser sphere of reddish stars. Another ring galaxy peeks out from behind the dark gap between the two stellar circles, much farther away from us. NGC 1275 image from Hubble ACS. Galaxy NGC 1275 shows the delicate thread-like structures in the surrounding gas. There are red filaments in the center of the Perseus galaxy cluster composed of cool gas suspended by a magnetic field and surrounded by 100 million degree hot gas. These filaments are dramatic markers of the feedback process that transfers energy from the massive black hole to the surrounding gas. As radio bubbles rise in the hot interstellar gas, cool gas is transported to the filaments from the galaxy's center. NGC 1275 is located in the center of the Perseus galaxy cluster and is one of the closest giant elliptical galaxies at a distance of 230 million light-years. 3 color filters were used to photograph the galaxy in July and August 2006. ARP 273, a rose of galaxies. The visualization of the interacting galaxy pair known as ARP 273 provides a unique three-dimensional view and serves as a visual reminder that astronomical images show objects that are spread across vast stretches of space. This movie combines the two-dimensional Hubble Space Telescope image with a more comprehensive ground-based image of the region around ARP 273. Through astronomy and computer graphics, a visual representation of a natural scene is created that cannot be experienced in person, but that inspires the imagination. A three-dimensional scene has been created by separating the foreground stars and background galaxies from the combined image. When possible, the shape and geometry of the interacting group are based on scientific knowledge and intuition and, where necessary, artistic license. NGC 1569, the Starburst Galaxy. The core of one of the most active galaxies in our local neighborhood, it is 5,000 light-years across. Millions of newly formed stars illuminate the galaxy called NGC 1569. NGC 1569 produces stars 100 times faster than our own Milky Way galaxy. Over the past 90 million years, this has been almost continuous. 3 giant clusters of stars, each containing more than 1 million stars, are at the core center. 2 clusters are so close together that they appear as one grouping. The clusters are situated within a large central cavity. Many massive young stars have already exploded as supernovae, blowing out the gas in the cavity. The explosions also triggered a violent flow of gases and particles that have formed giant gaseous structures. In the lower right, a sculpted structure is about 3,700 light-years long. These 2 giant bubbles of gas look like drifting islands. The largest bubble is approximately 378 light-years wide, while the smallest is about 119 light-years wide. Radiation from the young, bright stars within them illuminates them. Some of those stars can be seen peeking through their gaseous cocoons. Companion Galaxy M51 and Whirlpool Galaxy M51. M51's graceful winding arms appear like a grand spiral staircase that sweeps through space. The images taken with NASA's Hubble Space Telescope show a spiral galaxy's grand design from its curving spiral arms where young stars live to its yellowish core which houses older stars. Known for its swirling structure, the galaxy is nicknamed the Whirlpool. Whirlpool's most recognizable feature is its 2 curved arms, a hallmark of so-called grand design spiral galaxies. Spiral galaxies have numerous loosely shaped arms that make their spiral structure appear less pronounced. arms play an essential role in spiral galaxies. Compressing hydrogen gas, they create clusters of new stars. On the whirlpool, the assembly line begins at the inner edge with the dark clouds of gas, then moves to the pink regions of star formation, and ends at the brilliant blue clusters of stars along the outer edge. Scientists believe the whirlpool's prominent arms are due to a close encounter with NGC 5195, the yellowish galaxy at one of its outermost tips. The compact galaxy seems to be tugging at the arm at first glance. However, Hubble's clear view reveals that NGC 5195 is passing behind the whirlpool. Millions of years have passed since the small galaxy passed by the whirlpool. NGC 1300, a barred spiral galaxy. Within about 70 million light-years away in the constellation Eridanus lies the barred spiral galaxy NGC 1300. Hubble's composite image of the stunning island universe is the largest Hubble image of a complete galaxy ever taken. Hubble's image of NGC 1300 reveals striking details of NGC 1300's dominant central bar and majestic spiral arms. An examination of the classic barred spiral nucleus itself reveals a spiral structure region about 3,000 light-years across. NGC 1300, like other spiral galaxies, including our own Milky Way, is thought to have a supermassive black hole at its center. NGC 2841, the spiral galaxy. NGC 2841 shows a majestic disk of stars and dust lanes. A bright arc of light marks the galaxy's center. The dust lanes are silhouetted against the middle-aged population of whitish stars. Younger blue stars trace the spiral arms. The absence of pinkish emission nebulae suggests that new stars have not yet formed. Radiation and supersonic winds from young, superhot blue stars probably cleared out the remaining gas, which glows pink, thus stopping further star formation in the areas where they were born. In contrast to other spirals ablaze with emission nebulae, NGC 2841 has a relatively low star formation rate. In the constellation Ursa Major, the Great Bear, NGC 2841 lies 46 million light-years away. The wavelengths of light range from ultraviolet to visible to near-infrared. Hubble's Wide-Field Camera 3 captured this image in 2010 using 4 different filters. Galaxy M82 starburst. The Cigar Galaxy, also known as M82, appears bright at infrared wavelengths and is notable for its star formation activity. It experiences gravitational interactions with its galactic neighbor M81, causing it to have an extraordinarily high rate of star formation, a starburst. Young stars are born around the galaxy's center 10 times faster than inside our Milky Way. The radiation and energetic particles from these newborn stars carve into the surrounding gas, and the resulting galactic wind compresses enough gas to form millions of new stars. The accelerated rate of star formation in this galaxy will eventually self-limit. The process of star formation will destroy or consume the material necessary to create more stars if it becomes too vigorous. In tens of millions of years, the starburst will subside. German astronomer Johann Elert Bode discovered M82 and its neighbor M81 in 1774. M82 is a star 12 million light-years from Earth in Ursa Major's constellation. It has an observed magnitude of 8.5 and is best observed in April. Binoculars can see it as a patch of light, but larger telescopes are needed for a clear view of the galaxy's core. NGC 2207 and IC 2163 are spiral galaxies. 2 spiral galaxies glide by each other like magnificent ships in the night sky in the direction of the constellation Canis Major. NASA's Hubble Space Telescope's Wide Field Planetary Camera 2 captured images of the near collision. IC 2163 is the smaller galaxy on the right. NGC 2207 is the larger and more massive one on the left. The far-reaching tidal forces from NGC 2207 have distorted the shape of IC 2163, flinging stars and gas into long streamers stretching across 100,000 light-years. A team led by Bruce Elmer-Green and Deborah Elmer-Green performed computer simulations that demonstrate galactic collisions occur over a leisurely timescale. The National Science Foundation's Very Large Array Radio Telescope in New Mexico provides additional measurements which help reconstruct the collision based on the Hubble images. MAX 1206 – Gravitational Lens and Galaxy Cluster. The Hubble Space Telescope image shows the massive galaxy cluster MAX J1206. The cluster contains distorted images of distant background galaxies seen as arcs and smeared features. Gravitational lensing occurs when light from faraway galaxies is bent and magnified by the dark matter in the cluster. Astronomers can study distant galaxies that would otherwise be too faint to observe due to this phenomenon. Researchers measured the invisible glue that holds stars together within galaxies and makes up the bulk of the matter in the universe. A combination of visible and infrared light observations was taken by the Hubble Space Telescope in 2011. Stellar Fireworks Finale ranked first in Young Universe. Based on this artist's impression, an incredibly early universe, less than 1 billion years old, appears to have gone through a voracious onset of star formation, converting primordial hydrogen into many stars at an unprecedented rate. Compared to the sea of quiescent galaxies we see around us today, the sky would have looked very different back then. There are many starburst galaxies, but giant elliptical and spiral galaxies have yet to form. Starburst galaxies are filled with bright knots of blue stars that appear and disappear like fireworks. A torrent of ultraviolet radiation causes the regions of new starbirth to glow intensely red. Massive stars explode as supernovas and appear like a string of firecrackers across the sky. A starburst galaxy is sculpted with hot bubbles from supernova explosions and torrential stellar winds in the lower right. These galaxies have very little dust, since the heavier elements have not yet formed through nucleosynthesis. Hubble Space Telescope deep sky images support the theory that the first stars formed abruptly rather than gradually. Electrons and subatomic particles stream from the center of galaxy M87. One of nature's most amazing phenomena is the jet of electrons and other subatomic particles streaming out from the center of galaxy M87 like a cosmic searchlight. The blue of this jet contrasts with the yellow glow of billions of unseen stars that make up this galaxy. M87, NGC 4486, appears to be an ordinary elliptical galaxy, one of many ellipticals in the nearby Virgo cluster. Nonetheless, in 1918, astronomer H.D. Curtis noticed a curious straight ray emerging from M87. When the field of radio was blossoming in the 1950s, one of the brightest radio sources in the sky, Virgo A, was discovered to be associated with M87 and its jet. In the wake of these discoveries, decades of research have led to discovering the source of the jet's immense power. At the center of M87 is a supermassive black hole that has swallowed up a mass 2,500 million times the mass of our Sun. This jet is produced by the intense twisted magnetic fields trapped in the plasmas surrounding this black hole, and originates in the disk of superheated gas that swirls around it. Synchrotron radiation, electrons twisting along magnetic field lines in jets, produces the light we see and the radio emission, giving the jet its bluish tint. NGC 4038-4039 Antenna Galaxies. This is the sharpest image of the merging galaxies antenna taken by NASA's Hubble Space Telescope. As a result of the collision, billions of stars will form. The brightest and most compact starbirth regions are superstar clusters. A few 100 million years ago, two spiral galaxies began interacting, making the antennae galaxies one of the closest and youngest examples of galaxies colliding. The original galaxies consist primarily of old stars crisscrossed by filaments of dust, which appear brown in the image. Both galaxies are dotted with brilliant blue star-forming regions surrounded by glowing hydrogen gas, which appears in pink. In the antennae image, nearly half of the faint objects are young star clusters, containing tens of thousands of stars. The Crab Nebula, fragments in the heart. China's astronomers were startled by the appearance of a new star in 1054 AD, which was so bright for several weeks. On July 4, 1054, it exploded as a supernova. The Crab Nebula is visible today at the guest star location. Approximately 6,500 light-years from Earth, the Crab Nebula is the remnant of a star about 20 times as big as the Sun when it began. Hubble's Wide Field and Planetary Camera 2 acquired the Crab Nebula data in 1995. This false-color picture was created by combining 5 images taken with 5 different color filters. Unlike Jackson Pollock's abstract paintings, the image shows ragged shreds of gas expanding away at over 3 million miles per hour. Pulsars are neutron stars that revolve on their axis 30 times a second. In the Hubble image, the star's core is the lower of the two moderately bright stars to the upper left of the center. The ghostly diffuse bluish-green glowing gas cloud it produces in its vicinity and a blue arc immediately to its right results from heating its surroundings. Fireworks from space. Sheets of debris from a stellar explosion, N49 DEM-L190. These delicate filaments look like puffs of smoke and sparks from a summer firework display, but they are sheets of debris from a stellar explosion in a neighboring galaxy. It targeted a supernova remnant within the Large Magellanic Cloud, LMC, a nearby small companion galaxy to the Milky Way, observable from the southern hemisphere. N49, or DEM-L190, is the remnant of a massive star that died in a supernova blast thousands of years ago. Supernovae exploded billions of years ago in the Milky Way and left behind debris similar to our Sun and planets. The filamentary material will eventually be recycled into new generations of stars in the LMC. Hubble's giant mosaic of the Crab. NASA's Hubble Space Telescope took this mosaic of the Crab Nebula, a 6 light-year wide remnant of a star's supernova explosion. Native Americans also recorded this violent event nearly 1,000 years ago in 1054. Most of the hydrogen in the orange filaments is left over from the star. As the dynamo driving the nebula's eerie interior blue glow, the neutron star embedded in its center rapidly spins. In the neutron star, electrons are whirling at nearly the speed of light around magnetic field lines. Due to the neutron star's rotation, it emits twin beams of radiation that pulse 30 times a second, like a lighthouse. An exploded star's neutron star is its crushed, ultra-dense core. A drawing of the Crab Nebula made in 1844 by Irish astronomer Lord Rosse gave its name, using a 36-inch telescope. As seen by Hubble and large ground-based telescopes like the Very Large Telescope of the European Southern Observatory, the Crab Nebula takes on a more detailed appearance that sheds light on a star's spectacular demise 6,500 light-years away. Streamers from nebula N44C flutter in stellar breeze. A region of glowing hydrogen gas surrounds an association of young stars in the Large Magellanic Cloud. Softly glowing filaments of light emanate from a complex of young stars, like the hair in Botticelli's famous portrait of Venus's birth. NASA's Hubble Space Telescope, HST, took this picture of N44C, a nebula. The Hubble Heritage Project presented this image taken with the Wide Field Planetary Camera 2 in 1996. Unlike other nebulae, N44C has a scorching star that illuminates it. Massive stars, between 10 and 50 times more massive than the Sun, have maximum temperatures ranging from 54,000 to 90,000 degrees Fahrenheit, 30,000 to 50,000 degrees Kelvin. N44C star appears to be significantly hotter, about 135,000 degrees Fahrenheit, 75,000 degrees Kelvin. Theories have been proposed to explain this unusually high temperature, including the possibility of a neutron star or black hole that intermittently emits X-rays, but has now switched off. Image of the Egg Nebula in rainbow colors. The Egg Nebula offers astronomers a unique look at the normally invisible dust shells surrounding an aging star, a rippling pool illuminated by underwater lights. The hidden star emits two beams of light that illuminate the pitch-black dust like a flashlight in a smoky room. These dust layers extend over 1/10 of a light-year away from the star and have a structure that forms rings around the star. A dust belt runs almost vertically across the image, blocking light from the central star. With the artificial Easter egg colors in this image, we can see how the light reflects off the smoke-sized dust particles and then travels towards Earth. During the day, dust in our atmosphere reflects sunlight so that only certain light waves get reflected to us. The same is true for reflections off water or roadways. Polarizing sunglasses use this effect to block out all reflections except those aligned with the polarizing filter material. It is like sliding a piece of paper under a door. For the paper to pass under the door, it must be parallel to the ground. Known as the Cat's Eye Nebula. NASA's Hubble Space Telescope captured this new, detailed view of the Cat's Eye Nebula, NGC 6543, a bullseye configuration of 11 or even more concentric rings or shells around the cat's eye. Rather than being rings, each ring is the edge of a sphere projected onto the sky. That is why it appears bright along its outer edge. According to observations, the star ejected its mass in a succession of pulses every 1,500 years. Dust shells created by these convulsions contain as much mass as all the planets in our solar system collectively, still only 1% of the mass of the Sun. Concentric shells form an onion-like structure around the dying star. Hubble's view is similar to splitting an onion in half, where each layer can be seen. Astronomers were surprised to see bullseye patterns around planetary nebulae, as they did not expect that periods of mass loss at the end of stellar lives would repeat every 1,500 years. Many possible explanations have been proposed, including magnetic activity cycles like our Sun's sunspot cycle, companion stars rotating around the dying star, and stellar pulsations. Another theory is that the outflowing material is smooth and the rings are formed later due to the waves. Helix Nebula. A dying star is exhibiting a cosmic tantrum. The star's outer dusty layers unravel into space during death, glowing from the intense ultraviolet radiation emitted by the hot stellar core. Around 650 light-years away in the constellation of Aquarius is the Helix Nebula. It is typical of a class of objects called planetary nebulae, also known by the catalogue number NGC 7293. Their resemblance to gas giant planets led to their false name when discovered in the 18th century. Astronomers believe that planetary nebulae were once stars that looked a lot like our Sun. These stars transform hydrogen into helium in their cores in massive runaway nuclear fusion reactions. All of our Sun's light and heat comes from this fusion process. When our Sun dies in about 5 billion years, it will become a planetary nebula, When the hydrogen fuel for fusion reaction runs out, the star turns to helium for fuel, burning it into an even greater mix of carbon, nitrogen, and oxygen. The star will also exhaust its helium, displacing its outer gaseous layers and leaving behind the tiny, hot, dense core, known as a white dwarf. Despite being about the size of Earth, the white dwarf has a mass very similar to that of the initial star. In fact, a teaspoonful of a white dwarf would weigh as much as a few elephants. An intriguing feature of planetary nebulae is that they appear remarkably similar across various wavelengths, from ultraviolet to infrared. The helix is recognizable at any wavelength, but the combination shown here emphasizes subtle differences. MYCN18, a planetary nebula. Image of MYCN18, a young planetary nebula about 8,000 light-years away, taken with NASA's Hubble Space Telescope, HST. Hubble's image reveals that MYCN18 is an hourglass with intricate etchings on its walls. This picture was composed of 3 images taken in the light of ionized nitrogen, represented by red, hydrogen, green, and doubly ionized oxygen, blue. These results shed new light on the poorly understood ejection of stellar matter accompanying the slow death of Sun-like stars. Based on previous ground-based images, MYCN18 appears to be a pair of large outer rings and a smaller central ring, but the fine details are not visible. MYCN18, as revealed by Hubble, does not meet some crucial theoretical expectations. The hot star, which is supposed to eject light from the nebula and lie at its center of symmetry, is off-center. On closer inspection, an apparent bright elliptical ring at the center, which might be mistaken for an equatorially dense region at first sight, is revealed to be a potato-shaped structure with a symmetry axis significantly different from that of the enormous hourglass. NGC 2392, the Eskimo Nebula. NASA's Hubble Space Telescope captured its first glimpse of the heavens after its successful December 1999 servicing mission showing a planetary nebula, the glowing remains of a dying star. William Herschel first spotted NGC 2392 in 1787. The inner nebula also contains intriguing details. While the bright central region resembles a ball of twine, it is a bubble of material blown into space by the central star's high-speed wind. A dying star is surrounded by 2 elliptically shaped lobes of matter that stream above and below it. One bubble partially obscures the second lobe in this photo because it is positioned in front of another. The red rectangle. Dying star HD 44179. They may not have seen the fabled stairway to heaven, but they have captured something fascinating: ladder-like structures encircling a dying star. An image taken with NASA's Hubble Space Telescope reveals startling new details about one of the Milky Way's most unusual nebulae. HD 44179 is also known as the red rectangle, due to its unusual shape and color, as seen with ground-based telescopes. Hubble has revealed many new features in the red rectangle that could not be seen from Earth by ground-based telescopes. The Astronomical Journal published details of the Hubble study in its April 2004 issue. Hubble's sharp pictures reveal that the red rectangle is not really rectangular, but instead has an overall X-shaped structure that the researchers attribute to outflows of gas and dust from the star at its center. A star's outflows eject in opposing directions, producing the appearance of 2 ice cream cones touching at their tips. This nebula is also remarkable for its straight features that resemble ladder rungs, making it resemble a spider web, unlike any other nebula we know of. These rungs may have formed every few hundred years during episodes of mass ejection from the star. As a series of nested, expanding structures, they could resemble wine glasses seen exactly edge-on, so their rims appear as straight lines. As the dying star flung material into space, the planetary nebula began forming about 10,000 years ago. Nebula spirograph, IC 418. The star in the middle of IC 418 was a red giant, but then it ejected its outer layers into space, producing the nebula, which has a diameter of about 0.2 light-years. From the hot core of the red giant, the stellar remnant at the center emits ultraviolet radiation, causing the surrounding gas to fluoresce. For millions of years, the nebula will gradually cool and fade away as a white dwarf. IC 418 was likely like our Sun only a few million years ago. The Sun is expected to undergo a similar fate, but fortunately, this will not happen for 5,000 million years. Perhaps they are caused by chaotic winds from the central variable star, which changes brightness unpredictably in just a few hours. Extrasolar planet HD 189733b as seen by an artist. A hot Jupiter-class planet is shown orbiting its yellow-orange star HD 189733. NASA's Hubble Space Telescope measured the planet's visible light color, deep blue. It is not due to oceans, but to the effects of a 2,000-degree atmosphere where silicate particles melt to form raindrops of glass that scatter blue light more than red light. HD 189733b was found in 2005 and is only 2.9 million miles away from its parent star. The planet is gravitational tidally locked, so that one side always faces the star and the other is permanently dark. In 2007, NASA's Spitzer Space Telescope created a thermal map that revealed the presence of a hot spot on Earth in the early afternoon. The high-altitude clouds laced with silicates may blow from the day side to the night side at 4,500 miles per hour. The planet is only 60 light-years from Earth. Alpha Centauri, the closest star to our Sun, appears as two faint stars near the center of the image. HH-110 Cosmos Skyrocket. The Herbig-Haro 110 is a geyser of hot gas ejected from a molecular hydrogen cloud. Photo from the Hubble Space Telescope shows plumes that are light-years across. While gas plumes appear to be smoke, they are billions of times less dense than the smoke from a July the 4th firework. There is a wide variety of Herbig-Haro HH objects, but the basic configuration remains the same. Streams of heated gas are ejected in opposite directions away from a forming star. Scientists suspect that these outflows are fueled by gas accreting onto a young star surrounded by a disk of dust and gas. Using a disk as a fuel tank, a star as a gravitational engine, and jets as an exhaust. It is like a traffic jam on the interstate when these energetic jets collide with colder gas. The gas slows to a crawl within the shock front, but more gas piles up as the jets continue to slam into the shock from behind. The curving, flaring region begins to glow when the temperature rises sharply. As the name implies, bow shocks resemble the waves that form at the front of a boat. HH-901 Mystic Mountain Jet Detail. This close-up series shows the complex gas structures in a small portion of the Carina Nebula. A nebula is a cloud of predominantly hydrogen gas. Due to its dusty composition, the cloud is opaque. An ultraviolet gusher originating from a young star is eroding the cloud. The animals sculpt a variety of fantasy shapes, some resembling tadpoles. The 2.3 trillion mile-long structure at the upper right is a small piece of nebulosity freely drifting in some frames. In the upper left frame, there is a 3.5 trillion mile-long horizontal jet. A star hidden at the tip of the pillar-like structure is blasting it into space. A bow shock has formed near the jet's tip. Illustration of exoplanet HD 189733b, artist's rendition. In this artist's rendering, HD 189733b's atmosphere is shown evaporating due to a powerful eruption from its star. Concept art of the exoplanet OGLE 2005 BLG 390LB. Located near the center of our galaxy, the Milky Way, this exoplanet is around 25,000 light-years away from Earth. It orbits its parent star every 10 years, and is about 3 times as far away as Earth is from the Sun. Concept of an exoplanet orbiting Fomalhaut. It shows the newly discovered planet Fomalhaut b orbiting its Sun. Around Fomalhaut b is a structure mainly made of brown and gold colors. A Saturn-like ring may encircle the planet, say astronomers. A material ring also surrounds Fomalhaut. An edge of this vast disk is shown in the background as a cloud-like feature that intersects the 200-million-year-old star. Fomalhaut b is located 1.8 billion miles inside the disk's inner edge. Every 872 years, the planet completes an orbit around Fomalhaut. Gliese 876, a giant red dwarf star orbiting the Earth. New Hubble Space Telescope measurements of the star's wobble, caused by the planet's gravitational pull, have confirmed that the planet's mass is approximately twice that of Jupiter. There is only 1/5 the distance between the planet and the star between the Earth and the Sun. As the planet is too far away to be photographed by modern telescopes, it is probably a gas giant world possibly encircled by moons, as depicted in this illustration. As estimated by earlier ground-based observations, Gliese 876 also contains an inner planet with a mass half that of Jupiter. The inner gas planet in the system appears like a bright star near the red dwarf. Despite its proximity to Earth, the red dwarf star is too faint to see with the naked eye. Its mass is 1/3 that of our Sun. WFC3 Planetary Nebula NGC 6302. Located roughly 3,800 light-years away in Scorpius, NGC 6302 is a spectacular planetary nebula. More commonly known as the Bug Nebula or Butterfly Nebula, this celestial object resembles a delicate butterfly. The dainty-looking wings are roiling regions of gas heated to over 36,000 degrees Fahrenheit. Gases are hurling through space at 600,000 miles per hour. Expelled over about 2,200 years, the blowing gas represents the star's outer layers. Approximately half the distance from the Sun to the nearest star, Alpha Centauri, is covered by the butterfly. Towards the center of this fury is a dying star that was once about 5 times the mass of the Sun. Having ejected its gaseous envelope, it emits ultraviolet radiation, making the cast-off material glow. When viewed through a small telescope, this object is an example of a planetary nebula, which is named because many of them appear round like planets. A donut-shaped ring of dust, or torus, surrounds the star, hidden within the nebula's center, and appearing as a dark band that pinches it. Several planetary nebulae display the classic bipolar or hourglass shape owing to the thick dust belt surrounding the star. NGC 1309, ACS, a pinwheel-shaped galaxy. NASA's Hubble Space Telescope recently observed this dramatic spiral galaxy. A color image of NGC 1308, an upright spiral galaxy, is captured with stunning details. SN 2002FK, whose light reached Earth in September 2002, was located in NGC 1309. NGC 1309 is located 100 million light-years, 30 megaparsecs. About 200 galaxies make up the Eridanus group of galaxies. Trapezium Cluster of Orion, NICMOS. The NASA ESA Hubble Space Telescope uncovered a swarm of newborn brown dwarfs deep within a stellar nursery. Near-infrared images from the orbiting observatory's near-infrared camera showed approximately 50 of these objects in the Orion Nebula's trapezium cluster about 1,500 light-years away. An image taken by the Hubble telescope's Wide Field and Planetary Camera 2 cannot see brown dwarfs because they are too dim. As with the near-infrared image, this view does not show the assemblage of infant stars. This is because dense clouds of dust and gas surround young stars. Using its near-infrared camera and multi-object spectrometer, Hubble's near-infrared telescope captured images of those objects through the clouds. Investigating doomed star Eta Carinae, STIS. For decades, astronomers have been enchanted by the signature balloon-shaped gas clouds blown from two massive stars called Eta Carinae. Eta Carinae has exhibited violent outbursts due to her volatile temperature over the past 200 years. The newly repaired Space Telescope Imaging Spectrograph, STIS, aboard NASA's Hubble Space Telescope, has discovered a stream of charged particles emanating from a massive stellar wind and some of the chemical elements emitted during the eruption in the middle of the 19th century. Chemical information was resolved along a narrow section of one of the giant lobes of ejected material using STIS. In the resulting spectrum, iron and nickel define the outer material cast off from Eta Carinae in the 19th century. The STIS also reveals the interior material being carried away by the wind from Eta Carinae, the primary star. A sun's worth of mass is carried away by the wind every 1,000 years. The Pleiadae and HST field of view, FGS. The stars in this image are members of the Pleiades, or Seven Sisters, an open star cluster. Hubble's fine guidance sensors refined the distance to the Pleiades to about 440 light-years. Hubble's field of view includes the fine guidance sensors. A circumference approximately equal to the angular size of the Moon is traced. They are superimposed on this image to give a sense of Hubble's very narrow view of the heavens. Eagle Nebula, Messier 16. M16, or the Eagle Nebula, is dominated by towering tendrils of cosmic dust and gas. This is not Hubble's first image of this iconic feature of the Eagle Nebula, but it is the most detailed. Blue represents oxygen, red represents sulfur, and the green represents both nitrogen and hydrogen. A cluster of young stars emits scorching ultraviolet light outside the frame to bathe the pillars. Eventually, the dust and gas are being eroded by the winds of these stars. In addition to spanning roughly 4 to 5 light-years, the pillars of creation represent a fascinating but relatively minor feature of the Eagle Nebula, which spans 70 by 55 light-years. This nebula was discovered in 1745 by Swiss astronomer Jean-Philippe Loy-de-Chasseau. It is possible to see the Eagle Nebula through a small telescope with an apparent magnitude of 6. Pillars of creation can only be resolved with a large telescope and optimal viewing conditions. Nebulae of Orion. The Maya believes M42 of Mesoamerica to be the cosmic fire of creation. It is located in the constellation Orion. Throughout human history, many different cultures have known this stellar nursery as the Orion Nebula. 1,500 light-years away, the nebula is the nearest sizable star-forming region to Earth, with an apparent magnitude of 4. M42 can be seen with the naked eye due to its brightness and prominent location below Orion's belt, while its stellar birth is visible with telescopes. It is best observed in January. The Maya culture compared the Orion Nebula to a cosmic fire of creation. 4 massive young stars form the nebula's bright central region. 4 big stars are called the trapezium because they are arranged in a trapezoidal pattern. Ultraviolet light emitted by these stars is carving a cavity in the nebula and disrupting the growth of hundreds of smaller stars. Hubble's image of the Orion Nebula is the sharpest ever taken. This mosaic was created from 520 different Hubble exposures in multiple wavelengths of light. In the image, orange represents hydrogen, green represents oxygen, red represents sulfur, and observations are made with infrared light. Hubble captured most of the nebula, but ground-based images filled the gaps. Globules of Thackeray. Beautiful and remarkable images taken by NASA's Hubble Space Telescope show strangely glowing dark clouds. Dense, opaque dust clouds, called globules, are silhouetted against nearby bright stars in the active star-forming region IC 2944. The globules were first discovered in IC 2944 by astronomer A.D. Thackeray in 1950. Omega Centauri, the core of the globular cluster. Using NASA's Hubble Space Telescope, scientists have peered into the heart of a dense swarm of stars called Omega Centauri. Omega Centauri, a massive globular star cluster located some 17,000 light-years from Earth, contains several million stars in locked orbits around a common gravitational center. Ground-based telescopes have difficulty making out individual stars because the cluster's core is packed so densely with stars. As a result, Hubble's high resolution can pick up where ground-based telescopes leave off, capturing distinct points of light from stars at the cluster's center. M100 Galaxy. M100 is an excellent example of a spiral galaxy with a grand design. The Hubble image shows individual stars within the galaxy's prominent spiral arms. The dusty structures swirl around the galaxy's nucleus and are characterized by a flurry of star formation. Additionally, M100's characteristic arms contain several small black holes, including the youngest ever observed in our galaxy. In 1781, the French astronomer Pierre Misshapen, Charles Messier's fellow comet hunter, spotted the galaxy and discovered 8 comets in his lifetime. Despite its distance from Earth, M100 appears dim in the night sky. At the same time, it can be observed through small telescopes. Its apparent magnitude of 10.1. The galaxy can be observed in greater detail with larger telescopes. During May, you can observe M100 in the constellation Coma Berenices. Because of the camera's design, the image has a stair-step appearance. One of the 4 light detectors on the camera had a higher resolution but a smaller field of view than the other 3. Since the detector with the higher resolution does not cover as much area as the other 3, when the images from all 4 detectors are combined into one picture, there will be black regions. This is the Cygnus Loop Nebula. The Cygnus Loop, the Veil Nebula, is a remnant of a supernova explosion about 10 to 20,000 years ago. Modeling its spectacular filamentary shape suggests the explosion was inside an interstellar cavity created by the progenitor star. Many of an object's physical properties are uncertain in astronomy due to its distance. Recent distance estimates have ranged over a wide range, generally consistent with this one, though the most commonly quoted value is a 2005 measurement between 1,500 and 2,100 light-years. The past 2 decades have seen astronomers attempt to pin down the distance by measuring the distances to nearby stars, measured as absorption lines from the nebula in their spectra. But the distances to those stars are also uncertain, and parallax measurements of some of the stellar distances have also been unreliable. Recent efforts have also been made to measure the distance by observing the motions of the nebula gas directly, estimates suggesting a distance of 2,600 light-years, which is consistent with the old value of 2,500 light-years.
The Great Rift Valley. Evocative words that immediately suggest origins. There are many reasons I love visiting Ethiopia. I love the people. I love the food. I love the high-altitude freshness of Addis. I love the mountains and valleys and high plains. I even loved visiting Erta Ale, the legendary shield volcano at the Afar triple junction known as the Gateway to Hell, although I probably won't do it again. But I also love an idea. It's impossible to visit this ancient country and not catch a glimpse in your peripheral vision of a chain of ghosts stretching back 10,000 generations, because it is firmly embedded in popular culture that we came from here. Every one of us is related to someone who lived in Ethiopia hundreds of thousands of years ago. It is the Garden of Eden, the place where humanity began. What popular culture has yet to assimilate, however, is the fortuitous and precarious nature of the ascent of man. When I was growing up, I remember talk of the missing link, that elusive fossil that would tie us definitively to our ape-like ancestors. When I started school, DNA sequencing was not yet invented, and Lucy hadn't been unearthed. Today, we have a significantly more complete view of how Australopithecines like Lucy are related to modern humans, and whilst the details are still debated and new evidence is continually updating the standard model of hominin evolution, it's now possible to tell the broad sweep of the story in some detail. The members of our human evolutionary family are referred to as hominins. The split between hominins and the ancestor of the chimpanzee occurred at some point before 5 million years ago in Africa, and by 4 million years ago, Australopithecus afarensis, Lucy, was present. Their brain size was approximately 500 cc, around the same as a chimpanzee, and less than 1/3 that of a modern human. Around 1.8 million years ago, there was a step change in both brain size and the number of hominin species in the East African Rift. Several species of our genus Homo appeared, including Homo habilis and Homo erectus. They lived for a time alongside other species, including several Australopithecines and a genus known as Paranthropus. There are anthropologists who prefer to classify Paranthropus as a different species of Australopithecus. I make this point not to be confusing, but to highlight an important fact. The study of hominin evolution is a difficult area, and it's not surprising that there are ongoing debates about the classification of 2-million-year-old fossils and DNA sequences. What's important for our story, however, and what nobody disputes, is that there seems to have been a jump in both brain size and the number of species of hominins in the Rift Valley region around 1.8 million years ago. By around 1.4 million years ago, only one of these species had survived, Homo erectus, with a brain size of 1,000 cc. The next milestone is the appearance of Homo heidelbergensis around 800,000 years ago. Homo heidelbergensis is generally accepted to be the ancestor of Homo sapiens and the Neanderthals who lived alongside us in Europe until around 45,000 years ago, and possibly later. Homo heidelbergensis represented another jump in brain size, up to around 1400 cc, which is close to that of modern humans. In the late 1960s and early 1970s, 2 hominin skulls were found near the Omo River in Ethiopia. Known as Omo 1 and Omo 2, argon dating of the volcanic sediments around the level they were found dates them at 195,000 plus or minus 5,000 years old. These are the earliest fossilized remains to have been identified as Homo sapiens. The interesting question is what caused these rapid increases in brain size, driving hominin intelligence from the chimpanzee-like capabilities of Australopithecus to modern humans in only a few million years. Again, this is a very active area of research, and there are differences of opinion amongst experts. This is the nature of science at the frontier of knowledge, and this is what makes science exciting and successful. The model we are focusing on is the most widely accepted theory of human evolution. It is known as the recent single origin hypothesis, or more colloquially, the out of Africa model, and the dates and locations we've described so far might be referred to as textbook. There is broad consensus, therefore, about the when and the where, but not why, and it is to why that we now turn. There's a trend towards larger brain size over the 4 million years since the emergence of Australopithecus, but the trend is not gradual. There's a large jump around 1.8 million years ago with the emergence of Homo erectus, and another jump just under 1 million years ago with Homo heidelbergensis. The final jump occurs when Homo sapiens emerges 200,000 years ago. The time period around 1.8 million years ago also corresponds to a leap in the number of hominin species present in the Rift Valley. There were at least 5 or 6 species living side by side, suggesting that something interesting occurred around this time, which may have been responsible for, or was a contributing factor to, the observed increase in brain size, particularly in Homo erectus. The large number of deep water lakes appearing temporarily in the Rift Valley around 1.8 million years ago indicates that at this time the climate, and in particular the level of rainfall, was varying quickly and violently. Similar climate variation occurs around 1 million years ago and 200,000 years ago, and this appears to be correlated with increase in hominin brain size. The theory is that rapidly changing climatic conditions in the Rift Valley at these specific times played an important role in driving the increases in brain size. The selection pressures that may have led to these increases are unclear. Selection for adaptability was probably an important factor, but social factors such as the ability to live in large groups and intraspecies competition as a result of the larger number of species living side by side, particularly around 1.8 million years ago, must also have played a role. Having said that, it does appear that climate variation in the Rift Valley 1.8 million, 1 million and 200,000 years ago could have been a contributing factor to the development of our intelligence. This is known as the pulse climate variability hypothesis. We can now bring all these threads together to reveal a surprising and, for me, dizzying hypothesis, which, if correct, sheds new light on the immensely contingent nature of the existence of our modern civilization, or, in simpler language, why we are bloody lucky to be here. The 3 dates, 1.8 million, 1 million and 200,000 years ago, correspond to the times when the Earth's orbit was at its most elliptical. As described earlier, the mechanism by which climate changes due to precession at these times is well understood. The pulse climate variability hypothesis asserts that the unique geology and position of the Great Rift Valley amplified these changes, and that early hominins responded by increasing their brain size. If this is correct, our brains evolved as a response to changes in the Earth's orbit, driven by the precise arrangement of the orbits of the other planets around the Sun, and precession, driven primarily by the gravitational interaction between the Moon and Earth's axial tilt, both of which date back to a collision early in the history of the solar system. And all this is plainly blind luck. Without an inconceivably unlikely set of coincidences, and the way these conspired together to change the climate in one system of valleys in wonderful Ethiopia, we wouldn't exist. If this is correct, then what a response! I held a brain for the cameras at St. Paul's Teaching Hospital in Addis. It is the most complex single object in the known universe, a most intricate example of emergent complexity, assembled over 4 billion years by natural selection, operating within the constraints placed upon it by the laws of physics and the particular biochemistry of life on Earth. The brain contains around 85 billion individual neurons, which is of the same order as the number of stars in an average galaxy. But that doesn't begin to describe its complexity. Each neuron is thought to make between 10,000 and 100,000 connections to other neurons, making the brain a computer way beyond anything our current technology can simulate. When we do manage to simulate one, I have no doubt that sentience will emerge. Consciousness is not magic. It is an emergent property consistent with the known laws of nature. But that doesn't lessen the wonder one iota. Out of this evolutionary marvel, we emerge. Thoughts, feelings, hopes, and dreams exist on Earth because of electrical activity inside a 1.5 kilogram blob of stuff, which hasn't changed much since the earliest modern humans began the long journey out of Africa. If you could travel back in time and bring a newborn baby from 200,000 years ago into the 21st century, allowing it to grow up in our modern society with a modern education, it could achieve anything a modern child could. It could even become an astronaut. Which sets up one more question. If the hardware was present 200,000 years ago, then what changed to lift us from the Great Rift Valley into space? An unprecedented duel with nature. "The best thing we can do now is just to listen and hope," said Cliff Mitchellmore, broadcasting from the BBC studios 24 minutes from the expected splashdown of Apollo 13. On the 17th of April 1970, I was too young to watch the live broadcast, but I've seen the recording many times since. Grainy pictures from the deck of the USS Iwo Jima, its flight deck crammed with nervous sailors off the coast of Samoa. Patrick Moore and Geoffrey Pardo, grim-faced in the studios, and James Burke famously with fingers crossed behind his back. "Apollo Control, Houston, we've just had loss of signal from Honeysuckle." Honeysuckle Creek Tracking Station in Canberra, Australia, was the last ground station to contact Apollo 13 before it entered the Earth's atmosphere on its way home. Signal loss during re-entry is routine high drama on all space missions. The ionization of the atmosphere caused by the frictional heating of the spacecraft blocks radio signals, typically resulting in radio silence for 4 minutes. On Apollo 13, 6 minutes passed in silence. The brilliance of the BBC's quartet of commentators was in the silence they allowed on the airwaves. The only sound was the static of the NASA feed, a moment of genuine tension. No need for vacuous media babble. Nobody could bring themselves to speak. "We'll only know whether that heat shield was damaged by that explosion 3 days ago, when they come out of radio blackout in just over 2 minutes, said Burke. Silence. As 4 minutes passed, Houston reports, 10 seconds to end of radio blackout. Silence. Houston. We've had a report that Orion 4 aircraft has acquisition of signal. They're through, says Burke. Let's not anticipate because the parachutes may have been damaged. Chutes should be out, murmurs Burke, not broadcasting, just saying. There they are! There they are! They've made it, remarks Moore, and then applause. I make it no more than 5 seconds late, shouts Burke. No more than 5 seconds late. The safe return of Apollo 13 was arguably NASA's finest hour. 55 hours, 54 minutes, and 53 seconds into the mission, 320,000 kilometers from Earth, lunar module pilot Jack Swigert switched on a system of stirring fans in the hydrogen and oxygen tanks in the service module, a routine procedure. A piece of Teflon insulation inside the tank had been damaged, it was later discovered, by a series of unlikely events that happened on the ground during the preparation of the spacecraft for flight. The wire shorted, the tank exploded, and the side of the service module was blown off, critically damaging the spacecraft's power supply systems and venting the crew's oxygen supply out into space. The command module, the only part of the spacecraft capable of surviving a re-entry through the Earth's atmosphere, was now running on batteries, and with a rapidly diminishing oxygen supply that would not keep the astronauts alive long enough to return to Earth. The only option was to shut down the command module and retreat to the lunar module, effectively using it as a life raft. Lovell later spoke of how he didn't regret the mission at all. He was robbed of his moon landing, which must have been doubly frustrating given he'd already flown to the moon on the historic Apollo 8 mission. But his reaction, revealed in interviews in later life, offers great insight into the character of a test pilot. We were given the situation, Lovell explained, to really exercise our skills and our talents to take a situation which was almost certainly catastrophic and come home safely. That's why I thought that 13 of all the flights, including Apollo 11, that 13 exemplified a real test pilot's flight. Both Lovell and Hayes have said that the idea of not returning safely to Earth never really came up. There was nothing there that said irrefutably, we don't have a chance. Hayes was correct, of course, because they did return safely. But they only had enough food and water to sustain 2 people for a day and a half, and had to improvise a carbon dioxide filter to provide them with enough breathable air for the return journey. Locked in the lunar module with limited supplies of food and water, and temperatures dropping towards freezing, life was far from comfortable. With the command module powered down to preserve the sparse battery supplies left after the loss of the fuel cells, the crew had to survive in a hostile environment with limited resources. Like so many outposts of human civilization throughout history, shortage of water was a primary concern. Water was critical on the lunar module for two reasons. As well as being needed to keep the crew hydrated and to rehydrate the food, it also cooled the electrical systems on the spacecraft. Conserving water therefore became a critical part of the plan to return to Earth. Reducing their intake to just 1/5 of a normal human water ration, each of the crew suffered severe dehydration, and together they lost 31.5 pounds in weight, nearly 50% more than any other Apollo crew. Despite the discomfort, setting a new mission trajectory and navigating their way along it remained the primary challenge. The standard way to make in-flight course corrections on Apollo was to use the command module's main engine. But the system was located close to the damaged site, and mission controllers decided that lighting it was too great a risk. Instead, the decision was made to use the LM's descent engine to send them around the far side of the Moon and back to Earth in 4.5 days. This is known as a free return trajectory, a slingshot around the Moon at the correct angle to return directly to Earth. No one knew if an engine designed for a completely different purpose would perform this function successfully. But they knew that if it failed, they would not return. 5 hours after the initial explosion, the LM engine was fired for a 35-second burn, successfully putting the crew onto a free return trajectory. This solved one problem, but raised another. Calculations of the trajectory estimated return to Earth 153 hours after launch, which would push the key reserves on the craft too low for comfort. So it was decided to speed up the spacecraft with another burn, cutting the total time of the voyage by 10 crucial hours. Such were the slim margins on Apollo 13. The main navigation system in the command module was out of action, so Lovell had to calculate the correct navigational inputs, while back at base, Mission Control worked through the same calculations as a cross-check. Lovell also got to use his sextant, which he played with on Apollo 8, to navigate by the stars for real. The calculations are preserved as handwritten notes in the Lunar Module Systems Activation Checklist. This was the checklist Lovell and Hayes would have used to fly down to the Moon's surface. Now useless, Lovell used the waste paper to write down instructions to put the ship on course for Earth. 2 hours after they rounded the far side of the Moon, the LM engine fired, following Lovell's handwritten checklist, increasing the speed of the spacecraft by 860 feet per second and buying them 10 precious hours. The most dramatic rescue in the history of human spaceflight stands as a testament to the brilliance of the 3 test pilots Lovell, Hayes, and Swigert, and also to the brilliance of the engineers on the ground, who simply knew their stuff. NASA's Apollo engineers were young by today's standards. The average age of the team in mission control for the splashdown of Apollo 11 was 28 years old. This is one of the reasons why the United States reaped such a colossal economic reward from its investment in Apollo. The generation of scientists and engineers who worked on and were inspired by Apollo went out into the wider economy and delivered a huge investment return. A series of studies, including one by Chase Econometrics, showed that for every dollar invested in Apollo, at least $6 or $7 was returned as increased GDP growth. This should, of course, be bloody obvious. New knowledge grows GDP. But every generation of politicians seems to require re-educating to understand the difference between spending and investment. And while I'm polemicizing, let me say that the usual political argument that public support is needed for such large investments is drivel. Firstly, the investment in NASA wasn't that large, never exceeding 4.5% of the federal budget throughout the lifetime of Apollo. And secondly, it is a politician's job to lead from the front. Make the case that investment in knowledge, in pushing the boundaries of human capabilities and exploring all frontiers, both physical and intellectual, is the key to the future wealth, prosperity, and security of civilization. Aspire to be Kennedy, not a hand-wringing apologist for intellectual and technological decline. The 9 Apollo flights to the Moon remain the furthest modern humans have explored beyond the Rift Valley in our 200,000-year history. Homo sapiens first left Africa in large numbers 60,000 years ago. So on geological timescales, we didn't hang around. Our ancestors followed waves of earlier hominins. Homo erectus were in Southeast Asia 1.6 million years ago, and 500,000 years later Neanderthals had colonized Europe, and Homo floresiensis were in southern Asia. The details of the migration 60,000 years ago are particularly well understood as a result of the combination of genetic, archaeological, and linguistic studies. The precision comes in part from the tracking sequences of mitochondrial DNA, which is passed down from the mother and not shuffled by sex. This makes it relatively stable and easy to track. Changes are caused by mutations alone. The most widely accepted interpretation of the data suggests that a small population of between 1,000 and 2,500 individuals left East Africa 60,000 years ago and moved north across the Red Sea and through Arabia. The group then split, moving into southern Europe 43,000 years ago and travelling through India and into Australia on roughly the same timescale. The crossing into North America via eastern Russia was probably later, around 15,000 years ago. These early groups of humans were hunter-gatherers. It's been estimated that the basic social units would have reached a maximum of around 150 individuals. This is known as Dunbar's number, after the British anthropologist Robin Dunbar, who suggests that the largest social group amongst any given population of primates is related to the size of their brains, specifically the neocortex. Dunbar's number can be observed today in the size of the average person's social network, both in the real world and online. Our hardware, the brain, has not changed appreciably since the first humans appeared in Africa 200,000 years ago. These social groups would have lived in loosely bound tribes, perhaps reaching a size of between 1 and 2,000 individuals, operating within an area of around 100 kilometers. Populations would stabilize, perhaps in response to social factors, but also as a result of increased mortality rates caused by parasitic diseases and diminishing per capita resource availability, before fragmenting and spreading. In this fashion, the rate of progression of our ancestors across the globe has been estimated to have been around 0.5 kilometers per year, or 15 kilometers per generation. Population density did not rise significantly beyond these levels until these proto-societies shifted from a hunter-gatherer lifestyle to agriculture around 12,000 years ago. This shift was the trigger for the development of civilization, the most important single step following the migration out of Africa in the journey from ape-man to spaceman. There are many competing theories as to the reason for the domestication of crops, but many note the correlation between the first evidence of agriculture and the beginning of the current interglacial period known as the Holocene, 12,000 years ago. In the Fertile Crescent around modern-day Jordan and Syria, people known as the Natufians were beginning to settle into larger communities, perhaps because of the relatively benign climate. The area would have been forested and rich in wild cereals, fruits and nuts rather than the austere desert of today. One theory is that a brief 1,000-year cold period known as the Younger Dryas, beginning around 10,800 BCE, triggered drier conditions in the region, forcing the Natufians to begin cultivating the previously abundant wild crops on which they had come to rely. Whatever the reason, it's generally agreed that the foundational crops of modern agriculture, including wheat, barley, peas and lentils, were all to be found in the Fertile Crescent by 9,000 BCE, and by 8,000 BCE, the banks of the Nile were being cultivated. At approximately the same time, evidence of farming can be found in Asia's Indus Valley, in China, and in Mesoamerica. This suggests that there was no single environmental or developmental cause for agriculture, because it appeared independently at many sites across the world. Rather, our large brains and relatively large social groups were ready to take up the challenge when the need arose. Once agriculture was established, larger numbers of people could live together, taking advantage of the more stable food supply. The freedom from continual hunting and gathering would have introduced a new aspect to human life, free time, and it was used to great effect. Some of the earliest farmers settled in a place known as Beda in modern-day Jordan around 7000 BCE. Living in round stone-built houses, they grew barley and wheat and kept domesticated goats, engaged in ritual and ceremony, and buried their dead. Importantly, each of these activities was carried out in specific areas of the settlements, the beginning of town planning. By the 2nd century BCE, a Semitic people known as the Nabateans lived around Beda. They employed new technologies to increase the reliability of farming, and constructed walled agricultural terraces on the hillsides around the village to collect and store water. Animal husbandry was also expanding, with the domestication of cows, pigs, donkeys, and horses. Even previously dangerous animals were coerced into living with humans. There is evidence that the Nabateans kept dogs. As the great empires of Egypt, Greece, and Rome prospered, the Nabateans remained partially nomadic, driving their camel trains across the desert along the long-established trade routes between North Africa and India, and the great cities of the Mediterranean. But then, around 150 BCE, they decided to try something different. A few kilometers south of Beda, in a narrow gorge naturally formed in the soft sandstone rock, they built the city of Petra. Today, tourists stream through a magnificent passageway lined with buildings carved out of the desert rocks and known as the Sikh. But 2,000 years ago, the great and good of Mesopotamia, Rome, and Egypt would have walked this route into this jewel of late antiquity. The grandeur of the buildings is still overwhelming. They stand not as great architecture for their time, but as simply great, with no caveat. The most famous is called Al-Khazne, which means treasure box, because of the carved urn above the entrance, which Bedouin legend has it contains the treasure of a pharaoh. Monumental architecture is a common feature in the rise of human civilization. It is a statement of power and grandeur to impress and cow outsiders, but it also serves an internal purpose, cementing the position of the rulers in the hierarchy, and therefore providing the stability and security on which civilization rests. Over time, a virtuous circle emerges. The buildings help the civilization prosper, and the more prosperous the civilization, the more impressive the buildings become. Petra's wealth was derived from its location. Built within a natural gorge, the area is prone to flash floods, which provided precious water in a landscape that was arid by the time the Nabateans began to build. The city also sits at the fulcrum of the ancient nomadic trade routes along which wood, spices, incense, and dyes were transported from Africa and India and into the great Mediterranean civilization beyond. The appetite of the Greeks and Romans for exotic goods was insatiable. Black pepper alone fetched 40 times its own weight in gold in a Roman market. Petra, because of its strategic location, controlled all that trade and taxed it. Today, 1,500 years after the city was abandoned, it is still a magnificent sight, an overused but entirely accurate statement. Talk to an archaeologist, however, and you quickly realize how much more impressive it would have been in its heyday. The hillsides running down the valley from the carved tombs are scattered with rocks, but closer inspection reveals them to be bricks, the remains of houses, temples, and palaces. Everything from Al-Khazne to the houses would have been covered in white plaster and painted in bright colors which would have appeared resplendent against the monochrome desert sands. To build on this scale required a huge labor force. Petra was home to at least 30,000 people living in a few square kilometers of desert. Such a population density required technological innovation on a metropolitan scale, and the Nabateans, perhaps more than any other civilization in antiquity, were masters of fluid engineering. Virtually every drop of rainwater that fell on the surrounding hillsides was captured in grooves and stored in giant reservoirs and cisterns. They were better at plumbing than the Romans, who employed the Petran engineers in Rome. Petra had the world's first pressurized water system, which could deliver 12 million gallons of water a day into the city. Outside the city, the irrigation system continued out into the surrounding fields, lining the hillsides in still visible terraces. The Nabateans didn't simply build a city, they terraformed a landscape. I stood and imagined the ancient valley views with some awe. The mountain slopes would have been green with maize, barley, pulses, and vineyards. A desert turned green and feeding this grandest of desert civilizations for 6 centuries. Whenever I see the ruins of Petra, Rome, Athens, or Cairo, I wonder what Earth would be like today if the great civilizations of antiquity had not fallen. I blame the philosophers for not discovering the scientific method earlier and inventing the electric motor. How hard can it be? Agriculture, then, was fundamentally important to the rise of civilization because it enabled large numbers of people to live in one place and gave them access to resources and time which would have been unavailable to hunter-gatherers. With resources and time comes the division of labor, freeing up a small but important subset of individuals to engage in pursuits other than those necessary for immediate survival. Farmers, stonemasons, priests, soldiers, administrators, and artisans emerge, together with a ruling class who begin to direct the construction of monumental architecture, partly for their own selfish ends, and cities like Petra become possible. Petra was a relative latecomer in the emergence of the cities and civilizations of antiquity. The first great ancient civilization, the Old Kingdom of Egypt, arose around 2600 BCE along the fertile and farmed banks of the Nile, and precisely the same pattern of agriculture, followed by social stratification, ritual, and monumental architecture, can be seen. Present also in the Old Kingdom, and possibly developed there, was the one final vitally important innovation we will soon discuss: the written word. It all seemed so simple when written down on a piece of paper. The BBC prepares something known as a call sheet, which tells a film crew everything they need to know about a trip. Call sheets are very neat. All the timings work beautifully, carefully documenting flights, ground transfers to locations, and filming and rest periods, all of course in accordance with health and safety regulations and all that. Things never quite work out the way they're envisaged back in the office, of course. But filming the return of the Expedition 38 crew from the International Space Station to the Kazakh Steppe in March 2014 was the wildest adventure I've experienced. The call sheet said that we would fly into Astana on the 8th of March, arriving at 1 a.m. on the 9th into our hotel. After a leisurely breakfast at 9 a.m., we drive to a city called Karaganda, which has a spectacular statue of Yuri Gagarin in the town square. There we'd meet up with our drivers, who, embedded with Roscosmos, the Russian space agency, would drive us out to the landing site the following morning, arriving in time for a hot meal and a good rest on the steppe, ready to film the landing on the morning of the 11th, after, of course, a hot breakfast. We'd then drive back to the airport, hop on a flight, and be home in time for lunch on the 12th. A doddle. Bollocks. The steppe of central Kazakhstan in March is a featureless frozen wilderness covering around 800,000 square kilometers of the country's interior. There are no towns and few roads, just tufts of stunted brown grass and snow fading into an ice-grey leaden sky. In March 2014, temperatures were unseasonably cold, falling below -20 degrees C at night, and it was snowing. Our team had standard 4x4 vehicles, which got stuck in the snow by mid-afternoon the day before the landing, even though we'd set off 3 hours earlier than the 6 a.m. officially sanctioned health and safety call time because of the weather. This was problematic because our 8-man spaceman film was constructed carefully around this moment, the return of 3 human beings from space. Over vodka, cold meat, and bread, we discussed our options. We'd been helped along the snowy roads by a Russian team from the Siberian city of Tobolsk in 2 spectacular 6-wheel drive vehicles hand-built by a company called Petrovich. Tobolsk is best known for being the place dissidents were sent during the Soviet era. Tsar Nicholas II and his family enjoyed the Tobolskian hospitality for a year before being transported to Ekaterinburg to be shot. Mendeleev, the inventor of the periodic table, was born there, but so was Rasputin. It's a tough place, and they know how to build tough vehicles. Our guide from Roscosmos managed to radio the Petrovich team, and they agreed that if we could catch them up in the frozen wilderness, they could take 2 of us out to the landing site. The cameraman and I jumped aboard a pair of snowmobiles and headed out into the rapidly dimming late afternoon twilight in search of the men from Siberia. If we hadn't found them, then presumably you wouldn't be reading this. But we did. It was a difficult decision to jump on the snowmobiles. We didn't have a satellite phone because they are illegal in Kazakhstan, and nobody spoke English, so we couldn't quite assess the level of difficulty associated with finding these 2 Siberian needles in a Kazakh steppe. And we didn't know who the Siberians actually were. It seemed that they were freelancers, hired to take photographs and broadcast live television pictures back from the landing site for the Russian Space Agency. We also had to decide whether we could make the film with only 2 people. Much as I spend a lot of time dreaming about jettisoning directors, producers and executives, there is a reason why we usually take a crew of 6. Sound is particularly important. You don't really miss the sound man until he's not there. Our sound man on the series is called Andy, but we always called him Sound Man. There are too many other things to remember. As it turned out, the Petrovich crew were a hospitable and professional bunch. Although their willingness to spend many days out in the wilderness waiting for the Soyuz, they'd driven down from Siberia and were in no hurry to get home, played on our minds. Approaching midnight on the night before the landing, we received a message from Roscosmos that the landing might be postponed due to the poor weather, and the decision was made to camp out on the steppe and wait. In the distance, we could make out a small group of farm buildings through the snow, and we headed towards them. In broken English, one of the crew told us that it is a Kazakh tradition to welcome travelers into your home at any time of the day or night and offer them food. And so we found ourselves inside a farmhouse that appeared to have heated walls and resembled the inside of an oven, eating a feast of jam, bread, assorted sweets and horse, all washed down with vodka, which the Petrovich crew carried in large crates alongside their satellite broadcasting hardware. It was unforgettable. Human Universe was filmed as a love letter to the human race, and time and again when I found myself immersed unexpectedly in a culture, I've been reminded about why it is appropriate to want to write one. At 4 a.m., soaked in vodka, the call came through. Commander Oleg Kotov, Sergei Ryazansky and Mike Hopkins had climbed aboard the Soyuz and were preparing to depart the International Space Station. I was elated because I genuinely thought the landing would be called off, and I had no idea what that would have meant other than waiting for the storms to clear on the steppe. At 6:02 Kazakh time, the Soyuz TMA-10M, the 199th Soyuz to fly since 1967, undocked from the ISS. This is the point of no return except in an emergency. Just 2 hours and 28 minutes later, it fired its engine for a pre-programmed burn of 4 minutes and 44 seconds. This reduced the spacecraft's velocity by 128 meters per second relative to the station, which in its orbit that day was traveling at 7,358 meters per second. That number is not arbitrary. It is given by a simple equation which can be derived easily from Newton's law of gravitation and his second law of motion, F equals ma. We leave it as an exercise for the listener to show that these 2 laws of nature can be rearranged to show that the velocity v of any object in a circular orbit a distance r from the center of the Earth, mass me, is given by v equals the square root of gme over r. To derive this result, you need to know that the force required to maintain an object of mass m in a circular orbit is mv squared over r. The space station orbits at an altitude of between 330 and 445 kilometers. Let's choose the middle ground of 387 kilometers. This is a back-of-the-envelope calculation. Estimate is the name of the game, as my old physics teacher used to say at school. The radius of the Earth is 6,378 kilometers, and the mass of the Earth is 5.97219 times 10 to the 24 kilograms. Newton's gravitational constant is 6.67384 times 10 to the minus 11 meters cubed per kilogram per second squared. Do the calculation yourself. Maths is good for you. With these numbers, v is approximately 7,675 meters per second, which is close enough. The difference is due to the precise altitude of the ISS that day. I love doing little calculations like this. They reveal the immense power of mathematical physics. This really is the orbital velocity of the International Space Station, and it is forced to be so by laws of nature first published by Isaac Newton in 1687. If you've never done a calculation like this before, you should feel elated. The biologist Edward O. Wilson called this feeling the Ionian enchantment, a poetic term he introduced to describe the realization, credited to Thales of Miletus in 600 BCE, that the natural world is orderly and simple and can be described with great economy by a small set of laws. It is nothing short of wonderful that we can calculate the orbital velocity of the International Space Station together in a few lines of a popular book, and this points us neatly towards the story of the last great innovation in the ascent from ape-man to spaceman, the written word. But after all, who knows and who can say whence it all came and how creation happened? The gods themselves are later than creation, so who knows truly whence it has arisen? Ancient Brahmin verse. A neat piece of logic. There is tension at the interface between science and language. Language is concerned with human experience. Everyone understands what's meant by questions such as, "Why are you late?" "I'm late because my alarm clock didn't go off." But this answer is incomplete and could be followed by a series of further questions in an attempt to establish precisely why. Why didn't it go off? Because it's broken. Why is it broken? Because a piece of solder melted on the circuit board. Why did the solder melt? Because it got hot. Why did it get hot? Because it's August and my room is hot. Why is it hot in August? Because of the details of the Earth's orbit around the Sun. Why does the Earth orbit the Sun? Because of the action of the gravitational force. Why is there a gravitational force? I don't know. All scientific why questions end with "I don't know" if you keep pushing far enough, because our scientific understanding of the universe is not complete. The most fundamental description we have for anything comes down to a set of theories describing the smallest known building blocks of the universe and the forces of nature that allow them to interact with each other. These theories are known as laws of physics, and when we ask about the origin of these laws, the answer is we don't know. This is because in the Big Bang model, our understanding of physics before 10 to the minus 43 seconds after the origin of the visible universe is virtually non-existent, and the origin of the laws lies at some point before that. The laws themselves are later than creation, and who knows truly whence it has arisen. Our best theory of space and time, Einstein's general theory of relativity, no longer applies at the earliest times. The conditions were so extreme in those first moments, known as the Planck epoch, that some kind of quantum theory of gravity, which we do not possess, will be needed to describe it. The universe is now 13.798 plus or minus 0.037 billion years old, according to our current best measurements and theoretical understanding, and has been gently expanding and cooling ever since the Big Bang. The universe appears to be gently increasing its expansion rate, and approximately 68% of the energy in the universe is associated with this sedate acceleration. The energy has a name, dark energy, but its nature remains one of the great unsolved challenges for 21st century theoretical physics. Of the 32% that remains, approximately 27% is in a form of matter known as dark matter. The nature of this is also unknown, but it probably comes in the form of as yet undiscovered subatomic particles. The remaining 5% makes up the stars, planets, and galaxies we see in the night sky, and of course human beings. The part of the universe we can see is around 93 billion light-years across, and has reached a relatively chilly temperature of 2.72548 plus or minus 0.00057 Kelvin due to its expansion. The question of the origin of the universe is an old one in philosophy, and often framed in terms of the first cause argument. Leibniz is associated with a proof of the existence of God in this context, which goes something like this. Everything that exists must have either an external cause or must be eternal. If there are eternal things, then they must necessarily exist because they don't have a cause. Since the universe exists and is not eternal, it must have an external cause, and to avoid infinite regress, that cause must be an eternal and necessary thing, which we'll call God. This is quite a neat piece of logic, obviously because Leibniz wasn't an idiot. I don't consider such questions to fall necessarily within the domain of science. Rather, science is concerned with answering more modest questions, and this is the reason for its power and success. The goal of science is to explain the observed features of the natural world. By explain, I mean build theories that make predictions that are in accord with observation. This is a humble idea. There is no a priori aim to discover the reason for the existence of our universe or to build theories of everything. Science proceeds in tiny steps, attempting to find explanations for the blue sky, the green leaves of plants, or the stretched, red-shifted light from distant galaxies. Sometimes those tiny steps build up to something rather grand, like a measurement of the age of the observable universe, but that's not what anyone set out to do. This is why science is more successful than any other form of human thought when applied to questions within its domain, which is the explanation of the natural world. It starts small and works its way slowly and methodically forwards, deepening our understanding in careful increments. Our chapter title, Why Are We Here?, might therefore appear to be unanswerable by science. It's too grand a question. But that may no longer be the case, because the careful steps are taking science into this territory, and the scientific language is now in place to at least address the question, what happened before the Big Bang? This is clearly a prerequisite for being able to make any meaningful attempt to address the reasons for our existence, although it is surely not sufficient. Immediately, I have to explain a semantic distinction before 1,000 philosophers throw their togas aside and prepare to engage in a naked yet civilized and eloquent battle of ideas. I am defining the term Big Bang as the astronomer Fred Hoyle originally introduced it into physics in 1949. It is to be understood as the beginning of the hot, dense state in which our observable universe once existed. Conventional cosmological theory, as described in Chapter 1, traces the evolution of the universe backwards in time, with conditions getting hotter and hotter and denser until the point where we are unsure of the correct rules of physics. Currently, this is earlier than approximately 10 to the minus 10 seconds, which is associated with the current power of the Large Hadron Collider. If the universe existed in some other form before the hot, dense state came into existence 13.798 billion years ago, then that's what I'm referring to as the time before the Big Bang. Science might accidentally wander into Leibniz's territory if, for example, this time before the Big Bang were discovered to be infinite, or that the state before the Big Bang was logically necessary and describable by current or yet-to-be-discovered laws of physics. Such a theory would also have to explain precisely all the properties of the universe we see today. From a scientific perspective, of course, we don't care about Leibniz. It is not the role of science to prove or disprove the existence of God. Rather, we are only interested in taking our careful steps backwards in time, as far as the evidence and theoretical understanding allow. The exciting thing is that developments in cosmology since the 1980s now point quite firmly towards the existence of a state before the Big Bang, as defined above, and that is primarily what this chapter is about. This chapter is also about you. I suspect most of us have mused about the question, why are we here? For some, the question and answer may be absolutely central to their lives. For others, myself included, it's something I used to think about on a hillside, desolate, beside a punctured bicycle, whilst wearing a second-hand overcoat I bought from Affleck's Palace. But my existentialism faded with my hair. Having said that, a little existentialism, like the Manchester rain, never did anyone any harm. So let's place ourselves at the centre of things for a while, and explore the immense contingency of our personal existence, as a warm-up for the much deeper problem of the origin of the universe itself. It's a pretty deep chapter, this, so put on unknown pleasures, grab a bottle of cheap cider, and let's get going. If in a moment of solipsism you decide to work out the odds of your own existence, you might come to the conclusion that you are astonishingly special. You began as a particular egg inside your mother, fertilized by a particular sperm from your father. There were 180 million sperm around that day, each with a different genetic code, only one of which became you in combination with one of your mother's million or so genetically unique eggs. So without going any further, you might feel lucky. If you chose to carry on, you might factor in the odds of your parents having sex on that particular day, because sperm are constantly manufactured. Then there are the odds of them meeting at all, and the odds of them being them. And whilst we're picking up increasing armfuls of odds at the 1 in 100 million level, recall from Chapter 1 that there exists an unbroken line of your ancestors stretching back over 3.8 billion years to Luca, the last universal common ancestor. If any one of those living things had died before it reproduced, you wouldn't exist. That's pretty lucky, but also completely devoid of any meaning at all. Yes, the odds of you existing are almost but not quite zero, but given the existence of the human race and a mechanism for procreation, someone has to be born. So whilst the probability of any given individual existing is tiny, it is inevitable that new babies will be born every day. Seen in this light, you are not special, and your existence in the grand scheme of things is entirely understandable. Time for Joy Division Insider. This demolition of your individual self-importance relied on the fact that a mechanism exists for the inevitable production of large numbers of human beings, given the important precondition that humans already exist. We've explored the road to human existence at length in the book already, and argued that complex multicellular life and intelligence at or beyond the level of humans may be rare in our universe. It's also clear that there are fundamental properties of the universe itself that are necessary for the existence of any form of life. The universe must live long enough and have the right properties for stars to form, and those stars must be capable of producing the chemical elements out of which living things are made, carbon being the most important. What do we mean by properties? We're back to the nature of the laws of physics once again, because they describe the behavior of matter and forces at the most fundamental level. The laws restrict the possible physical structures that are allowed to appear in the universe. And stars, planets, and human beings are all examples of such possible physical structures. Questions now naturally arise, more modest perhaps than our grand "why are we here" puzzle, but more amenable to scientific inquiry. How do the laws of nature allow for human beings to exist? And by how much could those laws vary before life could no longer exist in the universe? Let us begin in the spirit of taking small steps, with a brief summary of the known fundamental laws of nature. Attempting to describe the laws that govern the existence of everything from galaxies to human beings in a single paragraph of a book of a TV series might seem overly ambitious. It is at one level, otherwise everyone would complete physics, chemistry, and biology degree courses in an afternoon. What we can do, however, is to outline the known fundamental laws in a concise and accurate way. So let us do that. There are 12 known particles of matter. They are arranged into 3 families, or generations. You are made out of particles in the first generation alone. Up quarks and down quarks bind together to make protons and neutrons, which in turn bind together to form your atomic nuclei. Your atoms are composed of electrons bound to those nuclei. Molecules, such as water and DNA, are built up out of collections of atoms bound together. That's all there is to you. 3 fundamental particles arranged into patterns. Particles called gauge bosons carry the forces of nature. There are 4 known fundamental forces: the strong and weak nuclear forces, electromagnetism, and gravity. To see how this all works, let's focus on the familiar electromagnetic force. Imagine an electron bound to the atomic nucleus of one of your atoms. How does that binding happen? The most fundamental description we have is that the electron can emit a photon, which you can think of as a particle of light. That photon can be absorbed by one of the quarks inside the nucleus, and this emission and absorption acts to assert a force between the electron and the quark. There is a vast number of ways in which the electrons and the quarks inside the nucleus can emit and absorb photons, and these all combine to keep the electron firmly glued to the nucleus. A similar picture can be applied to the quarks themselves. They also interact via the strong nuclear force by emitting and absorbing force-carrying particles called gluons. The strong nuclear force is the strongest known force, the clue is in the name, and binds the quarks together very tightly indeed. This is why the nucleus is significantly smaller and denser than the atom. Only quarks and gluons feel the strong nuclear force. Finally, there is the weak nuclear force. This is mediated by the exchange of the W and Z bosons. All known particles of matter feel the weak nuclear force, but it is extremely weak relative to the other two, which is why its action is unfamiliar, but not unimportant. The sun would not shine without the weak nuclear force, which allows protons to convert into neutrons, or more precisely, up quarks into down quarks, which has the same result. This is the first step in the nuclear burning of hydrogen into helium, the source of the sun's energy. During the conversion of a proton into a neutron, an anti-electron neutrino is produced along with an electron. The neutrino is the remaining particle in the first generation we haven't discussed yet. Because neutrinos only interact via the weak nuclear force, we are oblivious to them in everyday life. This is fortunate because there are approximately 60 billion per square centimetre per second passing through your head from the nuclear reactions in the sun. If the weak force were a little stronger, you'd get a hell of a headache. Actually, you wouldn't, because you wouldn't exist. And this foreshadows the subject of the fine-tuning of the laws of nature we will undertake later in this chapter. The one remaining type of particle is the Higgs boson. Empty space isn't empty, but is jammed full of Higgs particles. All the known particles, apart from the photon and the gluons, which are massless, interact with the Higgs particles, zigzagging through space and acquiring mass in the process. This is the counterintuitive picture that was confirmed by the discovery of the Higgs boson at CERN's Large Hadron Collider in 2012. Two further generations of matter particles have been discovered. They are identical to the first generation, except that the particles are more massive because they interact with Higgs particles more strongly. The muon, for example, is a more massive version of the familiar electron. The reason for their existence is unknown. This is all there is in terms of the description of the fundamental ingredients of the universe. There are almost certainly other particles out there somewhere. The dark matter that dominates over normal matter in the universe by a factor of 5 to 1 is probably in the form of a new type of particle which we may discover at the Large Hadron Collider, or a future particle accelerator. The evidence for dark matter is very strong, and comes from astronomical observations of galaxy rotation speeds, galaxy formation models, and the cosmic microwave background radiation that we met in Chapter 1 and will meet again later in this chapter. But because we don't know what form the dark matter takes, we are not able to incorporate it into our list. The mathematical framework used to describe all the known particles and forces other than gravity is known as quantum field theory. It's a series of rules that allows the probability of any particular process occurring to be calculated. The whole thing can be described in one single equation, known as the Standard Model Lagrangian. Here it is. L equals -1/4 W mu nu W superscript mu nu, -1/4 B mu nu B superscript mu nu, -1/4 G mu nu G superscript mu nu, plus psi bar j gamma mu bracket I delta mu minus G tau j dot W mu minus G dash yj B mu minus G s tj dot G mu bracket psi j, plus d mu phi squared plus mu squared phi squared minus lambda phi to the fourth, minus bracket yj psi bar jl phi psi jr plus y dash j psi bar jl phi c psi jr plus conjugate, close bracket. It takes a lot of work to use this piece of mathematics to make predictions, but the predictions are spectacularly accurate and agree with every experimental measurement ever made in laboratories on Earth. This equation even predicted the existence of the Higgs particle. That's how good it is. It probably looks like a set of squiggles unless you're a professional physicist, but in fact it isn't too difficult to interpret, so let's just dig a little deeper. The 12 matter particles are all hidden away in the symbol psi-j. The Standard Model is a quantum field theory, because particles are represented by objects known as quantum fields. There's an electron field, an up quark field, a Higgs field, and so on. The particles themselves can be thought of as localized vibrations in these fields, which span the whole of space. Fields will be important to us later, when we'll want to think about a certain type of field that may have appeared in the very early universe, known as a scalar field. The Higgs field is an example of a scalar field. The mathematical terms between the two psi-j's on the second line describe the forces and how they cause the particles to interact. The forces are also represented by quantum fields. The term -GSTJ.G mu, for example, describes the gluon field that allows the quarks in the psi-j terms to bind together into protons and neutrons. The term GS is known as the strong coupling constant. It's a fundamental property of our universe that encodes the strength of the strong nuclear force. Each of the forces has one of these coupling constants. We'll want to discuss these coupling constants later because they define what our universe is like and what is allowed to exist within it. The last two lines deal with the Higgs boson. The strength of the interaction between a matter particle and the Higgs field is contained in the YJ terms, which are known as Yukawa couplings. These must be inserted to produce the observed masses of the particles of matter. That's pretty much it. Here ends our crash course on particle physics. The central point is that there exists a remarkably economical description of everything other than gravity, and it is contained within the Standard Model. We considered the gravitational force in some detail in Chapter 1. It's described by Einstein's theory of general relativity, which is what physicists call a classical theory. There are no force-carrying particles in Einstein's theory. Instead, the force is described in terms of the curvature of space-time by matter and energy, and the response of particles to that curvature. A quantum theory of gravity, which we have already noted will be necessary to describe the first fleeting moments in the history of the universe, would involve the exchange of particles known as gravitons, but as yet nobody's worked out how to construct such a description. This is why Einstein's theory remains the only fundamental non-quantum theory we have. For completeness, let's refresh our memory of Einstein's theory of general relativity. G mu nu equals 8 pi gt mu nu. General relativity, like the Standard Model, contains a coupling constant encoding the measured strength of gravity, G, Newton's gravitational constant. The amount of dark energy is inserted by hand, in accord with observations, as was the case for the strengths of the forces and the masses of the particles in the Standard Model. General relativity and the Standard Model are the rules of the game. They contain all our knowledge of the way that nature behaves at the most fundamental level. They also contain almost all the properties of our universe that we think of as fundamental. The speed of light, the strength of the forces, the masses of the particles, encoded as the strength of their interaction with the Higgs bosons via the Yukawa couplings, and the amount of dark energy are all in these equations. In principle, any known physical process can be described by them. This is the current state of the art, but it doesn't mean that we know how everything works and can all retire by a long shot or a well-timed cover drive. Most games are skin deep, but cricket goes to the bone. John Arlott and Fred Truman. I timed a cover drive properly once when I was 14 years old playing at Hollingwood Cricket Club near Oldham. Front foot, head in line with the ball, sweet sound of the middle, 4 runs. I know what I have to do, but I never did it quite as well again. Cricket is an art built on simple rules, first codified by the members of the Marylebone Cricket Club on the 30th of May 1788. A significant date in world history, according to historians with good taste. Those original laws still form the basis of the game today. There are 42 of them, and they define the framework within which each game evolves. Yet, despite the rigid framework, no two games are ever alike. The temperature and humidity of the air, a light scatter of dew on the grass, the height of grass on the wicket, and hundreds of other factors will subtly shift and change throughout the game. More importantly, the players and umpires are each complex biological systems whose behavior is far from predictable, with the exception of Geoffrey Boycott. The presence of so many variables makes the number of possible permutations effectively infinite, which is why cricket is the most interesting of human pursuits, excluding science, sex, and wine tasting. Knowledge of the laws is therefore insufficient to characterize the infinite magic of the game. This is also true for the universe. The laws of nature define the framework within which things happen, but do not ensure that everything that can happen will happen in a finite universe. That rather obscure finite caveat will be important for us later on. Virtually all of science beyond particle physics and theoretical cosmology is concerned with the complex outcomes allowed by the laws rather than the laws themselves. And in a certain sense, our solipsistic initial question, why are we here, is also a question about outcomes rather than laws. The answer to the question, why did England beat Australia in the Great Ashes series of 2005, is not to be found in the MCC rulebook. And similarly, the natural world that emerges from the Standard Model and general relativity cannot be understood simply by discovering the laws themselves. It's worth noting that the laws of nature were not written by the MCC, or even the committee of the Yorkshire County Cricket Club. We had to work them out by watching the game of the universe unfold, which makes their discovery even more wonderful. Imagine how many matches would have to be viewed in order to deduce the laws of cricket, including but not restricted to the Duckworth-Lewis method. The great achievement of 21st century science is that we've managed to work out the laws of nature by doing just this, observing many millions of complex outcomes and working out what the underlying laws are. The Standard Model, then, cannot be used to describe complex emergent systems such as living things. No biologist would attempt to understand the way that ATP is produced inside cells using the Standard Model Lagrangian, and no telecommunications engineer would use it to design an optical fiber. They wouldn't want to, even if they could. You wouldn't gain any insight into how a car engine works by starting off with a description of its constituent subatomic particles and their interactions. So whilst it's important that we have a detailed model of nature at the level of the known fundamental building blocks, we must also understand how the complexity we observe around us emerges from these simple laws, if we're to make progress with our difficult why question. On Monday the 27th of March 1905 at 8:30 a.m., William Jones arrived at Chapman's Oil and Colour Shop on Deptford High Street, ready for a day's work. Jones normally arrived a few minutes after the shop manager Thomas Farrow had raised the shutters. On this particular Monday, however, the shutters were down. Farrow lived with his wife Anne above the shop, but no matter how hard Jones knocked on their door, there was no response. This was a most unusual start to the day, and his concern increased when a glimpse through a window revealed chairs strewn across the floor of the normally tidy shop. Jones and another local resident forced the door, to be confronted by Farrow lying dead in a pool of blood. Anne had been similarly bludgeoned in her bed, although she clung to life for 4 more days without regaining consciousness. Such scenes were not uncommon in Edwardian London. The reason that this crime is of note is because it was the first in the world to use a new technology to catch and convict the killers. On an inner surface of the empty cash box, the police noticed a fingerprint. They already had a suspect, a local man named Alfred Stratton, who was arrested 3 days later along with his brother Albert. The Strattons' fingerprints were taken, and a positive match was made between the cash box print and Alfred Stratton's right thumb. Although fingerprints were never used before in a murder case, expert witnesses convinced the jury that the complex patterns of the cash box fingerprint could only belong to Alfred Stratton. The jury took just 2 hours to find the Stratton brothers guilty of murder, and the pair was sentenced to death by hanging, with justice swiftly dispatched on the 23rd of May. Take a look at your fingerprints now. There is seemingly endless complexity in the swirls and ridges. Since every human being carries different fingerprints on the hands and the soles of their feet, which aren't fingerprints but there isn't a word for them, the size of database required to characterize every human being's fingerprints would be colossal. One of the most important properties of nature, however, is that the blueprints for the construction of the natural world are far simpler than the natural world itself. In modern language, there is a tremendous amount of data compression going on. The instructions to create fingerprints are far simpler than the fingerprints themselves. And more than that, the same instructions run over and over again from slightly different starting points in the embryonic stage of our development always lead to different fingerprints. This behavior shouldn't come as a surprise. The sweep of desert dunes or the patterns in summer clouds are all described by a handful of simple laws governing how sand grains or water droplets behave when agitated by shifting air currents, buffeted by chaotic thermals and winds, and reordered by the action of the forces of nature. And yet from a simple recipe, complexity emerges. The quest to understand how the boundless variety of the natural world emerges from underlying simplicity has been a central theme in philosophical and scientific thought. Plato attempted to cast the world available to our senses as the distorted and imperfect shadow of an underlying reality of perfect forms accessible through reason alone. The modern expression of Plato's ethereal dualism was captured eloquently by Galileo 500 years ago. The book of nature is written in the language of mathematics. The challenge is not only to discern the underlying mathematical behavior of the world, but also to work back upwards along the chain of complexity, to explain how those forms that Plato would have defined as imperfect arise from the assumed lower-level perfection. A rather beautiful early example of this quest is provided by Galileo's illustrious contemporary, Johannes Kepler. A brief history of the snowflake. Johannes Kepler is rightly best known for his laws of planetary motion that paved the way for Newton to write Principia. Hidden within his illustrious CV, however, is a publication that had a rather more whimsical, earthbound ambition. 2 years after publishing the first part of Astronomia Nova in 1609, Kepler published a short 24-page paper entitled De Nive Sexangula, on the six-cornered snowflake. It is a beautiful example of a curious scientific mind at work. In the dark December of 1610, Kepler was walking across the Charles Bridge in Prague when a snowflake fell on the lapel of his coat. In the freezing night he stopped and wondered why this ephemeral sliver of ice possessed a six-sided structure, in common with all other snowflakes, notwithstanding their seemingly infinite variation. Others had noticed this symmetry before, but Kepler realized that the symmetry of a snowflake must be a reflection of the deeper natural processes that underlie its formation. Since it always happens when it begins to snow that the first particles of snow adopt the shape of small six-cornered stars, there must be a particular cause, wrote Kepler. For if it happened by chance, why would they always fall with 6 corners and not with 5 or 7? Kepler hypothesized that this symmetry must be due to the nature of the fundamental building blocks of snowflakes. This stacking of frozen globules, as he referred to it, must be the most efficient way of building a snowflake from the smallest natural unit of a liquid like water. To my mind, this is a leap of genius, and a tremendously modern way of thinking about physics. The study of symmetry in nature lies at the very heart of the Standard Model, and abstract symmetries known as gauge symmetries are now known to be the origin of the forces of nature. This is why the force-carrying particles in the Standard Model are known as gauge bosons. Kepler was searching for the atomic structure of snow before we knew atoms existed, motivated by the observation of a symmetry in nature, the six-sided shape of all snowflakes. The inspiration for this idea, which is way ahead of its time, came from a peculiar source. In the years leading up to the publication of De Nive Sexangula, Kepler had been in communication with Thomas Harriot, an English mathematician and explorer. Amongst multiple claims to fame, Harriot was the navigator on one of Sir Walter Raleigh's voyages to the New World, and had been asked to solve a seemingly simple mathematical problem. Raleigh wanted to know how best to stack cannonballs to make the most efficient use of the limited space on the ship's deck. Harriot was driven to explore the mathematical principles of sphere packing, which in turn led him to develop an embryonic model of atomic theory and inspire Kepler's consideration of the structure of snowflakes. Kepler imagined replacing cannonballs with globules of ice, and supposed that the most efficient arrangement creating the greatest density of globules was the six-sided hexagonal form he observed in the snowflake on his shoulder. Kepler also observed hexagonal structures across the natural world, from beehives to pomegranates and snowflakes, and presumed that there must be some deeper reason for its ubiquity. Hexagonal packing, as Kepler referred to it, must be the tightest possible, so that in no other arrangement could more pellets be stuffed into the same container. This became known as the Kepler conjecture. It took almost 400 years to prove Kepler's conjecture, and this required the help of a 1990s supercomputer. Despite the time lag, Kepler's work had a more immediate impact, inspiring the beginnings of modern crystallography that led eventually to the discovery of the structure of DNA. What a lovely example of serendipity coupled with curiosity and a sprinkling of genius. From cannonballs to snowflakes to the code of life. As for Kepler's original thought on that frozen bridge, he never found the connection between the underlying structure of his ice globules and the hexagonal symmetry of snowflakes. Even though he realized that the regular patterns must reveal something about the shape of the building blocks of snowflakes and the details of the packing, he couldn't explain the ornate complexity or the flatness of the structure. Instead, he acknowledged his failure with the good grace of a true scientist. "I have knocked on the doors of chemistry," he writes at the end of his paper, "and seeing how much remains to be said on this subject before we know the cause, I would rather hear what you think, my most ingenious man, than wear myself out with further discussion." 3.5 centuries later, Japanese physicist Yukichiro Nakayara made the first artificial snowflakes in a laboratory. Writing in 1954, he describes a process that begins not with the snowflake itself, but with smaller substructures called snow crystals, which are in turn built up from collections of ice crystals, the globules Kepler was searching for. The hexagonal packing that Kepler suspected to be the origin of the snowflake symmetry begins with the formation of these ice crystals, when water molecules link together in a hexagonal structure via hydrogen bonds. Hydrogen bonding occurs because of the structure of the water molecules themselves, with a greedy oxygen atom hungry for electrons grabbing them off two hydrogen atoms, forming covalent bonds that lock the H2O molecules together, leaving a residual positive electrical charge in the vicinity of the two protons and a negative charge in the vicinity of the oxygen. This slight separation of charge in the water molecules allows them to bind together into larger structures through the mutual attraction and repulsion of the electrical charges, just as an electron is bound into its position around an atomic nucleus. The entire configuration, including the structure of the oxygen nucleus and the single protons that comprise the hydrogen nuclei, can be predicted in principle by the standard model of particle physics. Yet the details of any particular snowflake are beyond computation, because the seemingly infinite variety reflects the precise history of the snowflake itself. Once ice crystals form as agglomerations of water molecules held together by hydrogen bonds, they cluster around dust particles in the air, building on their underlying hexagonal symmetry to form larger snow crystals. As the crystals begin the long journey down to Earth, they join in ever larger, more complex combinations, shaped by endless variations of air temperature, wind patterns, and humidity, into myriad unique forms. The symmetry is all that remains of the simplicity, and it takes a careful and patient eye to see the endless variation for what it is, a reflection of the complex history of the snowflake, convoluted with the underlying simplicity of the laws of nature. The most vivid example of emergent complexity, and the closest to our hearts, is life. As we discussed in Chapter 2, the origin of life on Earth has a sense of inevitability about it, because its basic processes are chemical reactions that will proceed given the right conditions. Those conditions were present in the oceans of Earth 3.8 billion years ago, possibly earlier, and they led to the emergence of single-celled organisms. The fateful encounter which produced the eukaryotic cell around 2 billion years ago looks rather more like blind chance, but it happened here and laid the foundations for the Cambrian explosion 530 million years ago. There is a bit of hand-waving going on here, though, and to make a more persuasive case that all the complexity of Darwin's endless forms most beautiful can at least in principle emerge from simple underlying laws, one more example is in order. Perhaps the most beautiful manifestation of the artful complexity of nature can be found in the spots, stripes, and patterns on the coats and skin of living things. Emergent pattern writ large across venomous striped surgeonfish, emperor angelfish, zebra swallow-tailed butterflies, and the big cats of Africa and Asia. Everyone agrees that these patterns evolved as a result of natural selection of one form or another, and the raw material for the variation was provided by random mutations in the genetic code. But a very challenging scientific question of fundamental importance in modern biology is precisely how patterns such as these appear. How the leopard got its spots. Zebra moved away to some little thorn bushes where the sunlight fell all stripy, and the giraffe moved off to some tallish trees where the shadows fell all blotchy. "Now watch," said the zebra and the giraffe. "This is the way it's done. 1, 2, 3, and where's your breakfast?" All they could see were stripy shadows and blotched shadows in the forest, but never a sign of zebra and giraffe. That's a trick worth learning. Take a lesson from it, leopard. Then the Ethiopian put his 5 fingers close together and pressed them all over the leopard, and wherever the 5 fingers touched, they left 5 black marks all close together. Rudyard Kipling's Just So story, How the Leopard Got His Spots, tells the story of an Ethiopian man and a leopard. They went hunting together, but one day the man noticed that the leopard wasn't very successful. The reason, he deduced, was that the leopard had a plain, sandy coat, whereas all the other animals had camouflage. "That's a trick worth learning, leopard," he said, taking his fingers and thumb and pressing them into the leopard's coat to give it the distinctive 5-pointed pattern. If you don't believe in evolution by natural selection, this is the most plausible theory open to you. If you do, then what remains is to identify the mechanism by which the pattern is formed. The answer might appear to be solely a matter of genetics, but genes are not the whole story. It would take a terrific amount of information to instruct every single cell to color itself according to its position on the leopard's skin, and this is indeed not what is done. Nature is frugal and deploys a much more efficient mechanism for producing camouflage patterns. As with so many things in this book, I get to say yet again that this is an active area of research, and therefore exciting. The reason for the attention is that camouflage patterns on the skin self-organize during the development of the embryo, and embryonic development is of course fundamental to an understanding of biology. In the case of the leopard, it is thought, though not proven, that the camouflage is an example of a Turing pattern, named after the great Bletchley Park codebreaker and mathematician Alan Turing. In 1952, Turing became interested in morphogenesis, the process by which an animal develops its shape and patterning. He was particularly interested in the mathematics behind regularly repeating patterns in nature, such as the Fibonacci numbers and golden ratio in the leaf arrangements of plants and the scales of pineapples, and the appearance of camouflage patterns such as the tiger's stripes and the leopard's spots. Turing's influential and groundbreaking paper, The Chemical Basis of Morphogenesis, published in March 1952, begins with a simple statement. It is suggested that a system of chemical substances called morphogens, reacting together and diffusing through a tissue, is adequate to account for the main phenomena of morphogenesis. These systems are known as reaction-diffusion systems, and they can produce patterns from a featureless initial mixture if the two reactants diffuse at different speeds. There's a nice analogy that describes how such a system can work. This analogy was published by J.D. Murray in Notices of the AMS, June-July 2012. Why are there no three-headed monsters? Mathematical modeling in biology. Imagine a dry field full of grasshoppers. They are strange grasshoppers because when they get warm, they sweat, generating a large amount of moisture. Now imagine that the field is set alight in several different places. The flames will spread at some fixed speed, and if there were no grasshoppers, the whole field would be charred. As the flames approach the grasshoppers, however, they will start to sweat, dampening the grass behind them and inhibiting the flames as they hop away ahead of the approaching flames. Depending on the different parameters, including the different speeds of the flames and the grasshoppers and the amount of sweat necessary to quell the advancing flames, a Turing pattern can be formed, with areas of charred grass and green areas where the inhibiting grasshoppers prevented the fire from taking hold. It is thought that the leopard gets its spots in this way during embryonic development. An activator chemical, fire, spreads through the skin and stimulates the production of the dark pigmented spots, charred grass, but is inhibited by another chemical, sweating grasshoppers, spreading with a higher diffusion rate. The precise pattern produced depends on the constants of nature of the system, such as the speeds at which the chemicals diffuse, and on what a mathematician would call the boundary conditions, the size and geometry of the grassy field in our analogy. In embryonic development, it is the size and shape of the embryo when the reaction diffusion begins that determines the type of pattern produced. A long and thin domain produces stripes. A domain that is too small or too large produces uniform color. In between can be found the distinctive coat patterns of cows, giraffe, cheetah, and of course the leopard. Computer simulations of Turing patterns have been remarkably successful, not only in describing the generic features, particularly of mammalian coats, but also of some of the interesting details seen in nature. For example, the mathematical models predict that it is possible for spotted animals to have striped tails, as cheetahs do, but not for striped animals to have spotted tails, and indeed no such examples exist. Kepler's snowflakes and the leopard's spots are two picturesque examples of emergent complexity, the appearance of intricate, ordered patterns from the action of simple underlying laws. Nature contains systems far more complex than these, of course, you being a case in point. But to return to the question at the beginning of our solipsistic meander, the reason that you exist, given the laws of nature, is that you are allowed to. Just as all snowflakes and all leopards' coats are unique in detail because of their individual formation histories, so you are unique because no two human beings share a common history. But we wouldn't read any deep meaning into the existence of one particular snowflake in a snowstorm, and the same is true for you. Our focus should therefore shift from trying to explain the appearance of humans, or our planet, or even our galaxy, to a rather deeper question: the origin of the whole framework, of space-time and the laws that govern it, and the allowed structures within it. What properties of the laws themselves are essential for galaxies, planets, and human beings to exist? After all, as we've noted, the laws might be mathematically elegant and economical, but they do contain a whole host of seemingly randomly chosen numbers discovered by experimental observation and with no known rhyme or reason to them. The constants of nature, such as the strength of the forces, the masses of the particles, and the amount of dark energy in the universe. How dependent is our existence on these fundamental numbers? Our universe appears to be made for us. We live on a perfect planet, orbiting around a perfect star. This is, of course, content-free whimsy. The argument is backwards. We have to be a perfect fit for the planet because we evolved on it. But there are interesting questions when we look deeper into the laws of nature and ask what properties they must have to support a life in the universe. Take the existence of stars, for example. Stars like the Sun burn hydrogen into helium in their cores. This process involves all four forces of nature working together. Gravity kicks it all off by causing clouds of dust and gas to collapse. As the clouds collapse, they get denser and hotter until the conditions are just right for nuclear fusion to occur. Fusion starts by turning protons into neutrons through the action of the weak nuclear force. The strong nuclear force binds the protons and neutrons together into a helium nucleus, which in itself exists on account of the delicate balance between the strong nuclear force holding it together and the electromagnetic force trying to blow it apart because of electrically charged protons. When stars run out of hydrogen fuel, they perform another series of equally precarious nuclear reactions to build carbon, oxygen, and the other heavy elements essential for the existence of life. What happens if the strength of these forces, those fundamental constants of nature we met earlier in the chapter, are varied a bit? There are many examples of apparent fine-tuning in nature. If protons were 0.2% more massive, then they would be unstable and decay into neutrons. That would certainly put an end to life in the universe because there would be no atoms. The proton mass is ultimately set by the details of the strong and electromagnetic forces and by the masses of the constituent quarks, which are set by the Yukawa couplings to the Higgs field in the Standard Model. There really isn't much freedom at all. The mother of all fine tunes, however, is the value of our old friend dark energy, the thing that is causing our universe to gently accelerate in its expansion. Although dark energy contributes 68% of the energy density of the universe, the amount of dark energy in a given volume of space is actually small, very small, 10 to the minus 27 kilograms per cubic meter to be precise. The point is that every cubic meter of our universe has this amount of dark energy in it, and that adds up. Explaining why dark energy has this small but non-zero value is one of the great problems in cosmology, not least because if a particle physicist sits down with a quantum field theory and decides to calculate how big it should be, it turns out that it would be more naturally of the order of 10 to the 97 kilograms per cubic meter. That's a lot bigger than 10 to the minus 27 kilograms per cubic meter. Over a million times bigger, in fact. That's embarrassing for the particle physicists, of course, but from the perspective of fine-tuning, it's even worse. If the value of dark energy were only 50 times larger than it is in our universe, rather than somewhere else in this immensely large theoretical range, then it would have become dominant in the universe around 1 billion years after the Big Bang, during the time that the first galaxies were forming. Because dark energy acts to accelerate the universe's expansion and dilute matter and dark matter, gravity would have lost the battle in such a universe, and no galaxies or stars or planets or life would exist. What could possibly account for this incredible piece of luck? It can't really be luck. The odds are too long by a Geoffrey Boycott innings. One possibility is that there is some as yet unknown physical law or symmetry that guarantees that the amount of dark energy will be very close to, but not quite, zero. This is certainly possible, and there are physicists who believe that this may be the case. The other possibility, which was raised by one of the fathers of the Standard Model, Steven Weinberg, is that the value of dark energy is anthropically selected. Anthropic arguments appear at one level to be a statement of the obvious. The properties of the universe must be such that human beings can exist, because human beings do exist. This is, of course, true, but it is fairly devoid of content from a physical perspective, unless there is some way in which all possible values of dark energy, and indeed all the other constants of nature are realized somewhere. If, for example, there exists a vast, possibly infinite swathe of different domains in the universe, or indeed an infinity of other universes, each with a different amount of dark energy selected by some mechanism from the span of allowed values, then we would indeed have a valid anthropic explanation for our special human universe. It must exist because they all do, and of course we appear in the one that permits our existence. But surely it makes no sense to take refuge in a vast infinity of universes to explain our existence. Absolutely correct. If that's why the idea is introduced, it's no better than a God of the gaps explanation. If, however, there was some other reason, based on observations and theoretical understanding, that suggested an infinity of universes, then such an anthropic explanation for our perfect human universe would be admissible. Remarkably, and that remarkably overused word is appropriate for once, this outlandish suggestion is a widely held view amongst many cosmologists. If we look at our universe on the largest distance scales, by which I mean at distance scales far larger than the size of single galaxies, it has a number of properties that any theory of its origin has to explain. The most precise picture of the young universe we have is the photograph of the cosmic microwave background radiation, CMB, taken by the Planck satellite. This is the afterglow of the Big Bang, a photograph of the universe as it was 380,000 years after the initial hot, dense phase, when the expansion had cooled things down sufficiently for atoms to form. The most obvious feature of the CMB is that it's extremely uniform, glowing at a temperature of 2.72548 degrees above absolute zero, with small fluctuations at the level of 1 part in 100,000. Those very tiny temperature differences are represented by the colors in the photograph. This uniformity is extremely difficult to explain in the standard Big Bang model for a simple reason. Our observable universe today is 90 billion light-years across. This means that if we look out to the CMB from opposite sides of the Earth, we are looking at two glowing parts of the ancient sky that are now separated by 90 billion light-years. The universe, however, is only 13.8 billion years old, which means that light, the fastest thing there is, has only had time to travel 13.8 billion light-years. Two opposite parts of the CMB could therefore never have been in contact with each other in the standard Big Bang model, and there is absolutely no reason why they should be almost precisely the same temperature. I've emphasized almost in the previous sentence because, as we noted, there are very slight variations in the CMB at the level of 1 part in 100,000, and these are very important. The universe was never completely smooth and uniform everywhere, and these variations in density are encoded into the CMB as differences in temperature. The regions of slightly greater density ultimately seeded the formation of the galaxies, and so without them, we wouldn't exist. What caused these small variations in the otherwise ultra-smooth early universe? Another fundamental property of the universe that is difficult to explain is its curvature, or lack of it, which can also be measured from the CMB. Space appears to be absolutely flat, a veritable ice rink. Recall from Chapter 1 that the shape of space is related to the density and distribution of matter and energy in the universe through Einstein's equations. In the standard Big Bang theory, the universe doesn't have to be flat. In fact, it requires a great deal of fine-tuning to keep it flat over 13.8 billion years of cosmic evolution. Instead, the radius of curvature is measured to be much greater than the radius of the observable universe, more than 60 orders of magnitude larger. That's a big problem. In the early 1980s, the need to explain these and other properties of the observable universe led a group of Russian and American physicists to propose a radical idea. The modern version, the best-known proponents of which are Alan Guth, Andrei Linde, and Alexei Starobinsky, is known as the theory of inflation. We'll describe a particular version of inflation below, driven by something called a scalar field, which was first described by Andrei Linde. Space-time existed before the Big Bang, and for at least some of that time was described by Einstein's theory of general relativity and a quantum field theory like the Standard Model. The central idea in quantum theory is that anything that can happen does happen. Everything that is not explicitly ruled out by the laws of nature will happen given enough time. One of the types of things permitted to exist in quantum field theory are scalar fields. We've met an example of a scalar field earlier in the chapter in the guise of the Higgs field, which we know to exist because we've measured it at the Large Hadron Collider. Scalar fields have the property that they can cause space to expand exponentially fast. We touched on such a scenario in Chapter 1 without being explicit about the mechanism. It is the de Sitter's matterless solution to Einstein's field equations first discovered in 1917. Given general relativity and quantum field theory, therefore, it must be the case that scalar fields will fluctuate into existence in such a way that an exponential expansion of spacetime is triggered. In this exponential phase, spacetime expands faster than the speed of light. This might sound problematic if you know some relativity, but it isn't. The universal speed limit exists for particles moving through spacetime, but does not apply for the expansion of spacetime itself. In a tiny fraction of a second, around 10 to the minus 35 seconds in fact, an exponential expansion of this type can inflate a piece of spacetime as tiny as the Planck length to a quite mind-boggling size, trillions of times larger than the observable universe. Any pre-existing curvature is completely washed out, leading to a flat observable universe. It's like looking at a square centimetre-sized piece of the surface of a balloon of a light year in radius. You won't see any curvature, no matter how hard you try. Likewise, any variations in density will be washed out, leading to the smooth and uniform appearance of the CMB. Perhaps the greatest triumph of inflationary models such as these, however, is that they don't predict a completely uniform, homogeneous and isotropic universe. Quantum theory doesn't allow for absolute uniformity. Empty space is never empty, but a fizzing, shifting soup of all possible quantum fields. Like the surface of a stormy ocean, waves in the fields are constantly rising and falling, and the exponential expansion can freeze these undulations into the universe. Remarkably, when calculations using the known laws of quantum theory are carried out, the sort of density fluctuations that result from such a mechanism are precisely of the form seen in the CMB. These quantum fluctuations are the seeds of the galaxies, and therefore the seeds of our existence, frozen into the oldest light in the cosmos, and photographed by a satellite built by the people of Earth 13.8 billion years later. Inflation in this guise explains the observable properties of our universe, and in particular all the details of the CMB, which has been measured to high accuracy. This is why it is currently widely accepted as an essential ingredient by many cosmologists. As if this wasn't enough to get excited about, however, there is much more. One obvious question that arises is this: if inflation gets going, how does it stop? The answer is that inflation stops completely naturally, but with a fascinating twist that drives right to the heart of our "why are we here" question. The scalar field driving inflation fluctuates up and down in accord with the laws of quantum theory, just like the waves on the surface of an ocean. If the energy stored in the field is high enough, inflation begins. One might expect that such a rapid expansion would dilute the energy extremely rapidly, causing inflation to stop. But scalar fields have the interesting property that their energy density can stay relatively constant as space expands. You can think of the expanding space as doing work on the field, pumping energy into it and keeping its level high. And in turn, the high level of the field's energy continues to drive the expansion. This might sound like the ultimate free lunch, and in a sense it is, almost, although gradually the energy will become diluted and decay away. The time this takes depends on the size of the initial fluctuation in the field and the details of the field itself, but in general, the higher the initial energy, the longer the field takes to fall in value as the expansion continues. An analogy often used to picture this scenario is to imagine a ball rolling down the side of a valley. The height of the ball up the valley side represents the energy density of the scalar field. When the ball is high up, the energy in the field is high, driving the inflationary expansion. As the ball rolls slowly down the valley, the energy reduces and inflation turns off. At the valley floor, the ball oscillates back and forth until it comes to rest. The scalar field likewise oscillates, and in doing so, dumps its energy into the universe in the form of particles. In so doing, it creates a hot, dense soup, which we identify as the Big Bang. In other words, inflation ends naturally, and the standard Big Bang follows. The decay of the scalar field that drove inflation is the cause of the Big Bang. Let us step back a moment and recap with broad brushstrokes, because we seem to be wandering onto Leibniz's territory, and that's an astonishing place for physics to have arrived at. Our claim is that there exists a quantum field that causes the universe to expand exponentially fast for some period of time, and in doing so, produces all the features of the universe we observe today, including the existence of galaxies and the matter out of which they are made. This is a triumph, and is now part of cosmology textbooks. Before the Big Bang, there was inflation. Fine, our philosopher friends would say, but what happened before inflation? Here we must leave the textbooks and become a little more speculative, but not too speculative. We're still going to be working within the domain of mainstream physics. There is an extension of what we might term standard inflationary theory. It's known as eternal inflation. Put simply, there seems to be no reason why inflation should stop everywhere at the same time. There should always be regions of the universe where the scalar field fluctuates to such high values that the exponential expansion continues, and these regions will always come to dominate the universe, however rare they may be, because they are exponentially expanding. Where inflation stops, Big Bangs herald the beginning of more sedately expanding regions like ours, but elsewhere, there is an ever-growing exponentially expanding universe, constantly spawning an infinity of Big Bangs. This theory, known as eternal inflation, leads to an infinite, immortal multiverse, growing fractal-like without end. This is truly mind-numbing, but we must emphasize that it is an entirely natural extension of standard inflationary cosmology. Eternal inflation opens up even more exciting possibilities. As we discussed above, one of the great mysteries in physics today is the origin of the constants of nature, such as the strength of gravity, the masses of the particles, and the value of dark energy. These values appear to be fine-tuned for the existence of life, and understanding where they come from is a prerequisite for understanding our existence. In eternal inflationary models, each mini-universe can have different values of these constants, and different effective laws of physics. The word effective is important. The idea is that there is some overarching framework out of which our laws and the constants of nature are selected randomly. If this is correct, then each of the infinite number of mini-universes that branch off the fractal inflationary multiverse can have different effective laws of physics, and all possible combinations will be realized somewhere. No matter how fine-tuned our laws appear for the existence of life, it is inevitable that such mini-universes as ours will exist, and there will be an infinite number of each possible set of combinations. There is no fine-tuning problem. Given the multiverse, we are inevitable. This is reminiscent of our rejection of your own personal uniqueness whilst listening to Joy Division at the beginning of the chapter. Yes, in isolation, the odds of you existing are almost vanishingly small. But given a mechanism for producing human beings, babies are born all the time, and their existence is not surprising. Here we have a mechanism for producing universes. And with an even greater statistical sledgehammer, the mechanism doesn't simply produce a few billion of them, it produces a potentially infinite number. This is a quite stunning theoretical model, and I understand that it sounds like wild speculation. It isn't, though. Inflation is probably correct in some form, in the sense that before what we call the Big Bang, there was an exponential expansion of space-time. Scalar fields, which are known to exist, have the correct properties to drive such an expansion, although there are other theoretical models of inflation as well. Theoretical physicists studying inflationary models have discovered that almost all of them are eternal, in the sense that they stop inflating in patches rather than all at once. This means that the potential for creating universes in the guise of inflation is always expanding faster than it is decaying away, and it will therefore never stop. We live in an infinite, eternal, fractal multiverse, comprised of an infinite number of universes like ours, alongside an infinite number of universes with different physical laws. We exist because it is inevitable. Almost. There is one very important caveat to this picture. Recent research suggests that eternal inflationary models may be eternal in the future, but not in the past. They never stop, but they may have to start. I can't give you a definitive answer to this ultimate question because nobody yet knows. I can quote from André Linde's recent review of inflationary cosmology, Inflationary Cosmology After Planck, 2013. In other words, there was a beginning for each part of the universe, and there will be an end for inflation at any particular point. But there will be no end for the evolution of the universe as a whole in the eternal inflation scenario. And at present, we do not know whether there was a single beginning of the evolution of the universe as a whole at some moment t equals 0, which was traditionally associated with the Big Bang. And so we reach the end. Defining the Big Bang as the initial hot, dense phase of our observable universe that gave rise to the CMB 380,000 years later, we understand what happened before. There was a period of inflationary expansion, which could have been driven by a scalar field in accord with the known laws of physics. That inflationary expansion is probably still going on somewhere, spawning an incalculable number of universes as we speak, and it will continue doing this forever. We live in an eternal universe in which everything that can happen does happen. And we are one of the things that can happen. Did the whole universe have a beginning, an essential external cause in the spirit of Leibniz's God? We still don't know. Possibly there was a mother of all Big Bangs, and if so, we will certainly need a quantum theory of gravity to say anything more. What does this mean? The wonderful thing for me is that nobody knows, because the philosophical and indeed theological consequences of eternal inflation have not been widely debated and discussed. My hope is that in trying to summarize the issues, regrettably briefly and necessarily superficially in the television series, and in a little more depth here, these ideas will be accessible to a wider audience and stimulate discussion. This is desirable and necessary, because ideas are the lifeblood of civilization, and societies assimilate ideas and become comfortable with their implications through understanding and debate. If eternal inflation is the correct description of our universe, it will be the artists, philosophers, theologians, novelists, and musicians, alongside the physicists, who explore its meaning. What does it mean if the existence of our universe is inevitable? What does it mean if we are not special in any way? What does it mean if our observable universe, with all its myriad galaxies and possibilities, is a vanishingly small leaf on an ever-expanding fractal tree of universes? What does it mean if you are because you have to be? I can't tell you. I can only ask, what does it mean to you? For small creatures such as we, the vastness is bearable only through love. Carl Sagan. They must have descended into the darkness for a reason. Their burning dry grass torches would have filled the caverns with acrid smoke, sucking the oxygen from the wet air. They would have moved carefully, fearfully perhaps, enveloped in a dim, flickering sphere of red, fading into a profound, silent dark, the like of which I don't experience. A child held her hand against the rock and blew a red pigmented mixture across it with a straw. She smiled. My hand. Her companions reached into the pigment and in careful movements inked a line of dots beside the handprint. The precision of a young imagination. A retreat into the lightness of the cave mouth. Perhaps we'll come back someday, she thought. Over 40,800 years later, I held my hand next to hers. Because the experts on the Upper Paleolithic told me that the handprints are always those of children, and most likely always female. El Castillo in northern Spain contains some of the oldest cave art in the world. It is not known precisely how old, because the pigments themselves cannot be dated. The art is covered in calcite, which dripped and crystallized across the handprints and dots, as the whole of recorded history played out above. Calcite contains uranium-234 atoms, which decay with a half-life of 245,000 years into thorium-230, which in turn decays with a half-life of 75,000 years. Thorium is not soluble in water, so there was none when the limestone formed. By measuring the concentrations of the uranium isotopes 234 and 238 and the thorium-230, a precise date for the formation of the calcite can be measured. This gives a minimum date for the art, since of course it must have been created before it was covered. The limestone covering the red dots formed 40,800 years ago. The oldest handprint was covered 37,300 years ago. These dates are significant because before 41,000 years ago, there is no evidence of modern humans in Europe. Homo sapiens arrived tantalizingly close to the minimum age of the art in the darkness of El Castillo, leading some anthropologists to suggest that the art is not human. Rather, it might have been created by our close cousins, the Neanderthals, who dominated Europe at the time. I find this possibility profoundly interesting and moving. It's interesting because the creators of this art had all the attributes that we might lazily refer to as uniquely human. The retreat into the deep caves was undoubtedly a sophisticated response to the world. This is not mere decoration, because cave art like this is not found near the cave entrances where these people lived. Its creation is highly ritualized. The darkness is integral. One of the most beautiful pieces in El Castillo is a bison, half carved out of a column of rock and shaded with pigments to emphasize the arch of its back. When illuminated by torchlight, the rock casts a flickering animal shadow onto the cave wall. The interaction of light and dark was important to the rituals carried out here before history, perhaps before humans. The cave resonates with ideas, curiosities, and fears. It represents a border, the transition from existence to living. If this is a human place, it's a record of the first stumbling steps towards humanity. But if it is Neanderthal, it is a record of an ending, an ascent cut short. Perhaps we'll come back someday, thought the little girl in my imagination. Not long afterwards, her species became extinct, outcompeted by their incoming cousins. Perhaps. It is possible that the date coincides with the migration of Homo sapiens into Europe because the art is indeed human. Some anthropologists believe that the art may have been a response to the native Neanderthal population, a sort of prehistoric shock and awe, asserting cultural dominance and engendering a sense of community and superiority in the nascent human population. Things never change. If this is the case, the Neanderthals inadvertently played a role in our ascent. The roles may have been reversed, however. Perhaps our ancestors found a young, emerging, and more sophisticated culture when they crossed the Mediterranean. A species distantly related to us, whose desire to explore the darkness we assimilated. Perhaps our intellectual climb was, in part, a response to them. Intellectual superiority does not guarantee survival. Witness the fall of classical civilization. This possibility is illustrative of a fact that we modern humans often subconsciously rest in the shadows. Things can end forever. Species become extinct, and that doesn't only apply to animals with feathers and no feelings. The Neanderthals became extinct, and they may have begun to imagine a future before they lost it. The red handprints of El Castillo are overwhelming in this context. Go there. Hold your hand up to hers. Hear the giggles. Picture the smiles. Imagine the beginnings of hope. And listen to the silence. At least 40,800 years later, we can use our knowledge of nuclear physics to move backwards through time to piece together her story. Science is a time machine, and it goes both ways. We are able to predict our future with increasing certainty. Our ability to act in response to these predictions will ultimately determine our fate. Science and reason make the darkness visible. I worry that lack of investment in science and a retreat from reason may prevent us from seeing further, or delay our reaction to what we see, making a meaningful response impossible. There are no simple fixes. Our civilization is complex. Our global political system is inadequate. Our internal differences of opinion are deep-seated. I bet you think you're absolutely right about some things and virtually everyone else is an idiot. Climate change, Europe, God, America, the monarchy, same-sex marriage, abortion, big business, nationalism, the United Nations, the bank bailout, tax rates, genetically modified crops, eating meat, football, X Factor or Strictly. The way forward is to understand and accept that there are many opinions, but only one human civilization, only one nature, and only one science. The collective goal of ensuring that there is never less than one human civilization must surely override our personal prejudices. At least we have come far enough in 40,800 years to be able to state the obvious, and this is a necessary first step. We've woken up at the wheel of the bus and realized we don't know how to drive it. Sudden impact. On the 15th of February 2013 at 9:13 a.m., a 12,000-ton asteroid entered Earth's atmosphere traveling at 60 times the speed of sound. It came from the direction of the sun, so there was never any chance of seeing its approach. The rock broke up at an altitude of 29 kilometers, depositing over 20 times the energy of the Hiroshima bomb into the sky above the Russian town of Chelyabinsk. Thousands of buildings were damaged by the shockwave, and 1,500 people were injured, mainly by flying glass, as windows smashed in multiple cities across the region. Sound waves from the explosion rattled around the globe twice, and were detected by a nuclear weapons monitoring station in the Antarctic. The Russian Parliament's Foreign Affairs Committee chief, Alexei Pushkov, took to Twitter. Instead of fighting on Earth, people should be creating a joint system of asteroid defense. Naive idealism? Overreaction? Hollywood? Not really. 16 hours later, a 40,000-ton asteroid named 367943 Duende streaked by at an altitude of 27,200 kilometers, well within the orbits of many of our satellites, although it missed them all. This one had a name, because it was discovered by astronomers in Spain in 2012. There is a 1 in 3,000 chance that Duende will strike the Earth before 2069. If it does, it could destroy a city, which isn't too bad. Before Chelyabinsk, the last recorded large impact was the Tunguska event over Siberia in 1908. The shockwave created by the airburst flattened 2,000 square kilometers of forest in an energy release close to that of the United States' most powerful hydrogen bomb test at Bikini Atoll in March 1954. Events on this scale are thought to occur on average once every 300 years, and could easily wipe out a densely populated region. The best-known impact in popular culture was the Chicxulub event in Mexico's Yucatan Peninsula 66,038,000 plus or minus 11,000 years ago, which wiped out the non-avian dinosaurs. Precision is important when available. If they'd had a space program, Carl Sagan once quipped, or perhaps lamented, the dinosaurs would still be around, although in that case we wouldn't. The Chicxulub asteroid was probably around 9.5 kilometers in diameter, and the energy release of such an object exceeds that of the world's combined nuclear arsenal by a factor of 1,000. Or if you like scary statistics, that's 8 billion Hiroshima bombs. Such events are estimated to occur on average every 100 million years, give or take, and are quite capable of destroying human civilization and possibly causing our extinction. At the other end of the scale, rocks of around 1 millimeter in diameter hit the Earth at a rate of 2 a minute. Alexei Pushkov was right. It is absolute idiocy not to pay attention to the danger of impacts from space, and fortunately our space agencies have begun to do so. NASA's Near-Earth Object Program created the Sentry system in 2002, which maintains an automated risk table continually updated by new observations from astronomers around the world. I'm writing these words on the 3rd of September 2014, and there are currently no high-risk objects in the table, although there are 13 asteroids with the potential to impact Earth that have been observed within the last 60 days. The risk posed by an asteroid is quantified on the Torino scale. Every known near-Earth asteroid is assigned a value on the Torino scale between 1 and 10, calculated by combining the collision probability with the energy of the collision in megatons of TNT. Asteroid 99942 Apophis reached level 4 on the Torino scale in December 2004. Initial observations and calculations suggested this 350-meter-wide asteroid had a 1 in 37 chance of a potential collision with the Earth on the 13th of April 2029, and a further chance of hitting us 7 years later if it missed first time around. This would not have been a civilization-threatening event, but it could have laid waste to a small country. Subsequent observations have effectively ruled out the risk from 99942 Apophis, but statistically speaking, such an impact is expected to occur every 80,000 years or so. Although the Sentry table is currently benign, there are at least 2 very good reasons why we shouldn't relax and forget about impact risks. Firstly, we haven't detected all of the threatening objects by any means, as the Chelyabinsk event so effectively reminded us. And secondly, we don't currently know precisely what to do if we do observe an asteroid with our name on it, which could happen tomorrow. In 2016, a new early warning system called ATLAS, Asteroid Terrestrial Impact Last Alert System, came online. 8 small telescopes scan the sky for any sign of faint objects that may pose a threat to the Earth. ATLAS will give up to 3 weeks warning of an impact, which is enough time to evacuate a large region, but probably not an entire country. The cost of our global insurance policy? 1/3 of the annual wages of Manchester United striker Wayne Rooney. Such comparisons always sound childish, of course. I'm well aware of how capitalism functions, and I know that Wayne Rooney generates income for the Manchester United Corporation in excess of his wages. But the aim of this chapter is to argue that there is a flaw in the majestic edifice of human civilization, our myopic and cavalier disregard for our long-term safety. In my view, the reason for the short-sighted approach is that nothing catastrophically bad has happened to humanity in recorded history that we haven't inflicted upon ourselves. Unless, of course, you believe in Noah's Ark. And even that was presumably down to us, because one assumes that God is usually quite a patient sort. One of the central themes of this book has been to argue that the human race is worth saving, because we are a rare and infinitely beautiful natural phenomenon. One of the other themes is that we are commonly and paradoxically ingenious and stupid in equal measure. I do not personally think that there is anyone out there to save us, and so it follows that we will have to save ourselves. At least, that would seem to me to be a good working assumption. This is why I don't feel naive, idealistic, or like a particularly radical member of the student union in a Che Guevara t-shirt when I asked the question, is it reasonable to spend less on asteroid defense than on a footballer's annual salary? When I look in the mirror and think about that, my face assumes an interesting shape. You should try it. NASA is working hard in the face of apathy to do something to close the gap between the capabilities of the dinosaurs and us. 20 meters beneath the surface of the Atlantic Ocean, 8 kilometers off the coast of Key Largo, Florida, is the Aquarius Reef Base. Originally constructed as an underwater research habitat to study coral reefs, it is used by NASA to train astronauts for future long-duration space missions. The base allows for saturation diving, which greatly increases the length of time a researcher can spend exploring the reefs. On a normal scuba dive, a diver can spend a maximum of 80 minutes at a depth of 20 meters without having to go through decompression. The diver can remain at this pressure for several weeks, however, as long as they decompress when they return to the surface, a process that takes almost a day. Since the air pressure inside Aquarius is the same as the pressure outside in the water, researchers living inside the base can spend many hours a day exploring the seabed using standard scuba equipment, but with the important caveat that they cannot return to the surface a few meters above their heads. If anything goes wrong, they must return to Aquarius and deal with the problem inside the base. For all practical purposes, therefore, they are isolated. It's not possible to panic or simply lose patience and return to civilization above. This is why NASA uses the Aquarius base to train astronauts to work in a hostile environment and test their psychological suitability for long-duration space missions. Filming inside Aquarius was a personal highlight of human universe. We didn't want to have to decompress, of course, so we had a strict time limit of 100 minutes inside the base, spread over 2 dives. The ex-US Navy diver in charge of our dive was wonderfully clear as far as timings were concerned. If I say leave, you don't smile and take one more shot, you leave. Otherwise you stay, for a long time. Your choice. I know you media types. Aquarius has the look and feel of a spacecraft from a science fiction film. There are 6 bunk beds piled 3 high at one end, and a galley area complete with microwave and sink at the other. In between there are control panels, some books on marine life, and a laptop computer station. Above the table, there is a single round window looking out across the reef. Through an airlock-style exit, there is a dive platform with access to the scuba tanks and the open sea. NASA's Extreme Environment Mission Operations, NEMO, team had just completed a 9-day mission when we arrived. Led by Akihito Hoshide of the Japanese Aerospace Exploration Agency, the mission was part of the long-term goal of landing astronauts on an asteroid and developing the capability to deflect one should the need arise. There are strong scientific and commercial reasons for exploring asteroids. They are pristine objects that will allow us to better understand the formation of our solar system over 4.5 billion years ago, and rich in precious metals precisely because they are pristine. On Earth, heavy metals such as palladium, rhodium, and gold migrated into the Earth's core, leaving the accessible crust depleted. Asteroids are too small to have separated in this way, leaving the primordial abundances of these valuable metals untouched and accessible. Whether for commercial, scientific, or practical reasons, learning how to land on asteroids, exploit their resources, and manipulate their orbits is clearly an eminently sensible thing to do. And make no mistake, we will have to move one at some point. Seeing the future. In the year 35,000 CE, the red dwarf Ross 248 will approach the solar system at a minimum distance of 3.024 light-years, making it the closest star to the Sun. 9,000 years later, it will have passed us by, ceding the title of nearest neighbor to Proxima Centauri once again. Coincidentally, in 40,176 years, Voyager 2 will pass Ross 248 at a distance of 1.76 light-years. We know this because we can predict the future. We've encountered Newton's laws several times in this book. In Chapter 3, we used them to calculate the velocity of the International Space Station in a circular orbit around the Earth. At a distance r from the center of the Earth, the velocity v is v equals the square root of gme over r. Let's look at this equation in a different way by rewriting it as dx by dt equals the square root of gme over r. Here we've used the notation of calculus. That may strike fear into your heart if you haven't done any mathematics since school, but don't worry. All we need to know is the meaning of the symbol dx by dt. In words, this denotes the rate of change of the position of the space station with respect to time, otherwise known as its velocity, v. You have an intuitive feel for this, even if you've never done any mathematics. If you get into your car and drive it away from your house in a straight line at a velocity of 30 kilometers per hour, then in 1 hour, you will be at a position 30 kilometers away from your house in the direction in which you drove the car. The equation is telling us what the position of the space station will be at some point later in time, given knowledge of where it is and how it is moving in the present. It predicts the future. This sort of equation is known as a differential equation. In Chapter 4, we wrote down the rules of the game, Einstein's general theory of relativity and the standard model of particle physics. The notation is a little more complicated, but in the standard model you'll notice the symbols d mu and delta mu, which are more complicated versions of dx by dt. In Einstein's equations, there are also these so-called derivatives hidden away in the compact mathematical notation. The known fundamental laws of physics all function in this way. Given knowledge of how some system or collection of natural objects is behaving now, we can compute what they will be doing at some time in the future. The system in question may be a solar system, a collection of atoms and molecules, or the weather. There are practical limitations, of course, and the weather forecast is a good example. Earth's climate system is very complicated, with many hundreds of thousands of variables. Ocean currents in the Pacific might affect future rainfall in Oldham, and so long-term forecasting of local weather conditions comes with increased uncertainty. People do, of course, make statements, often based on human experience rather than science, which are more likely to be right than wrong. Red sky at night, shepherd's delight; red sky in the morning, shepherd's warning. This is often true in countries like the UK, whose weather is dominated by westerly winds, because a red sunset is usually a sign of high pressure to the west, which is associated with fine weather. But if you're doing well in a statistically significant sense using folklore or ancient wisdom, it's because the patterns and regularities you're using to make your predictions emerge from underlying physical laws which are described by differential equations. The laws of physics, in essence, reflect the underlying simplicity of nature and the regularity with which it behaves. They're not magic. We can describe the natural world using mathematics because it is regular and behaves consistently. It is my opinion that we must observe a universe that behaves in a regular and consistent way, because such behavior is necessary for complex structures like brains to evolve. A universe of anarchy with subatomic particles interacting without some sort of framework or rules would surely not support life, or indeed any structures at all. This is known as a selection effect. We observe a universe whose behavior can be described by a limited set of differential equations because we wouldn't exist if it were not so. This is my opinion, and there are scientists and philosophers who might disagree. It could be the case that there is no simple underlying framework to the universe, and our success to date has deceived us. Or perhaps the ultimate laws are and will forever remain beyond human understanding. We might simply not be smart enough to figure them out. There are also systems that cannot be described using differential equations. The patterns generated in Conway's Game of Life are an example, where algorithmic rules are used to generate complex patterns, and even computing devices such as Turing machines. But what can be said with certainty is that as far as we can tell, the natural world does behave in a way that is amenable to a description based on the differential equations of physics, and these allow us to predict the future given knowledge of the present. This is why our asteroid defense system will work if we make enough high-precision observations of the sky. Sort of. Caveats. There are always caveats. We should be confident in science. It works. But it has limitations, some of which are fundamental. We've encountered Newton's laws of motion and gravitation time and again in this book. They're very simple, the archetypal physical laws, and are used every day by engineers, navigators, and asteroid watchers. One of the simplest imaginable real-life systems to which Newton's law of gravitation can be applied is a single planet orbiting around a single star. For this case, Newton's laws allow for a precise prediction of the future position of the planet. The orbit is predictable and periodic, which is to say the planet returns to precisely the same position around the star every orbit. It's clockwork, the way the solar system is often pictured. If a third object, a moon, say, is introduced, it was proved in the late 19th century by Heinrich Burns and later Henri Poincaré that no general solution to Newton's equations can be found. There are a handful of special cases, which are still being discovered, for which there are repeating solutions, but in general, the orbits of three bodies acting under gravity never repeat. Their motion around each other traces out a tremendous, ever-changing mess. This isn't a failure of mathematics. Natural systems really do behave in this way. The solar system is a case in point. The planets orbit like clockwork on timescales of millions of years, but we are currently unable to predict the Earth's orbit for more than 60 million years into the future. Beyond that, the sensitivity of the predictions to uncertainties in our current knowledge of the Earth's orbit and the gravitational influence of other bodies in the solar system become too great. This isn't only a reflection of our lack of knowledge. It also reflects an important fundamental point, which is that solar systems such as ours are unstable over long timescales. Their behavior is chaotic. The apparent clockwork can break down into a whirling, unpredictable swarm. Recent simulations suggest that Mercury could be wrenched out of its orbit and collide with the Sun, and that even the Earth may have a close encounter with Venus or Mars on time periods of 3 to 5 billion years. The words could and may are emphasized for a reason. These predictions are statistical in nature. It's estimated that there is a 1% chance that Mercury will be thrown into a much more elliptical orbit during the next 5 billion years. The uncertainty is down to the extreme sensitivity of the predictions to what physicists call the initial conditions, the current knowledge of precisely where everything in the solar system is at this instant, and how everything is moving at this instant. Other errors are caused by our precise knowledge of the mass and shape of all the objects in the solar system, not to mention the slight perturbations from incoming comets and the ever-shifting asteroids. The area of physics and mathematics concerned with such systems is called chaos theory, and as the pioneer of the field Edward Norton Lawrence put it, nature's complexity usually leads to a situation in which approximate knowledge of the present, which is in practice all we ever have, does not approximately determine the future. For the asteroid hunters, this is an intensely problematic truth. It is not possible to observe an asteroid once and then pop its position and velocity into a computer to work out whether it will ever hit us. Instead, a gravitational keyhole system is used. A keyhole is a small volume of space close to the asteroid's current orbit. If an asteroid passes through the keyhole, perhaps because of a gravitational nudge from some other object in the solar system, then it is highly likely that it will impact the Earth on its next pass. 99942 Apophis was assigned such a keyhole in 2004 when it was classified as 4 on the Torino scale. Fortunately, it didn't pass through, and this is why it is currently classified as harmless. The keyhole system reflects the fundamental unpredictability of complex physical systems over long timescales. This is why we have to keep observing and retain a keen understanding of the fundamental limits of our calculational prowess. Science isn't magic. This realization is, of course, important in a practical sense, if one is interested in saving the planet from asteroid impact. But it's also very important to embed caution and humility into our/my polemical celebration of the power of science. Scientific predictions are not perfect. Scientific theories are never correct. Scientific results are always preliminary. Whole fields of study can be rendered obsolete by new discoveries. But, I insist, science is the best we can do, because it is not simply another arbitrary system of thought based on dreamt-up human axioms. It is the systematic study of nature, based on observations of the natural world and our understanding of those observations. Scientific predictions are not matters of opinion. At any given time, science provides the best possible estimate of what the future might bring, given our current understanding. The predictions may be wrong, they may be inaccurate, the errors may be fundamental in origin, but there is simply no other rational choice than to act according to the best available science. Imperfect though by necessity, its predictions will always be. The wonder of it all. As of September 2014, in a population of 7.24 billion, 545 people have been to space, 24 people have broken free of the Earth's gravitational pull, and 12 have landed on another world. In 2013, Charlie and Dorothy Duke, a retired church-going couple from New Braunfels, Texas, reached their 50th wedding anniversary. With 2 grown sons and 9 grandchildren, Charlie and Dottie must have celebrated a life well lived, captured in photographs adorning the walls and mantelpieces of the family home. There is one Duke family photograph, however, that holds a unique place in history. I myself have a copy of it on my wall at home, signed by Charlie, and it's one of my favorite things. The photograph, taken in 1972, is an image of Charlie, Dottie, and their 2 young sons Charles and Thomas when they were just 6 and 4 years old. The picture itself is of no particular note, a simple portrait of a family in 70s clothes, sitting on a bench in a garden. It's not dissimilar to one of me and my granddad photographed at around the same time. I was in Oldham, the Dukes were in Florida. The reason I have a copy of the Duke's photograph is not what it is, we are not related, but where it is. Charlie and Dorothy Duke are the only grandparents on Earth who can point their grandchildren's eyes towards the moon and tell them there is a photo of Grandma, Grandpa, Dad, and Uncle resting on the surface. Charlie Duke was the pilot of Orion, the Apollo 16 lunar module. At the age of 36, he remains the youngest human ever to have walked on the moon. Together with Commander John Young, my childhood hero, the 2 astronauts spent 3 days in late April 1972 exploring the Descartes Highlands, covering almost 27 kilometers in the lunar rover. The primary scientific aim of the mission was to explore the geology of the lunar highlands. It was thought that the unique rock formations around the landing site were formed by ancient lunar volcanism, but Young and Duke's exploration demonstrated that this explanation was incorrect. Instead, the landscape had been forged by impact events, scattering material outwards from the craters and littering the surface with glass. After 3 days on the lunar surface and setting a lunar land speed record of 17 kilometers per hour, Charlie Duke removed his family portrait from his spacesuit pocket, placed it on the lunar surface, and snapped it with his Hasselblad. Inscribed on the back are the words, "This is the family of astronaut Duke from planet Earth. Landed on the moon, April 1972." I remember being 4 years old in Oldham when Apollo 16 was on the moon. 42 years later, I talked to Duke for hours in a diner in Texas, with absolutely no regard at all for the film crew trying to make human universe. When I stepped onto the moon, it occurred to me that nobody had ever been here before. You looked out onto the most pristine desert, the most incredible, beautiful place I've ever seen. No life, nothing like Earth. The rolling gray lunar surface with the blackness of space above. How ambitious was Apollo? I asked. They gave us 8.5 years to do it, and we did it in 8 years and 2 months. Nobody even knew how to do it, replied the test pilot, who was used to doing things that nobody can do. Yeah, sure. 15 minutes in space and we're going to land on the moon in 8.5 years? But the remarkable part is that we did it. And I had a part in it. Would it be possible now? No. We don't have the manpower to do it. 400,000 people, and unlimited budget, and you can do a lot. And that's what we had. What do you say to people who criticize manned exploration? There's surely more to human exploration than just science. It's the wonder of it all, replied the astronaut. And that's what we bring, what manned flight brings to the human spirit, the human being. The wonder of it all. The beauty of the universe, the orderliness of the universe. And you see it with your own eyes, and it just captures your imagination. Let's see it. Let's do it. And let's discover it. That's been the human spirit all along. I think Apollo is the greatest human achievement. People argue with me, of course. Gil Scott-Heron wrote a song called Whitey's on the Moon. A rat done bit my sister Nell with Whitey on the moon. Her face and arms began to swell, and Whitey's on the moon. I can't pay no doctor bill, but Whitey's on the moon. 10 years from now I'll be paying still while Whitey's on the moon. The economics of Apollo are interesting. As Charlie said, the budget was whatever it had to be to get to the moon by 1970. At the peak of spending in 1966, NASA received 4.41% of the federal budget, equivalent to around $40 billion today. That's a lot of money, almost half the United Kingdom's annual debt interest bill. That's meant to be sarcastic, of course. The total cost of Apollo was in the region of $200 billion at today's prices, which is around a quarter of the cost of the UK's bank bailout programme initiated in October 2008. That's unfair, a city type might splutter over a glass of Don Ruinart, because that money was an investment in financial stability and has been repaid, give or take the odd 100 billion, which is neither here nor there. My reply would be yes, but Apollo was probably the most savvy investment in modern history. In 1989, the then US President George Bush said Apollo provided the best return on investment since Leonardo da Vinci bought himself a sketch pad. Many academic studies have been carried out, and the most commonly quoted figure is that for every dollar spent on Apollo, $7 was returned to the economy over the period of a decade. Why? Because Project Apollo was conceived and executed in a tremendously smart way, distributing high-technology jobs and R&D projects across the country. It was also unarguably inspirational, propelling thousands of kids into science and engineering. The average age in Mission Control Houston on the 20th of July 1969, when Neil Armstrong landed on the moon, was 26. The old man in charge, Gene Kranz, was 36, and the old man flying the lunar module was 35. What happened to all those brilliant engineers? They went out into the economy, of course, took the technology and expertise developed for the moon landings, and invented the modern world. The kids they inspired became known as Apollo's children, the generation of optimists, steeped in possibility, who powered the United States economy through the last third of the 20th century. The world loves this America, the one that flies to the moon not because it's easy, but because it's hard. I think America has lost its way, which might seem rich from a citizen of a small island that spends more on the wages of Premier League footballers annually than it does on research into the physical sciences and engineering, including its contributions to CERN, the European Space Agency, and all UK-based scientific facilities. We've lost our way too. And so has the world. The World Bank defines R&D as current and capital expenditures, both public and private, on creative work undertaken systematically to increase knowledge, including knowledge of humanity, culture, and society, and the use of knowledge for new applications. The United States spent 2.79% of its GDP on increasing knowledge in 2012. The UK spent 1.72%. It has been estimated that the return on R&D spending in today's world economy is approximately 40 to 1. Imagine what we could do if we took these figures seriously. My granddad, sitting behind me in that 1972 family Christmas photograph, was born in 1900. He was 3 years old when on the 17th of December 1903 at Kill Devil Hills in North Carolina, Orville Wright took the controls of the Wright Flyer and lifted off the ground for 12 seconds. He was 68 when he saw Neil Armstrong walk on the moon. Orville Wright himself died in the year that Neil Armstrong began studying aeronautical engineering at Purdue University, Indiana. I still find it hard to believe that I have spoken to someone who was born before powered flight, and to someone who walked on the moon. It's important to notice that this sentence can't be followed. Someone who walked on the moon, comma, and someone who... what? Where will the next generation of Apollo's children come from? Perhaps a new superpower will take America's place as the great exploring nation. China and India, those re-emergent cradles of civilization, have ambitions in space. As Jacob Bronowski wrote in The Ascent of Man, humanity has a right to change its color. But I share his regret that the retreat of Western civilization may leave Shakespeare and Newton as historical fossils, in the way that Homer and Euclid are. If that is the case, it will be our choice. 2 more astronauts followed Duke and Young onto the lunar surface. They left at 10:55 p.m. GMT on the 14th of December 1972. Commander Gene Cernan, as he prepared to step onto the ladder of the lunar module, quietly spoke the final words from the moon. "I'm on the surface, and as I take man's last step from the surface, back home for some time to come, but we believe not too long into the future, I'd like to just say what I believe history will record. That America's challenge of today has forged man's destiny of tomorrow. And as we leave the moon at Taurus Littrow, we leave as we came, and, God willing, as we shall return, with peace and hope for all mankind. Godspeed, the crew of Apollo 17. Gene Cernan, Taurus Littrow Valley, 14th of December 1972. Dreamers, Part 1. Apollo was about many things. It was about winning a race against the Soviets. It was about national pride. It was born out of fear as well as optimism. It was about laying the foundations of American dominance in the late 20th century. It was about economic stimulus. It was about dreams. It succeeded on all fronts. Was it really about dreams? Well, space is there, and we're going to climb it. And the moon and the planets are there. And new hopes for knowledge and peace are there. And therefore, as we set sail, we ask God's blessing on the most hazardous and dangerous and greatest adventure on which man has ever embarked. I think so. Kennedy was a politician, but I believe he meant it. So what of the dreamers now? Is the 21st century the era of pragmatism? The era in which we believe because we have to that the interests of shareholders are aligned with the interests of humanity? Innovation funds the shops on New Bond Street, but is that all? A common governmental lament is that new knowledge is not converted efficiently enough into economic growth. Is that what knowledge is for? Who pays for progress? Who should pay for progress? Human Universe is a piece of documentary television, and this book is based on the series. Television is about stories, examples that illustrate a point. Human Universe is also, at heart, optimistic, because I am optimistic. I think we as a civilization could do better, as I'm sure you've gathered, but it would be ridiculous to suggest that we're not doing some things right. In the final episode, we found 2 stories that demonstrate that long-term thinking is not dead. One almost Apollo-like in state-funded grandeur, and the other more modest but equally important. The first was a project I'd visited once before, back in 2009, known as the National Ignition Facility at the Lawrence Livermore National Laboratory in California. The aim is to make a star on Earth. Nuclear fusion is the power source of the stars. The Sun releases energy in its core by turning hydrogen into helium. Two protons approach each other at high speed because the core is hot. The core became hot initially through the collapse of the gas cloud which formed the Sun. Protons are positively charged, and therefore repel each other through the action of the electromagnetic force, but if they get close enough, the more powerful nuclear forces take over. The weak nuclear force acts to turn the proton into a neutron, with the emission of a positron and an electron neutrino. The proton and the neutron then bind together under the action of the strong nuclear force to form a deuterium nucleus, which is an isotope of hydrogen, because it contains a single proton, with a neutron attached. Very quickly, another proton fuses with the deuteron to form helium-3, and finally two helium-3 nuclei stick together to form helium-4, with the emission of the two spare protons. The important result in this convoluted process is that 4 protons end up getting converted into a single helium-4 nucleus, made of 2 protons and 2 neutrons, and the helium-4 nucleus is less massive than 4 free protons. This missing mass is released as energy, in accord with Einstein's equation E equals mc squared, and this is why the Sun shines. The energy released in fusion reactions is colossal by terrestrial standards. If all the protons in a cubic centimetre of the solar core were to fuse into deuterium, enough energy would be produced to power the average town for a year. Or to put it another way, 1 kilogram of fusion fuel produces as much energy as 10 million kilograms of fossil fuel, which is approximately 100,000 barrels of oil, with no CO2 emissions. The waste product is helium, which can be used to fill party balloons. Energy is the foundation of civilization. Access to energy underpins everything, from public health to prosperity. Access to clean water is surely more fundamental, you might say, but this requires energy. Even in the most arid regions, desalination plants or deep wells can deliver water in abundance if sufficient energy is available. It isn't, of course. Profligate energy use has a bad name today, but consider this. In every country in which the per capita energy use is greater than half the European average, adult life expectancy is greater than 70 years. Literacy rates are greater than 90%, infant mortality rates are low, and more than 1 in 5 of the population is in higher education. The reason energy use has a bad name is not because it is bad in itself. It is good. It is the foundation of modern civilization, and modern civilization is a good thing. I don't want to live on a subsistence farm, sleep in stifling heat, run the risk of dying of malaria and have no access to clean water or cutting-edge medical care. I'm lucky. I live in a city. I buy all the food I want from nice shops. I have a fulfilling job in a university, and I get to do research at places like CERN, which is interesting. I want everyone in the world to have choices, like I have. And that means I want everyone in the world to have access to energy, like I have. In 2011, 1.3 billion people lacked access to electricity. Yes, energy use is good. The problem with energy is how we produce it. The world produces more than 80% of its energy by burning fossil fuels. This is expected to fall to 76% by 2035, as nuclear and renewables grow in importance. Burning things is humanity's oldest technology. The energy sector is responsible for 2/3 of global greenhouse gas emissions. The most recent scientific modelling suggests that global average temperatures will rise by around 2 to 2.5 degrees C above the average of the years 1986 to 2005 by 2100. The rise could be less, as low as 1 to 1.5 degrees C, or it could be 4 degrees C or more. Some of the uncertainty depends on our actions, and so there are assumptions about future behavior built into the predictions. But over 90% of computer models agree that global temperatures will have increased by 2100 as a result of greenhouse gas emissions from fossil fuel burning. Nuclear fusion, then, is a good idea. If it can be made to work in an economically viable way, it will provide limitless, clean energy for everyone. It is not the only way of achieving this goal, One can make a case for solar power, and indeed an increased contribution from other renewables and nuclear fission. But it is a possible way to solve the world's energy problems for good, in principle, and is therefore worth exploring. The challenge is technical rather than fundamental, in the sense that we know fusion works because the sun does it. Fusion is difficult to achieve on Earth, primarily because of the colossally high temperatures and pressures required. There are two approaches being followed, and each is Apollo-like. In Europe, a worldwide collaboration involving Russia, USA, the European Union, Japan, China, Korea, and India is in the process of constructing ITER. This machine is in effect a magnetic bottle, which can store a plasma at temperatures in excess of 150 million degrees C, 10 times that of the solar core. ITER will use deuterium and tritium, which is another isotope of hydrogen comprising 1 proton and 2 neutrons, to make helium-4. This bypasses the slow initial weak interaction in the Sun that makes deuterium out of hydrogen, making ITER a lot more efficient than our star. Deuterium is extracted from seawater, and tritium is made inside the reactor itself by irradiating a lithium blanket with the spare neutrons produced during the fusion reaction. An 800 megawatt fusion power station of this type would consume around 300 grams of tritium fuel per day. ITER is not particularly telegenic at the moment because it's under construction and will not be commissioned until 2019. This is why we chose to focus on the US National Ignition Facility, which is already up and running. NIF is pure science fiction. In fact, it was used as a set for Star Trek Into Darkness. It is the world's largest laser system by an order of magnitude. The laser delivers 500,000 gigawatts of power onto a target smaller than a peppercorn in a series of increasingly powerful hammer blows tuned to arrive with a precision of better than 1/10 of a billionth of a second. That is 1,000 times the peak energy generating capacity of the United States. This, as you can imagine, creates a bit of a bang. The peppercorn-sized target contains deuterium-tritium fuel, just like ITER. The laser pulses raise the temperature of the pellet's gold container, and the X-ray radiation produced drives a rapid collapse of the fuel, initiating fusion. The devil is in the detail. The precise timing and duration of the laser pulses and the shape of the gold container all contribute to the chances of success and the efficiency of the process. Despite the tremendous engineering difficulty, in September 2013, more energy was released from a deuterium-tritium fuel pellet than the pellet absorbed, although this was only 1% of the total energy input to the lasers. Nevertheless, this demonstrates that so-called inertial fusion works in principle. The inertial fusion power stations of tomorrow would use far more efficient laser systems, NIFs are now more than a decade out of date, and the fuel pellet technology being developed by NIF. The technology has been demonstrated to work, at least on a vast government-funded research scale, and this is how difficult things like space exploration have to begin. Commercial companies will rarely take such enormous risks, and this means that we, the taxpayers, must pay for the creation of this type of knowledge. As with Apollo, we will be repaid, but the investment horizon is beyond that of the average accountant. It therefore appears that there is no technical reason why such power stations could not be constructed. There is much research to be done, but the barriers are likely to be budgetary rather than fundamental. The United States spends more on pet grooming than it does on fusion research. There's a serious point behind that cheap shot. I think one of the primary barriers to progress is education. I am a believer in the innate rationality of human beings. Given the right education, the right information, and the right tuition in how to think about problems, I believe that people will make rational choices. I believe that if I said to someone, "Here's the deal. You can have limitless clean energy for your lifetime, for your children and grandchildren's lifetimes and beyond, in exchange for grooming your own cat," then most people would reach for a comb. I have to believe that. Otherwise, this book is a futile gesture. The second of our stories couldn't be more different. It involves no high technology and very little cash, but it may have a tremendous impact. Securing the future isn't all about money. It's also about action. The Svalbard Global Seed Vault is modest and beautiful from the outside. In common with all publicly funded construction projects in Norway, the simple door on an Arctic hillside is a work of art, created by Divek Sanna. In the summer, it reflects the eternal sun. In winter, fiber-optic cables shine in the perpetual night. The doorway leads into a converted coal mine deep in the permafrost. There are 3 caverns, each maintained at a temperature of -18 degrees C by a cooling system. The temperature was chosen very precisely. It's the temperature at which seeds metabolize slowly but do not die. At -18 degrees C, the most hardy seeds remain viable for over 20,000 years. Only one of the caverns is in use. The other 2 are for the future. Inside, there are over 800,000 populations of seeds from almost every country in the world. All the seeds are agricultural crop varieties, the raw material for and the foundation of global food production. Seeds from America and Europe nestle next to those from Asia and Africa. Syrian seeds rescued from the recent troubles in Aleppo, the home of a local seed bank, sit beside those from North Korea, South Korea, China, Canada, Nigeria, Kenya, and so on around the world. The vault contains virtually the whole history of human agriculture, stretching back to its origins in the Fertile Crescent all those years ago. Each seed population reflects some choices that were made, some environmental challenge, or perhaps simply the taste of a farmer or his village. There are varieties manipulated by multinationals, or carefully cultivated and cherished by isolated tribes. The boxes are food for the imagination, time capsules, the stuff of dreams. They are also of fundamental importance. Why protect agricultural seeds? The answer is that biodiversity is a very good thing. Life on Earth forms a tangled web, a great genetic database distributed across hundreds of thousands of extant species of animals, plants, insects, and countless single-celled organisms. The more species there are, the more data there is in the database, and the more chance the whole biosphere has of responding to the challenges, be they from disease, natural or human-induced climate change, loss of natural habitat, or whatever. This is obvious. If there are genes somewhere in the great database of life that allow wheat to grow with less water and the climate becomes more arid, then those genes will be valuable to us. If we lose particular genes, then we lose them for good. Today, fewer than 150 species of crop are used in modern agriculture, and 12 of these deliver the majority of the world's non-meat food supply. There is diversity in the form of different varieties, of course. There are estimated to be more than 100,000 varieties of rice. But the overwhelming majority of crop species used throughout human history are no longer cultivated. They are stored, however, in seed vaults, ready for use if needed. The Svalbard Global Seed Vault is a backup, our insurance policy, ensuring that even if countries lose their seed vaults through natural disasters, war, or simple neglect, then irreplaceable parts of the great genetic database of life will not be lost with them. The Norwegian government owns the seed vault, but the depositors own the seeds. A charitable trust, the Global Crop Diversity Trust, meets most of the operating costs through an endowment fund. Carey Fowler was the executive director of the trust during the establishment of the seed vault. He was a pleasure to speak to when we filmed in Svalbard. A dreamer, yes, but a dreamer who gets things done. Those of us in my field, we live in a world of wounds, said Fowler. We see the injuries, we see the loss of diversity, the extinction, and at a certain point, enough is enough, and you try to figure out what can we do that's not just stopgap, that really is long-term, and that puts an end to the problem of crop diversity. Because we know that we're going to need this crop diversity in the future. It's the biological foundation of agriculture. We'll need it as long as we have agriculture. Which is as long as civilization exists, I added. Fowler nodded. After that, we won't be bothered, will we? The Svalbard Global Seed Vault is built, effectively, for eternity, or at least for tens of thousands of years. It is supported by practically all the governments of the world, and is a genuine investment in our future, based on sound science and an understanding of the potential challenges and risks that we may face as a single global civilization. It's not big, flashy, or expensive, but it's important. And perhaps as importantly, somebody actually did it. I find that inspiring.
In the fall of 2003, it unleashed an eruption of energy equal to 200 billion hydrogen bombs, blasting a tidal wave of superheated charged particles at speeds of up to 6 million miles an hour. It was one of the largest solar storms ever recorded. And it was aimed at Earth.
They were some of the fastest, hottest, and strongest storms ever measured.
Assaulting the Earth, the sun's energy forced space station astronauts to take cover in their most sheltered compartments. Lights went out. Communication streams were cut. Airliners scrambled for safety.
This really was a hurricane of space storms.
Though no major damage was done, these storms were a stark reminder that we live at the constant mercy of the sun. It controls all aspects of our lives: our climate, our food, our bodies.
We actually live inside the sun's atmosphere. We, along with all the other planets, are greatly influenced.
But is its influence changing?
It's actually growing more powerful.
Might we lose its protection from deadly cosmic rays?
At its boundary, where it's protecting us from the intergalactic winds, that boundary is actually shrinking a bit.
Will our technology-dependent society be able to handle another solar superstorm?
Sometimes these effects can be so severe that they're catastrophic.
And when will the next superstorm strike?
Three, two, one, go for drop.
Pegasus is away on the IBEX mission. All Pegasus.
Fall 2008.
Stage 1 ignition.
NASA launches IBEX, the Interstellar Boundary Explorer. Part of its mission is to study the effects the sun has on the furthest reaches of our solar system. IBEX joins the long list of human attempts to explain our star's impact on our solar system, our planet, and our lives.
The sun. The sun provides all of our light and heat. If it weren't for the sun, we wouldn't be alive.
We people are very interested in what goes around us. We like to understand our neighborhood. The sun in the universe is our street, our neighborhood.
The sun. We are actually affected by its moods. In fact, it's like the parent, and all the planets are the children that are affected by its moods.
We need to know how it's going to evolve and how the changes that are always happening in the sun affect us here on Earth.
The sun, if we want to understand the universe and the stars that make up the universe, then it's important to study the one that's closest to us.
We've learned more about the sun in the past 40 or 50 years than in all of recorded history.
This golden age of exploration was kicked off by a unique mission that gave us close-up images of our sun from above our atmosphere.
Skylab, we're reading you loud and clear over the Vanguard for 8 minutes.
In 1973, Skylab became the first manned space station. It sent back images of the sun, clearer than anything taken from Earth.
The Skylab mission was one of the very first laboratories that was dedicated just for the research and study of the sun. In some ways, it's kind of the grandfather of the current missions today.
Right now, a fleet of about 20 space